in order to facilitate the autonomous exploration of all diverse types of environments. And to that end, we developed the idea of collaborative walking and flying robots that through resilient localization and mapping and through resilient autonomy in path planning for exploration and obstacle avoidance and object detection will allow the autonomous exploration of any type of subterranean environment. And we are proud to say that we believe that this is indeed platform-wise and capabilities-wise the proper approach. And this was motivated from the idea of what is the minimum set of robotic systems that will allow to navigate all types of underground environments, regardless of the individual complexities. Of course, this means that we're not optimized for one particular type of underground environment, but it should mean, or we hope it means, and we are optimistic that this is the case, that we can navigate almost equally well any type of environment, being an underground mine, being a subway metro station, being at a natural cave such as those found in California, or being a natural cave with spacious environments such as those found in many other places around the world. So accordingly, today, my colleagues primarily will be telling you about our technological contributions across 5 fronts in resilient and versatile robots with dexterity, so legged robots and flying robots. And you see here Animal C and RMF, one of our 2 systems that we used towards the end of the competition. Resilient perception through multimodal fusion to penetrate extreme conditions of perceptual degradation, including self-symmetric geometries and dust, smoke, haze, etc., etc. Resilient autonomy and a unified exploration planner across legged and flying robots with the legged systems that specifically have handled also terrain, further accompanying this with a special planner that accounts for the terrain, the profile of the terrain, and so on and so forth. Of course, high-performance artifact detection and localization, and the solution we managed to arrive at in terms of communications. But here I already have to say that I think and we believe that many problems with communications can be offset with more resilient autonomy throughout the mission. And I'm not going to spend much time because it's only 5-minute introduction, but I want to honestly highlight that I think our team in the beginning faced a lot of problems, especially because we approached the problem with the idea of having legged and flying robots early on, no other traditional, more traditional, more mature type of technology to be used throughout the competition. This means in the tunnel circuit, we suffered a little bit. In fact, we explored most of the area there with the use of a roving system we repurposed for the purpose of exploration in the environments of the tunnel circuit back there at NIOSH. In the urban circuit, with much more time now from the tunnel circuit, we've had some level of maturity, but still face challenges with traversing stairs and other such environments. Indeed, however, we were further encouraged with the success of our colleagues, for example, from CoSTAR, who went fantastically well with the use of legged systems in this stage of the competition. And we arrived at the final event with more mature systems across all fronts, from robots to planners to multimodal SLAM and so on and so forth, in order to be able to resiliently explore a significant subset of the prize run of the DARPA SubT Challenge Finals. And this is the map that you will see soon from our side. And soon also my colleagues will explain all individual components from robots to perception to autonomy to allow us to reach this level and win the competition. Indeed, very close, for example, with the same score, but with small difference in time with our colleagues from CSIRO, and very close with all the other teams. So with that, I want to thank from my side, indicate that there are many lessons, of course, learned throughout the competition and many still challenges that could be solved better in principle, including, for example, better multi-robot exploration and multi-robot coordination with less need for human high-level coordination between what each robot does. But nonetheless, I think through the subterranean challenge, ourselves and all the teams reach a significant level of maturity and a milestone about the exploration of such environments. Last slide from my side, we have released and we try to release a lot of open source code throughout the competition. So if those are useful, we are happy that we have released them in the community. And if they are useful, please contact us for any further collaboration. Thanks a lot.
All right, thank you very much. So I think we're next. So I'll just share my screen. That's working. Okay. So I'm Jason Williams. So I'll be presenting here for team CSIRO Data61. So we're a collaboration between CSIRO, Georgia Tech, and Emerson. So this is the teams that we deployed through the 4 circuits, where the cave one, obviously, like that didn't happen, but we were able to operate our own event in Finals, Queensland, here in that time. So just an outline of our approach. It was all built around a Wildcat, which is a robust multi-agent SLAM capability with map sharing in between all of those agents. So we'll be talking more about that later on, but that enabled us to do a lot of things there. And so one of them was multi-agent navigation that provided us the capability to do map sharing, have shared traversability maps, frontiers, and all of that kind of thing. It enabled us then to do coordination through a multi-agent task allocation system where all of that information was shared in the same coordinate system, etc. So we had objects detection, again, with all of that information being shared in between robots. We had global tracking of objects, and then all of that information was shared through a distributed peer-to-peer database. So in terms of platforms, so we had robust tracked, quadruped, and drone platforms, and the droppable comms nodes, obviously. And I guess another aspect of our solution was that we emphasized the reuse of as much of the code as we could across those platform types. So, I mean, particularly the nav stack on the ground platforms across multiple types. There was extremely little that was unique to one particular type. So what I'd like to run through briefly here is just what the final run looked like for us. So this is the starting area up here. And so then we have the robots coming in. This is a spot going into the urban area that I'll focus on to begin with. So we'd had issues with the tracks that are up here in the early runs. So the operator focus was kind of on this up front to just give the direction that we needed not to go in there. So in the meantime, these other agents are operating autonomously. So this one, this is what the operator is seeing. This one's gone into that end cave and lost communications at that point. At this point, this one's gone also out of comms. And I think this agent got disabled on some tracks. And so at this point, this is the main one that that the operator is able to apply some control of. So briefly, this spot came back into communications. While it was out of comms, it had linked up with this other agent down here. So it came back into comms. And so the segments of map that you can see there made it back to the base. And so at this point, the operator has one robot which is within range, and he has a pretty good idea of what's going on, of like where the other agents are, and the fact that they're carrying more data. So like what's going on at this point then is a race against time to try to get this agent down in order to link that up. And I mean, here we are with 2 minutes left where that communications link is re-established, and that data is kind of finally coming through. So it was a very exciting end to that, and so there was actually more data in those robots that kind of made it through in the seconds after that clock ended. So that's our intro. This is the point cloud, but we'll talk more about this when we get over to the SLAM side. So with that, I will stop sharing. And I'll hand over to Team Marble. So Sean, can I hand over to you?
All right, welcome everyone, either good morning or good evening, depending on where you are. So I'll go ahead and share my screen now. All right, so Sean Humbert, Team Marble. Let me just take a quick moment to recognize all the really talented students that help support our program. So myself, Chris Heckman, Eric Frew, and Steve McGuire were the PIs on the project. Also had support from SSCI and Meshmerize as our industry partners. So relative to the mapping and localization part, Chris Heckman's going to be our panelist here. We came into the project with visual and radar inertial SLAM as our core competencies, but quickly after STIX, it was very obvious that sort of the inertial, LiDAR inertial stuff was the way to go. So we ended up using an optimization-based like smoothing and mapping technique, LAO-SAM. So we also had a number of features within our mapping. So we ended up with using an Octomap package with 15 centimeter voxels. So we had diff-based sharing and merging of maps between robots. And we also had a basic level of semantic labeling. And so we labeled traversability and stairs, because as we know, the spots need to go or be kicked into stair mode to be able to handle that stuff. From the mobility side, we fielded 2 Huskies and 2 Spots. We also had aerial vehicles to field too, but based off the course, we felt that these were the best platforms. The Spots were definitely a game changer, really opened a lot of terrain for us. And so Eugene Rush will be the person that will be our panelist for the mobility side. On the autonomy side, we certainly started this project off thinking this is going to be a showcase for autonomous robotics, and we designed our system to be really strongly, heavily weighted on the autonomy side with very minimal human supervisor interaction. But at some point, our system became robust enough so that we were actually considering the system as a tool. And in the final event, we actually incorporated some additional human supervisor elements that really helped us out. So, but the main pieces of our autonomy are graph-based planner. We had dynamical obstacle avoidance, pose graph sharing for deconfliction and coordination, and sort of a very elegant and computationally inexpensive terrain solution, which we'll talk about in our session. And then at the mission level, again, we were able to incorporate the human supervisor elements, which really helped us out quite a bit, and we'll talk about that. But that software is Bobcat. So on the comm side, we went through many iterations as we all did. I think for the final event, we just ended up with high power beacons that we're able to deploy from our comms droppers, which were the Husky platforms. But we had everything from small hockey pucks up to smart beacons that could do ICP and map sharing and so forth. But so Meshmerize was our industry partner here that really helped us out with the software side of things. But again, one of the main benefits of our comm systems is it was very modular. And so we're able to add a first person view. And we never really considered that in our solution until we got to the final event. And so that actually helped us out quite a bit as well. So for the artifact detection, we, again, many iterations here. We had sort of the RealSense cameras with all the USB problems that I think a lot of other teams were having. So we went to Ethernet connections. So we were running Gigi cameras and TensorRT YOLO for our classification. And then we used our Octomap to actually do the referencing and the distance estimation and localization for all the artifact stuff. And so Harel Biggie will be our panelist there to talk about that. So these were our final maps from our robots. So again, our Huskies didn't do a whole lot. They basically were just kind of, in the terrain that was accessible, then we were able to drop comms, droppers and things. But our Spots did most of the exploration for us. So that was the D01 and D02. And then just, our score was 18. I think our maximum feasible score was 22. 25 artifacts actually came in front of our sensors and our field of view. Adding that first person view was really critical for us. We scored 9 additional artifacts due to that functionality that we added basically at the finals competition. And we missed about 4 artifacts just due to human supervisor workload toward the end there. So again, our maximum feasible score is probably about 22, but we ended up scoring 18. So I think with that, I'll stop sharing and hand it back to you, Jason.
Okay, no, I'm good. Yes, you trying to mute that again, right?
Sorry.
Yeah. Sorry, we have issues switching in between systems. Okay, thank you very much for that, Sean. So we can move on to Explorer now. So Stephen, are you there and ready to take over?
I am here. Good morning. I'm going to share my screen. Can you guys see my screen here?
Yep, that's good.
Okay.
I think swap you.
Yeah. Sorry, what we're seeing is the presenter view.
Oh, okay, got it. There we go. Good morning. My name's Steve Willits. I'm a scientist in the Air Lab at the Robotics Institute at Carnegie Mellon University. I'm going to present this introduction of our team and some of our robots today. I will like to mention some of the sponsors that are shown here on the slides. We're very grateful for the support that they've given us throughout the last couple of years. Our team was basically made up of two universities. Oregon State University focused mostly on software efforts and mainly the object detection, global planning efforts, and coordination of the robots. While here at CMU, we handled all of the hardware design and builds, focused more on the perception, SLAM and mapping aspects, and the behavior executive with coordination between all the other submodules. I would like to, we had a big team basically over the last couple of years. We had a lot of people in the program throughout the years, but also a lot of students, just to mention some of the faculty and staff between the universities that worked on the program. And we were able to graduate 24 master's and PhD students and 27 undergraduate students. So this program not only touched the commercial side of robotics, but also a lot of our students are now applying the things that they learned from this program on their own. I mentioned the large amount of active members. These are just pictures from all of the events. We did attend all of the events throughout the program. And just to touch on what our high-level themes were, modular autonomy was something that we strived for from the beginning. All of the robots that we built for this basically can be broken into about 5 components: a rough and rigid steel chassis, modular direct drive, independent wheels, a power system battery, which consisted of 2 valence batteries, an e-box to run all the electronics, and then in the upper left, the modular payload, which I'll talk about here in a minute. Resilient autonomy was really the other thing we focused on, and I'm not going to get into the details that are going to be talked about later on, but you can see here at the top, the behavior executive was really the core of the system that was able to communicate with everything from frontier planning to what path we're going to take, and our local planners and recovery behaviors for getting through some of these difficult courses. So just quickly to show you the robots that we brought to the final competition, we had 3 ground robots, 4 of these smaller DS drones, and 3 Canary larger drones, and 1 Spot that I'll show here in a little bit. But I really just want to focus on the payload. Like most other teams, we carried a LiDAR, an IMU sensor, the superodometry that we'll talk about later on really fused. It's an IMU sensor-based odometry system with cameras and LiDAR as the secondary functions. I did include the specifics of the robots here, but I would say that the main difference between our 2 larger robots was an articulating chassis on this R2 robot. This allowed us to get through a lot of very rough, rugged terrain, whereas our R1 robot seemed to do better in urban flat surface type environments. And the 3rd smaller robot, this little guy was really our workhorse throughout the program. He came to an unfortunate end at the final day of the final competition by driving off a cliff, but he also has a articulating front and rear suspension system and also carries the same payload that our R2 robot has. We also used modular communication nodes, basically dropping breadcrumbs with Radiant Wi-Fi communications throughout the underground. These were fairly reliable communication systems for us. And here's just an overview of what the smaller drones looked like. Basically, we could get higher speeds with these drones inside small spaces. They were fairly crash tolerant, so we could run into things and not have to worry about the props being damaged. And an endurance of about 13 minutes actually allowed us to cover quite a bit of ground, and you'll see that later on how the drones played into our final runs. Also, the larger Canary drone, this had an endurance of 20 minutes. This one could not be launched from the ground robots because of its size, but this was really kind of our go seek and return with comms type of application. The final payload, our newest one, we did run this in the final competition. Spot was not a big part of our performance there. In fact, I think we ran it only on the final competition day. And that's kind of that's the end. Are there any questions?
So I might save questions for the panel sessions in the respective areas. So thank you very much. And so with that, can we move on to Team CoSTAR? So Ali, are you there?
Yes, I'm here. Can you hear me?
Yes, I can hear you. And
okay.
Your presentation.
Awesome. Hello, everybody. Good to see many of you again, and good to meet new people on this call. Good morning to everybody, or afternoon, night as well. It's 5:30 here a.m. So I'm Aliaga. I'm representing Team CoSTARs here as in the intro part, and later today our team members are going to cover a lot of technical details about our approach in this competition. Our team is a collaboration between NASA's JPL, Caltech, Professor Burdick's lab, and MIT, Professor Carlone's lab, CAIST, Dr. Shim's lab, and really Dr. Nikopoulos' lab. And we have had support of a lot of industry partners throughout the last few years in our efforts. Okay, there's a very large team behind the results we are going to present today at different talks. And in addition to our core team, we have had support from amazing researchers and students from several different schools and our industry partners, including support from our competitors in the competition that we collaborated with along the way in this effort. Okay, so why NASA is part of this? Initially, at the first place, our main motivation is to develop technologies and systems to help us explore one day real-world caves on other planets. This is a big target, an important target for NASA in general. Again, we will talk a little bit more about it later today. In terms of concept of operation, we relied on a multi-robot team where we had the robots had complementary capabilities from both locomotion and sensing perspective. We also had different computers and computational capacity on them. In terms of concept of operation, we relied on a concept where we deploy communication nodes, as you see the blue nodes here, like breadcrumbs closer to the entrance of the course to create a wireless mesh network. And as robots went further in, they left the comms, collected info, and came back based on certain triggers and conditions, and to be able to get the data and retrieve it in an efficient way to the human supervisor. Here are some of the robots we deployed in the last 3 to 4 years. We deployed legged platforms, wheeled systems, tracked robots, as well as drones. And very early on in the program, we also invested a little bit on this concept called rollercopters, drones that can roll on the ground but fly when needed to extend their operation range. At the peak of our development and peak of our operations, we were able to run 11 robots simultaneously, 4-legged, 4-wheeled, and 3 drones. In the background, autonomy-wise, we developed this product or software framework, we call it Nebula, that with the mindset of it being agnostic enough to the mobility platform that we can put it on all these different platforms that you saw in the previous photo. Here are some of the selected modules of this framework: robust navigation, mapping, multi-robot networking, task allocation, machine learning aspects to it, and traversability analysis, which we will be again talking and going into more details of these different modules later today in different talks. The modules come together in an architecture. Here's a simplified view of the Nebula architecture that we will be talking today about. But at the peak of what we achieved in the last 2 to 3 years are summarized at these numbers. In our best runs, we were able to go about 2 kilometers per single robot over extreme environments. And a single robot in 60 minutes were able to map up to 4 kilometers of these extreme types of environments. We were able to, at some of our practice runs, drop 35 nodes with our self-deploying communication system covering several kilometers of limestone mines to extend the reach of the operation. As I mentioned, we were able to, at some point, deploy and work with 11 robots, 4-legged, 4-wheeled, and 3 drones. But on average, we worked with 4 to 6 robots closer to the end of the competition. Machine learning-wise, in the final event, we were able to score 100% of what we the robots got to. And traversability-wise and modularity of the framework-wise, we were able to implement and integrate the framework on more than 14 different types of robots. With that, maybe a very brief touch on our timeline and some of the competition results. So as you all know, this was a very intense effort from the field testing perspective. We enjoyed that part of the effort a lot, and throughout the last 3 years, we tested in many different places across the country. For tunnel, we had tests in West Virginia and California mines. and then similarly for urban in various different locations. We had a little bit of a gap because of COVID, but then post-COVID, a couple months before competition where we got access to robots, we went to Kentucky and limestone mines to test in those classes of environments. A little brief overview of our strategy of deployment. SubT has been pushing both development of algorithms and advanced capabilities, as well as reliability of products that you deploy and they work. But realistically, in real world, there are constraints on how far you can go along this way. And there's a trade-off between this reliability and advanced capabilities. And this is how our team evolved in this trade-off. We started a certain level of autonomy, certain level of risk. As our time and resources increase, we increase our autonomy in urban and stayed similar level of risk. In final event, we pushed a lot on autonomy, accepting some risk, and that's kind of how our strategy and mindset of technology development evolved over time. If we knew what we know now today about the competition, probably we would have picked these kind of square points over the years, but we will be talking a little bit more about these in the later talks today. But those trade-offs basically shaped our performance over different competitions. Here you can see in the solution complexity side that our complexity increased over time and the level of autonomy increased over time. We also, you can see the level of risk we were taking as the solution were evolving over time. These trade-offs helped us to win the urban competition, to be second and to win the second and fifth place on tunnel and mixed environment. I'll show now some videos of our final run, very briefly touch on how things went, but I'll pick the second day that our robots deployment were successful. On the last day, we had a little bit of a hiccup with some of our calibration systems, so we robots need to came back and we do some of the work and send them in. That's why the last day is not very is not a complete run. So I'm going with the day 2 here with these quick videos for next 30 seconds. At the bottom right, you see the world from the robot, one of our robots' perspective as it explores the environment, and top left, the internals of the algorithms. In this run, we deployed 5 robots, and our best robot that you see here explored about 600 meters across 3 domains and traversed about 1.6 kilometers in total. Again, we will be touching a little bit more on these results in later talks today. With that, I guess this is my last slide. I already covered our high levels, and for more details, again, in the later talks, we can take questions today. Thank you.
All right, thank you very much, Ali. So next we move to team CTU CRAS NORLAB. So Thomas, are you on the line? I can't hear you if you are. So I can see your screen, but I'm not hearing anything from you.
Okay, sorry, my bad. I forgot to switch on the mic. Give me one more.
Yeah, can hear you now, but the screen sharing.
Okay, now it should be complete, I hope.
Yep, excellent.
Okay, done. So I'm Tomáš Svoboda, and I will tell a little bit more story about our team. So we are essentially 4 labs, 3 from Czech Technical University in Prague and 1 from University Laval. The 3 Czech labs are actually sitting in one building in Karlova na Měsí in Prague. So very compact environment from that point of view. Yeah, this is us. Most of the team members.
I just want to say I don't see full screen. Maybe Thomas, you want to maximize your view. I think everybody also sees your Slack and your machine behind.
Okay, thank you. Now it's better. Is it better now?
Yes. Now it's okay.
Okay. Sorry.
It's okay.
Now it's okay.
It's okay. Okay, thank you. So as you know, we started as a self-funded team, and the motivation why we joined was really that we were attracted by the topic, and because we were collaborating with firefighters and some other users, but the SubT challenge was really tempting us because it was really pursued for full autonomy, and we as a roboticists, we love to see our robots doing things by themselves. So that was the main motivation. Yeah, we started in a tunnel, not that many. We took our old robots and went into the competition. The good thing was that we really knew our robots. So we were really able to keep them alive despite their age. The performance was kind of okay. As we knew the system and the robots, we were able to push it to the limit. So thanks to the funding, we were able to continue. A little bit more robots, but still the old ones. We essentially borrowed a few robots from our colleagues across the Europe. With whom we were participating at the European projects. Yeah, and again, we loved the environment because finally we were able to show our articulated tracked robots that were able to descend the staircase and do all the mapping detection, despite the fact that we didn't have a 3D lidars. We were using this funny SIG 2D lidar swiveling from one side to another. And again, the overall performance was quite satisfactory again. So thanks to another generous funding, we were able to continue. So this is where we were after the urban. We were using the Husky, as many of you were. The articulated tracked robots we loved. The flying robot and a small hexapod, which was essentially too small for most of the environments in the end. So DARPA generously offered us for the last 10 months before the final event funding. So we were able to upgrade our robots. So this is our upgraded flying quadcopter. Interesting thing about this, that is this is the physical counterpart of the virtual one, which was very successful in the virtual competition. Many other teams were using this virtual quadcopter, and it actually proved it actually showed nice performance during the system final event as well. It's rather compact, can fly for a long, and it detected a few objects. So we opted also for the spots because we loved their performance during the urban by CoSTAR. And we even upgraded the old body. So we added the 3D lidar, redesigned the body, and added the new things. And we, of course, designed a new payload. And the intention was really to make it as same as possible for all those kinds of robots. And as already some of you mentioned, this gave us some advantages. And some in-house communication unit. This is us in Kentucky, all the robots. So we had a nice robots, but you know how the last year was. So actually, some of the robots came just a few days before we went to US, and one robot even came to us to the Kentucky just a few days before the competition. So for most of the last year, we had actually one running platform, the old Husky. So we didn't practice that much. We actually didn't practice almost zero from center point of view. So yeah, unfortunately, the final run didn't went that good as we hoped for. After some all nights effort, we were able to make all robots running, but actually many robots so performed suboptimally, to put it gently. The spot worked in quite fast, did its job, mapping, finding objects, and so on, but it simply fell too prematurely. So yeah, we didn't really master the walking pattern of the spot. So yeah, they were falling simply too often. Yeah. And here we go in the cave part, and now it's gone. Okay, so the result was not that good as we hoped for, but luckily, sort of, we were able to run our system in the virtual, where the performance modes was a bit better. And we really used the virtual environment for testing our system, because as I mentioned, we didn't have the real robots for most of the last year. So we simply resumed to testing within the virtual by necessity, and which at the end made our return home a bit sweeter. Okay, thank you.
Okay, thank you very much. So we're running a little bit behind. We have 2 more teams to go. There was a question asked about, can we ask questions in this part? So for everyone in the audience, like I think we'd like to keep those for the panel sessions in the various areas. So if you want to hold on to those for that point, they'll be welcome there. So if I can hand over to Kevin from Coordinated Robotics. Are you on? Yep.
I am on. Thank you.
Excellent. And I can see your slide. Thank you.
Okay, so my name is Kevin Knadler from Coordinated Robotics. We worked with California State University, Channel Islands, and a professor and a number of undergraduates there. Also worked some with the local middle school and a few other people from just the local area that were interested in participating. At the competition, we built, before the competition, 15 ground vehicles and 8 drones, and shipped 3,390 pounds of robots and parts and such to the competition. The team, here's a picture of the number of people, one of the robots there. You see some of the undergraduates, professor at CSUCI is there on the right. Some of the middle school students actually helped assemble one of our vehicles for the urban contest. We would have had them do some assembly for the final as well, but due to COVID, they were not having any club meetings, and so did not do that. Our overall strategy for communications was to use fiber optics plus a wireless mesh to improve our communications relative to the urban circuit. In the narrow sections of the course, our intent was to use wall following or manual driving, and then we had a frontier exploration that we developed for the open areas. In terms of traversability, use wheeled vehicles for the flatter areas, treaded vehicles for the stairs, and our aerial vehicles for the vertical areas. Okay, and then some of the issues we ran into, like everyone else, we had COVID issues. Didn't have access to a couple of the robots. That wasn't as much of a problem. We actually put robots with the students, and so most of the students actually had a robot at their house to work on. The bigger issue we ran into was the lack of in-person meetings. being pretty much a volunteer organization, a lot of the motivation for these students was working with the other students, having those meetings and discussing their progress. And so without that, it made it a little bit harder to really keep the team going and keep a high level of motivation. We had a couple vehicles fail before the contest. We had enough, so that was not as critical. At the contest, we'd shipped our robots to arrive on the 14th, and the team flew in on the 16th, but the robots were not there. We knew that in advance, but still it was not good. And so we had to have discussions with the shipping company a bunch to finally get them to release it. They are not going to release them for a few more days. And so we would have been unhappy if we would have had to wait for a while longer to get our robots. Our first practice run, we ran into issues with things such as the usual issue with Linux, USB things didn't come up the same on each different robot. And so we had some issues with just integration there. The second run, we started using our automatic alignment that used to get the robots initialized to position and orientation. But after they initialized, they would then crash. And so that was basically a software issue that we had. On the final run, we had some localization issues. In particular, as the robots advanced in, they would get lost fairly quickly. And so that was a big issue. But overall, our goal was to learn things and get a bunch of students involved. And so we did that. And we'll be having a number of students talk for other portions of it. Thank you.
Okay, thank you very much, Kevin. So finally, we go to Team Robotica. So Martin or Lisa, are you there?
Yes, I'm here. But I will ask Kevin to stop. Yeah, thanks. Just a sec. No stress. I'm sorry. Do you see my screen, please?
Yes, I do.
Okay, I will leave the talk to Lisa from Boston IBM, so you would understand a bit, and otherwise, like, yeah, enjoy. I hope it works.
Okay, so we're seeing slides, but we're not hearing anything. So I think the audio is not going through Zoom.
Okay.
It's okay now, Martin. Yeah, it's okay now.
So did you hear the?
Yeah,
I don't know.
I can hear you now.
We can hear you talking, but if there's a recording that's going along through the PowerPoint, we're not hearing that.
So when it shares through Zoom, there's a little tick to share audio.
So Navinder's saying that there's a little tick when you share, saying share audio.
Yeah, on Zoom, when you share your screen at the towards the bottom, there's a little tick box or radio button that says share audio. So maybe you'll have to stop sharing and then go back to share screen. Usually there's an option saying share audio.
Yeah, sorry for.
In large mega caverns, which was surely a mistake. There were also many other things happening. Ema was born 1 week before we left to Kentucky. Frantisek submitted his solution for NASA's Space Robotics Challenge Phase 2 shortly before SUT. The announcement of results was a day after SUT final second place. Congratulations. Martin was working on finalization of the automatic concrete factory line even on the day of our flight. Pavel and Spynek could not come as they had delivery of more than 100 sorting robots by the end of September. And yes, luckily the shipment of first autonomous locomotive was postponed to November. Robotica's solution was maybe on the other side of spectrum when compared to other teams. Robotica is self-funded teams and SubT Challenge was a hobby we did in our free time. Moreover, we participated in both system and virtual track as there was need of overlap as much as possible. The goal was to keep things simple, cheap and with large impact. The robots were fully autonomous, must from virtual track. Moreover, to establish communication for deep exploration is not cheap. We would love to reach similar results as our robot Freja in virtual cave circuits, where she traveled 4 kilometers. If the robots work on its own, they have to return home, in order to inform operator, and send localized artifact to DARPA server. As very important trick was symmetry of robots, so they can return via following trajectory the rear sensors have recorded on the way in. They are also redundancy backup, if the front sensors are destroyed.
Okay, thanks.
Okay, thank you very much, Martin. So that's the end of this introduction section. So at this point, I'll hand over to Sebastian, who's going to moderate the mapping part.
Okay. Can you guys hear me? Yes. Okay, cool. Yeah, so let's get started on the mapping section. I think that's going to be a lot of fun. So I'm going to be pretty brutal. If you go over 5 minutes, I'll stop you. so you know, I think there, and you know, we can have a lot of this because I think there's a lot of interesting questions to discuss about, and you know, I think we all can, you know, there's lots of talks on the methods that I think people have given. So let's not get too hung up on this. You know, I think you know, let's give everybody a couple of minutes to tell what they've been doing, and then I'm really excited about getting into some of the questions. So I guess we'll start, keep the same order. So Costas, I guess you're up first.
Not myself, but our team.
Or your team, yes, sorry, yes. Okay, let me set my timer. Okay.
Sebastian, can you hear me?
Yes.
Sharyar, perfect. So I'll start. Hi everyone, I'm Sharyar Khatak. I'll be discussing our approach on behalf of Team Cerberus in terms of localization and mapping. So our focus, given the DARPA SubT Challenge and its focus on navigation in austere conditions, we early on identified that multimodal sensing would be a key element of our strategy. And in this domain, we researched and developed a couple of techniques that exploited not only individual modalities, so given like LiDARs, inertial, thermal, and visible, as well as kinematic on robot setups available, but also exploring their complementarity or how they can be used in a complementary way. So multimodality was one of the key aspects or the key focus of our team. And as you can see on the robots below, so given their different payload capacities, we tried to make each robot or respect each robot's carrying capacity and equip it with the necessary sensing. So for example, on the bottom left is our animal robot having the highest payload capacity. It carried a LiDAR sensor for localization, 2 LiDAR sensors for its traversability mapping. It had an alpha sense unit with 7 cameras with an IMU, which was hardware synchronized. And then it also had, as a bit of other robots, joint encoders, which when coupled with the body IMU, the Bosch IMU, as you can see, gave us kinematic information. And then moving on to our central robot, which is our Charlie robot, which is a traditional flyer. It had a subset of all these sensing. So for example, it has 1 thermal camera, 1 RGB camera, 1 LiDAR, and 1 IMU. So a subset of the sensors that the animal robot can carry. And then there was our smaller robots, for example, the RMF, which had an IMU, a LiDAR, and a black fly camera for identification of artifacts. And then there was also the difference in compute capabilities of these different robots. So the larger robots had more power to power a higher performance computer, whereas the smallest robots also had low power computers. So our approach from the very beginning was to design an approach which would be flexible in terms of both the sensing modalities available on each robot, and then you can pick and choose what type of estimation you want to run on each robot and how you can fuse them. So it's a flexible approach. And then how we fuse it was in hierarchical fashion. That estimation would always move from left to right. And given the sensing available, you always will have an estimate and you will always have a map. And if an estimation solution is good, it will always propagate it to the next step, always moving from left to right. And we term the solution as complementary SLAM. Taking advantage of the complementary nature of all the sensing modalities that are listed on the left. And these health checks that I mentioned, they were both based on data level. So for example, for dust rejection in images, we were using temporal nature of spatial entropy to understand where the dust is and not track features on the dust clouds. And as well as estimation level checks, for example, in light odometry for a scan-to-scan registration, we would check the minimum eigenvalue to understand that how good this fit was. And if this health check was passed, this estimate would be again passed further down the line in the next step. So again, always moving from left to right. And the idea was that you always have an estimate of localization and you always have an onboard map. And this approach, CompSlam, ran on all the robots that were deployed in the final competition. So in the final competition, or in the final run of the competition, we deployed 4 animal robots. The names are listed here with their individual distances they covered with their maps on top of the ground truth map provided by DARPA. A total, they covered 1.7 kilometers. Now on the back end, we had a centralized mapping approach. So all these map as well as the onboard sensing data was sent back. And the idea was that this not only finds a multimodal constraint between the robots, but also it improves the graph individually and improves, provides a better map for the operator to refine or report artifacts. And this is the final map that the operators saw. And this was a combination of both the onboard localization method as well as the global optimization solution. We did suffer some global mapping setbacks, given that some robots came back later into the communication rate and dumped a lot of data, so constrained by time or optimization. And well, this was the final map that the operators saw. And yeah, I think I'm on time. Okay. So thank you so much.
Thank you. Perfect on time. Awesome. So one thing I wanted to say, so maybe while the next speaker sets up, please post questions if you have them right away to the chat and YouTube chat, the chat here, or the Google Doc or Slack. So I'll be monitoring all 4, and I think that's probably the best way that we can keep track of these questions. So next, I guess we'll have CSIRO go next.
Brian muted.
And then then we can we'll keep the questions coming, and then we'll try and get going.
Just checking you guys can hear us.
Yes, and you can see the slides.
Okay, hey guys, I'm Castro. I'm going to be talking about our SLAM solution, WildCap.
Just to get better access to that microphone, you might want to watch your laptop.
Right. Okay, so this was an overview of our map. So the colors show different robots, and the ground truth here is shown in gray, and you can't see much of it just because the map accuracy is quite good. So in terms of our SLAM solution, so I'll start with the hardware. We decided to basically have the same sensor pack on all of our robots. It's called CatPack. So it has, I'll talk more about CatPack, but basically it's based on a spinning Velodyne and IMU. So all of our robots, if you can see, all of them have a CatPack on them. Our drones have a different form factor of CatPack. It's called Hover Map. It comes from Emerson, one of our partners, which is a spin-off from our group in CSIRO. So inside the CatPack, as I said, there's a Velodyne. There are 4 cameras, which we didn't use in our SLAM solution. but we use it for point cloud colorization. And there's an NVIDIA Jetson Xavier, which is our compute for all of our SLAM. And also there's an IMU. On the right, you can see the field of view of our cameras, and also the sphere you see without the cones at the poles. That's basically the field of view you get from the spinning LiDAR. So I gave a talk recently at the Tartan SLAM series organized by AirLab. So that has much more details in it, but just as an overview of our algorithm, so we basically have a odometry module where we do local trajectory optimization in it. And the output of that is going to be a good estimate of the odometry and also submaps that are locally very accurate. And then these submaps are then used in a post-graph optimization module that you see on the right. And then we detect loop closures between these submaps, and that gives us global consistency. So we basically figure out where to put these rigid submaps and how to connect them. So some of the notable features of our approach, I've listed them here. So we use circles as the type of feature that we extract from LiDAR. We have an alternating minimization between finding correspondences between circles and optimizing the trajectory. As I said, there's a sliding window optimization where we use a continuous time representation for the trajectory. And we have M estimators to give us robustness against outliers. We do try to calibrate all sorts of extrinsics and other parameters online as part of the trajectory optimization. And one notable fact about our post-graph optimization module is that we do try to merge submaps when they do have a lot of overlap. This is because we don't want the complexity of the solver to grow with the length of the trajectory, but rather to be proportional to the size of the environment. So in terms of our multi-robot SLAM solution, what we basically do is that we share these submaps that we create based on local trajectory optimization modules between the agents, and then each agent solves the whole joint post-graph optimization problem by itself. So this is a short video of how this is going to look like. So the colors you see are those submaps. And then these submaps are put together using post-graph optimization, which gives us global consistency. So I'm going to skip this for the interest of time. You can see the loop closures that are detected. Some of these submaps are getting merged, and then you get globally consistent trajectory. So this is a video of our final map. I guess we don't have time for that. And then this is a fly-through video. So the longer version of this, again, you can find it in our recent Tartan SLAM series talk. So I just let this play, and thanks, Basti.
Okay, great. Thank you. And yeah, I mean, there's lots more details in the Tartan SLAM talk, and you can also check that out, and then hopefully we'll have some time for questions more detailed. Okay, great. Thank you.
Thanks.
So next we'll have Marvel.
Yep. I am waiting to be able to share my screen. Hi, everyone. Good morning, good afternoon, good evening. I'm Chris Heckman, talking briefly about our mapping solution for Team Marble today. So here's our sensor head. It was the same sensor head on all of our platforms. It was a 64-beam Ouster LiDAR, Lord microstrain IMU, and flash LiDARs and Big E cameras. The cameras were only used inevitably for the artifact detection. Here's a general overview of the evolution of our SLAM systems. And so we started off with visual inertial only, an in-house one, as well as a open source package. And we moved from using cameras to LiDAR, first a 2D solution, then a 3D solution. And then we threw all of cartographer out, and then we built up a LeoSAN solution that was customized for this. There were some really good advantages of using LeoSAN. If you've never tried it, it's a really remarkable package, easy to make modifications to, built on GTSAM. In terms of mapping, we used largely an Octomap-based technique. We also infused traversability information as well as some other semantic information into the map. This was built on a custom solution for us. As you can see here, for instance, the rails in this in the ground here in a tunnel-like environment show up as sort of a peak in a traversability setting or anti-traversability setting here, that then get promulgated into an Octomap, which then can be transmitted and deployed across different robots so that we actually can see where a robot might have trouble because of what particular item in the ground, for instance, and use different planners on different robots to be able to bridge that gap. So here's sort of an overview, top level overview of how we did sharing of maps and what information we did share. We labeled traversability and stair presence because of obviously some robots, the spot robots, can go upstairs and the Huskies couldn't. We were able to do this using some compatibility with our diff-based mapping, which was only sharing small submaps across agents, as well as compression of maps, and use this to be able to inform planners later on. This is sort of a timeline of how that worked. And here's a little video of our maps being populated. Just regular point clouds from the Aster to start, and then eventually some information for labeling of the point clouds, as well as the Octomap being populated here. Black is traversable, white is not traversable, and red is sort of about to be populated, sort of still uncertain. And the purple is our stair detection, as well as a simple planner going up the stairs. Okay. So we also used map merging technique, as many others have. Here we display just kind of an overview of it at the top level, where different misaligned information from different robots is merged into an aligned map here on a second robot. And this was used based on a low overlap ICP method that we developed for this application. Worked pretty well. We didn't end up having to do any postgraph optimization in this case, although the other solutions that people are discussing are really slick, and love to hear more about them in papers. And this is just an overview or an example of our Octomaps populating in this notorious cave environment here. I just want to talk very briefly about fog. So, many of us saw this part in the competition, and we thought, well, great, what's going on? We're totally screwed. Here's what it looked like in our Octomap. We ended up just teleoping and using first-person video to be able to get through this. But we also developed a radar-based technique that can see through fog that integrates with our Octomap pipeline and is supervised by LiDAR point clouds. Those of you that you've used radar before know there are a lot of false positives. This LiDAR technique essentially filters out the places where radar points do not correspond to LiDAR points. So if a LiDAR can see, a radar can see, and then on deployment, then the LiDAR is no longer used. And so this is just essentially a filter that operates over the point clouds that are coming from a radar. These are based on TI radar chips that we've published with in the past. And we've also developed this for full state estimation pipeline using radar inertial odometry on top of the radar Octomap mapping that works pretty well in this case. You'll see as we sort of move through this hallway, at least, that we can actually populate the walls of the Octomap and not sort of have so much drift that you can't navigate in this environment. So that's all I had to talk about. Perfect timing. Thanks.
Okay, great. Thanks, Chris. And I guess we'll move on to Explorer. Okay. And yeah, keep on posting questions in either Doc, Slack, or in the chat here.
Hi, Basi, can you hear me?
Yes.
Okay, cool. Yeah. So I'm Lucas. I'm Lucas. I'm presenting today for Explorer. I was the SLAM lead at Team Explorer. Me and Shibo, we were the main guys for SLAM on our team. And the main contribution, I guess we want to talk today is the superodometry algorithm. That's the brainchild from Shibo Zhao. And it's a pipeline for laser and actually multi-sensor registration. And it's an IMU-centric sensor fusion pipeline that allows us to integrate different modalities like the laser, as I said, the camera, thermal cameras, or depth cameras all around the IMU sensor. It combines the advantages of the tightly coupled methods with loosely coupled methods so that we have some factor graphs running separately and they can share some constraints and feedback with each other, but they're not, they're tightly coupled in a way, but also loosely coupled if you see it from another side. And for the SubT challenge, specifically, although we, in the course of development, we experimented with different sensors and different estimations, we ended up choosing the LiDAR inertial version of superodometry. So we used a Velodyne 16 and an XSense IMU, and that was basically the core of all our algorithms. The only, I think, exception was on the spot payload that we had an Epsilon IMU. Otherwise, this was the basic. And then the superodometry pipeline, it's a new pipeline. The IMU odometry is going to be running in the center. It's going to be fusing constraints from different modules, either the visual inertial or LiDAR inertial in theory. As I said, we basically just chose in our final solution the IMU and the LiDAR. So it allows for these different factor graphs to go on separately, and then just share some like sparse constraint between them. We have a paper on it, you can check that out. And then we did some contributions for the main things we contributed here, we were thinking about was the robustness of actually taking this algorithm out there in the real world and what kind of scenarios that we're going to find and what we need to do to make it like almost never fail. That was the main, like robustness was the main thing. So we did a new PCA-based feature extraction method for the feature extraction stage of laser odometry, such that we can get more distinct features from the map, from the input scale frame. And we also did an auto resolution algorithm to handle the range of environments. So something we used to face a lot was that we are thinking, especially, I think maybe a lot of people had this thing before the competition, oh, we're going to the mega cavern, it's going to be a huge environment, but also we know it's going to have small environments. And how does mapping handle that variation in the same run? Because it's common, I guess, for some algorithms to we set some parameters for one environment each time, and then it's hard to change them on the fly. And so we did something for that, where we considered the radius or the average distance from the robot of all the points we get, and then we adjust those resolutions on the fly. We also had to handle dust because our team is very heavily biased towards aerial robots. We had many aerial robots that were really fast flying, but the issue was that they would like get some dust around it. And so how can we maintain navigability and robustness for mapping even when we have quite a good deal of dust? So we just did a heuristic where if anytime we get enough laser points that are far away from the robot, we just ignore the points that are too close, because those tend to be, especially for the aerial robots, dust points. And the other challenge we had was handling the differences in our robot hardware. And so we have, in the drones, for instance, we have one NUC for everything, SLAM planning and object detection was actually running on a dongle. But for the UGVs, we had just one NUC for SLAM. It was our best computing platform. And for Spot, we had to run SLAM on our Xavier. Oh, not doing this. Yes. So here are some of our results. On day one, we had 3 robots, two ground robots and 1 canary drone. We had an interesting issue that day where the robots kept coming back because of the time, remaining time, some odd issue there with the standards of DARPA. And then on the second day, we did much better. we had 3 robots and 2 ground robots and 2 drones. And finally, on the 3rd day, we had 7 robots in total, and we were able to export the 26.
Lucas?
Yes.
We're out of time.
Okay, that's it.
Okay, great. Thanks, Lucas. And then, okay, next up, we have CoSTAR.
Okay. Can you hear me okay?
Yes.
Okay. So the CoSTAR's kind of overall SLAM architecture, the goals of the features that we want is to be robust, to be able to accommodate multiple heterogeneous robots, to be able to scale to large environments, and then to be adaptable to those different types of robots in different domains. And so this is the overview high-level flow diagram. On the robot side, we have different sets of sensors running different sets of odometry algorithms, which have health checks to then do robust fusion or multiplexing of odometry. So we get out a robust odometry. And then that goes into our global SLAM solution where we build a postgraph on each robot and send that as well as keyed sensor information back to the base station for a centralized SLAM approach. On the state estimation side, we use something called HERO, heterogeneous redundant odometry, where again, we have these checks on health, both on the sensor side, so think of it mainly on the LiDAR, also some vision side, and on the algorithm side, where we're running parallel odometry algorithms. We then check the health to say whether we're going to fuse them together or reject them or reinitialize them. And then that gets output in as our odometry. For odometry algorithms, there's a few different approaches we have, either coming straight from the robots with wheel odometry or kinematic odometry or spots visual odometry. We use one of the hover maps from Emerson, as well as one algorithm I'll talk a little bit about, which is our LiDAR odometry approach called Locus. It's got your typical, I'm not sure if someone can remove that notation of the line someone drew on, that'd be good. But we have a typical point cloud pre-processing and then scan alignment. The key parts here is that we're trying to infuse robustness within the odometry algorithms we're using, as well as in the robust fusion. So part of that is doing an integration of initial guesses from odometry and IMU to the scan alignment in a robust way where we can switch between them if their health is not great. Then we also look at ways of adapting the filtering based on the environment. So we have a consistent point cloud size to manage the computational load, as well as sliding maps to manage the memory load there. On the global SLAM side, we use an algorithm called LAMP, Large-Scale Autonomous Mapping and Positioning. The key parts is a centralized SLAM approach with outlier resilient postgraph optimization and prioritized loop closures. So the diagram that we see here is a bit of an overview. So for each robot, we get in an odometry source from HERO, for instance, and use that to build our postgraph, as well as adding IMU factors. And then periodically, every 2 meters or so, we add a point cloud, which is adaptively filtered to be consistent size for the environment. That information is sent back from each robot to the base station, where we fuse it together through inter-robot loop closures and do our postgraph optimization, and then send back the multi-robot postgraph. Let's see if I can clear this. Okay, there we go. So the benefit of the multi-robot approach is that we can have enhanced accuracy for the multi-robot overall localization, but it also brings challenges, such as how we generate loop closures accurately, how we address the risk of false positives, and then how we deal with the scale. And the scale also increases the risk of false positives. So we tackle these in a few different ways. For the loop closures, it's primarily a LiDAR-based approach, but we search for loop closure candidates with an adaptive range, where we increase the range based on the uncertainty, and also using the communication nodes as artificial beacons to say we definitely have visited that location before. This is for the deployed communication beacons, which we'll hear about later. We then accumulate nearby scans and do some robust initial alignment with the LiDAR scans, for instance, using Teaser++ before doing an alignment with GICP. But the way we tune this is a little bit different, because we want to absolutely make sure that if we do have just one loop that comes around, that we capture it and can use that to improve any drift. And so we allow a lot of loop closures through, which means we allow a lot of false positive loop closures. Hence, we rely on our robust postgraph optimization. This is really core to LAMP, is we use graduated non-convexity. It's an algorithm that can allow up to, or can handle up to 90% outliers. And that's integrated through GTSAM and Chimera RPGO. And that allows us to be robust to these outliers. So an example here is this is a prelim 2 map from the final. Different colors of different robots. And you can see these white lines. It might be hard to make out. They're false positive loop closures. They're loop closures that are matching between clearly not the same places. But we're able to handle that, and the map is consistent. We turn an outlier rejection off, then the map's an absolute mess. Now, obviously, we'd like to improve the loop closure side to minimize the false positives, but in the system that we have, we found this was quite effective for us. It also shows the power of this GNC algorithm. Now, finally, on the scale, what we do is we prioritize the loop closures. There may be thousands of loop closure candidates we get with multi-robots. And so part of that is prioritizing based on observability of the point cloud in the point cloud pairs that we're looking to close a loop. We also do a loop batcher, and that batcher looks at the structure of the graph and picks a subset of candidate loop closures that is going to maximally improve the error in the graph based on the graph structure. Those go through in a queue to a parallel loop computation. Then there would be things that come through that, the loops that come through that go into the post-graph optimization. When we change to this framework, we're able to increase the throughput of the number of loop closures we got by 6 times and have a 45% reduction in the error compared to just computing loop closures as we detect potential loop closures. Some example maps just to wrap up. On the left is a large kind of exploration in the limestone mine with a single loop closure. So we're able to capture that single loop closure and get a consistent map. On the right is a similar environment, but much more complex. So lots of narrow corridors that are very self-similar. So a lot of aliasing, a lot of chance for false positives, but with the outlier rejection, we're able to have a consistent global map there. And with that, I'll finish up.
Okay, great. Thank you. And, next we have CTU CRAS NOLAB.
Do you hear me?
Yes. Can we see your slides?
So my name is François Pomerleau. I'm from Laval University in Canada. I think I have to share my time with my Czech colleague, so I will make it very short. I need to say I thought it was more an open discussion, so my slide will be very high level, and I will actually ask questions at the end because it seems that there is more question about questions in the chat than actual questions. I will talk about mostly the UGV mapping. So we essentially use only LiDAR MU odometry for our solution. We had 2 type of LiDARs because we couldn't agree actually on which one should we use. So on our side, we went for LS LiDAR C16, so 16 beams, 200 meter range. And then we also try with the 128 Oster sensor. So that's one of my first questions. Would you prefer high-res LiDAR over long-range radar? So if you have comments or thought about that, it would be great to hear about it. We use the Xsense MTI 100, and we do incremental mapping without global optimization. Actually, our solution as visual odometry, we know that we drift under 1%, and that was good enough for the to get points actually on the course. So that's my second question for all of you. Do you have the feeling that it was necessary to have a loop closure algorithm running on that course? We are super lightweight for our odometry, so we downsample to 2,000 points per registration to make it work. All of our code is available, and we run that node since many years, and we are based on lib point matcher, which is also online. Key elements, so we use point-to-point estimator deskewing. We have dynamic points removal for the smoke and the element moving in the environment, and all of that was published many years ago. We slightly modified our mapping to be constrained on gravity vector. So essentially, we minimize 4 degrees of freedom instead of 6, which was good enough most of the time since the environment, at least in the urban challenge, was rather flat, but it was also reducing a lot the drift even in the final. We tend to use our LiDAR dosimetry on kilometer scale maps. So we have a tiling system. Here we see actually reloading the map when we are getting close, but at the scale of the environment, that was not that much necessary. So if you spend most of the time in the middle, we had most of the map in memory, but we were still super quick for the computation. And here we see that that was on the after test even. We didn't drift that much on our LiDAR odometers. Then one of the questions is what happened during the competition. We reported very bad deviation for a couple of points. Here's the actual map after we cleaned a bit. We had quite some struggle with the initial calibration. So that's my last question for all of you. I didn't hear about any strategy for your total station and your initial calibration. I saw that some of you have the map cut over here, and some of you also start only here. We also didn't have good communication, so we only reported topological map. This is why you see those kind of weird blobs over here, and that increased the deviation. And my colleague will talk about LOM, but here we process their map where we drift a bit less. So if you have any answer to all of my questions, if you have other questions, please let me know. I will hand over to my colleague. Do I do that? No, how do I? Here we go.
So we have 10 seconds.
So maybe not to my colleague. So for the flying guy, they were using LOM with a mix of Octomap. And they had a couple of problems in the long corridor. It was coupled with the fact that the Ooster was short range, so 60 meters. And they were reporting a couple of meters of drift, but in general, for a lightweight flying system, they were able to fly actually quite well in the environment. That's about what I could say.
Okay, next we have coordinated robotics.
Can you see me okay, or is that showing the presenter screen?
This is the presenter view.
Okay, sorry.
You can also click swap displays if it doesn't work.
I'll just go with this. This will be fine. I only have a couple slides. So hi, everybody. My name is Jason Isaacs, and I'm an associate professor at California State University, Channel Islands, and I'm going to be talking to you about coordinated robotics approach to mapping. So like a lot of the other teams, we tried to have a modular sensor tower that we had common sensors as much as we could across all of our platforms, in particular our ground platforms. And here's just an example of one of the tracked vehicles we had. So we had LiDAR sensors. We did have a mixture of different LiDAR sensors across the different platforms, but they were similar enough that it worked okay. So primarily we used Velodyne VLP-16s or VLP-16 lights. We did have two OSO-64s that were primarily used with drones or in the after event testing. We used depth camera Intel 435 eyes, as well as a fisheye camera for object detection. And then our IMU was a MemSense MS IMU 3025. Not all of our platforms had this IMU, and so that kind of changed how we approached a SLAM depending on if we had the IMU or not. The algorithms we used were the LeoSam primarily. I know other teams had mentioned this before, and these were this was what we used on any of our ground vehicles that had the nicer IMU. For the ones that did not have the IMU, we used Lego Loam Bohr, which is derived from the Lego Loam papers. And then for some of the drones that didn't have IMU, we used our tab map and the depth cameras. And then some of the drones actually had the nicer LiDAR units, so we used LeoSam on those. We did run into quite a bit of problems at the course, as you might have seen in the videos of our runs. So prior to the competition, we primarily tested our systems on the Cal State University Channel Islands campus, which was largely just large courtyards and outdoor spaces. We didn't have access to a lot of narrow corridors and things along those lines. So you can see a map here on the right of a map that we were able to produce with our system in sort of the courtyard outside our building. But at the competition where the corridors were much tighter, our mapping solution failed rapidly upon entering the course. We were able to kind of figure this out during the post-event testing phase. And so we ran some tests where we were trying to compare the LiDAR. So we mounted the VLP-16 and the Ouster OSO64 on the same platform and then manually operated the robots through the urban and tunnel sections of the course. And we were trying to compare the performance of LeoSam with the inputs from each of the LiDARs separately. And what we found was that there were 3 parameters on the LeoSam algorithm that if we had been able to fix these during the competition, our mapping performance would have been greatly enhanced. So we ended up disabling loop closure, setting the algorithm to indoor mode, which is probably as big a thing as anything. And then we adjusted the parameters to trust the IMU more with the roll pitch yaw estimation. And so here's pictures of the 2 different maps that we were able to produce during this this extra run after the competition, using the Velodyne VLP-16 on the left and the Ouster on the right. And you can see that during the urban and tunnel circuit sections, both held up pretty well. But once we got over into the large cave section on the sort of rear of the course, the Velodyne solution started to drift a little bit, whereas the Ouster solution held up pretty well throughout all 3 of the sections of the course. And so that was good for us. Okay, thank you.
Thank you.
Sorry to go over.
No problem. Thank you. So next we'll have Robotica.
The map had to be published to DARPA's server in the finals for all teams, including self-funded teams. Our bandwidth was very limited, so only regular 3D position and artifacts were shared among robots in the base station. In order to publish map data, the robot had to be in Wi-Fi range, which we discovered only reached the first intersection that lead to the 3 distinct sections: urban, tunnel, and cave. The robot had to return home after performing deep exploration in order for the operator to see the detailed 3D point cloud map. For the SubT Finals, both robots Skitty and Clawback K2 used a pair of 2D lidars from SICK and Intel's Reolsen's depth cameras D435i and tracking cameras T265. The robots create their own local map and evaluate terrain traversability. The list of available directions is then published in the form of a 360-degree scan. The bundle of tracking and depth cameras worked very well, as one can see on the data collected by Skitty and Vipastek Cave in the Czech Republic.
Okay, now I will try to show you the video. As Lisa said, this is because like in the finals, the robots really didn't go that far as all other robots. So this is in the Czech Republic in some publicly or public cave. And I was quite surprised with the lightning, with the light conditions, and just the combination of the RGBD camera, the data sense depth camera, and the tracking camera. Like you can see it's quite dark there. It's, I think, tracking nice, and we might be like speed it up. So, and it's really like quite cheap solution compared to like 3D lidars. I know that like most of you use the cameras. I don't know if you use the tracking cameras as well, or you combine. So on our robots, we had one in front, one in back. And yeah, now there will be some quick like drive through. I think it's like a few hundred meters. It's not that far, but still, if it's just this pair of sensors, like for me, it was like nice to have. Okay, so now I would leave it to like discussion, because I'm sure there'll be more interesting things. Thank you. If I can stop sharing. I hope you heard anything.
Yeah, awesome. Yeah, thank you. Yeah, thanks everybody for the presentation and staying on time. And I know there's like a lot of exciting details and things that could have talked about. So I'm really happy that you tried to restrain yourself. And so so maybe I can kick it off with questions. Please post them either in the chat or on Slack, or I also see a bunch in the Google Doc. And I think Navinda has been copying over the questions from the YouTube stream over into Slack. So I'll start with one question. So in the end, everybody kind of arrived at LiDAR plus IMU. It seemed like as the modality. I mean, maybe the one outlier is a spinning LiDAR versus a static LiDAR. But is that the end? Like, is there a fundamental limitation to visual SLAM? Let's say, that. Can we, do we give up now? Like say LiDAR is the only way to go. Like to hear what you guys
I'd love to start with answering that question, because I think that it was funny at the debrief, people were like, oh, mapping and localization seems solved. And I think that with a LiDAR, it definitely is highly accurate when you're moving at the speeds that we're talking about and environments that we saw here. And this is not the worst environment for a LiDAR, as we all saw, right? I mean, vision, this is not a good environment for vision. And so when you think about what you need to bring to the table for vision, like an active illumination, or being able to reduce specular highlighting as a result of shiny surfaces, these things were the places where we saw our vision system just like fall apart, and why we inevitably moved to LiDAR. I think that the research to be done in those areas is pretty compelling. And I would also say finally that vision is an amazing sensor. Everyone used a camera, right? We just decided not to use it for our localization and mapping components. Most of us didn't.
Oh, sure.
So we just added the sensor onto it to help.
Yeah, I mean, I'm just curious, I've not seen a drift rate from a visual SLAM system that's less than a LiDAR SLAM system. Is that a fundamental limitation? Like, is that?
So the other way around, what would be the good environment for vision and bad for LiDAR, for example?
Well, I think Tim and Victor tried to produce one in the final challenge, right? Basically, you had a like nice and featureless corridor that wasn't quite as bad, but could have been bad.
It was also bad for visual because it was a very wide corridor. So
sure, and it was bad for vision and for LiDAR, I guess. Yeah.
But in that corridor, it wasn't long enough. The Velodyne could see both ends of the corridor, so it was mostly fine, I think.
Yes.
I think it was 30-ish meters. So, and it was white, so you could clearly see the reflection on the other side.
So I think that focusing on the environment that's bad for LiDAR but it's good for vision is a red herring, because you can put a camera on some platforms or on many platforms, but you can't put a LiDAR on every platform. So I think it is use cases. It's not just environments that we should be considering.
And to be fair, everybody had to use cameras for the artifact detection. So it's not that it's a useless sensor. We had to use it. There's no way to detect artifact with LiDARs. I'm
right.
not against it's not a good
I
fight.
think it was interesting. There wasn't like a lot of, let's say, or radar or ultra wideband ranging radios, or like, there would have been there's a pretty big solution space, but it kind of converged to a LiDAR plus IMU system, I think, in the end.
I was wondering, for radars, was there anybody that used one? Could you see through the walls, or even in the post-event experiment, was there someone deploying
So yeah, we ran radar in the post prize run, and there are reasons for that related to integration. But as far as the data sets we collected, we did not see through the walls with the radar frequencies that we're using, 76 to 81 gigahertz.
Okay. No, it was a mystery for me if somebody could see through the old core.
Yeah, maybe at a lower frequency, but at the frequencies used for like automotive grade stuff, then it reflects on PLA, for instance, like a thin sheet of PLA.
Yeah. So maybe another question. So we saw some teams. I guess most teams had some sort of loop closure in the SLAM system. And I guess some teams relied on it more and some teams less, right? I'm just kind of maybe speaking for our team. We did have loop closure, but it didn't really, we mainly relied on odometry. Like it was kind of, I would say like 95% odometry and maybe some small things for loop closure. We didn't run loop closure, for example, on the drones. I saw, I think maybe JPL's approach, or like the CoSTAR's approach, I think was very heavy on the loop closure, if I remember, and maybe also CSIRO. So it would be interesting to kind of hear your opinions. For example, we implemented like a multi-robot loop closure merging, but it decided it was too fragile in the end, and we didn't want our map to be messed up by some kind of weird loop closure event happening. So I'm curious to hear your opinions on this.
Yeah, so with a heterogeneous robot team, you may have different capabilities of localization, and so that's where I think we initially felt the same, that there was a risk that one robot going wrong, having a bad loop closure, could destroy your complete multi-robot map. That's why the kind of the outlier rejection stuff I was talking about was so important. But then once we got that implemented, then we found that you could save a robot that was having issues with its odometry through the multi-robot loop closures. And so it was more robust in that sense, that if you had a robot that was not doing as well with odometry, then we were able to kind of correct that and still have that robot to be useful. But yeah, having the outlier rejection was critical for that, because otherwise it's too risky.
Yeah, so just from our team CSIRO Data61 perspective, I think, we didn't really necessarily have to rely on loop closure, but as part of the multi-agent solution, it's doing loop closure as part of the multi-agent solution. So yeah, I think the odometry is good enough, especially for a small course like this. It was fine. I think for a much bigger course, it would have been a lot more important for us. And I think just briefly going back to an earlier point about why LiDAR, one of the things I think we haven't touched on is the field of view of these LiDARs is very good in general compared to cameras, unless you're fusing cameras, and I think that adds a lot of the constraints into the SLAM solution that maybe the camera's not providing.
Okay, cool. So maybe next question. So in the course, maybe we can just go around the room, like everybody can just comment. Did you have a situation where you experienced SLAM drift, and then maybe kind of related to this what about some of the fog smoke that DARPA set out? So maybe we can just go in order. So let's start maybe with Cerberus.
Yeah, so our solution was more like yours in the sense that we had heavy reliance on the odometry for the robots individually, and then the backend was handling a multi-robot separately. Drift was similar on the order of magnitude, like 1% per 100 meters. And the further the robot went, we did see this. We were thinking fog would be a huge problem, but how DARPA used fog is like they triggered it when the robot went in there. So typically, like the SLAM had a map already available. And then if you have some kinematic information and the robot keeps walking, you just like fit into the map again. So it just sort of like mitigated that effect. It would have been very tricky that if there was like consistent fog, like you enter into an area that was already foggy rather than triggering, and then you were in a corner situation where you never had a look ahead map built in. So that then like you had complete degradation. So fortunately that was not the case, or we didn't encounter that. So I think that also helped quite a bit in the LiDAR situation.
Yeah, just a quick comment on the fog and LiDARs. One of the things that Velodyne has that Ouster doesn't have, or at least until recently, is dual return mode. So it can penetrate through fog. So you can pick up actual structure. I think that's, you can see a trend in people using LiDAR and the issues they had, and Velodyne and maybe less issues. For us, it wasn't a big concern. And then in terms of, I guess the robustness picture, one of the comments from the team was that even when robots were falling over, there was still, the solution was okay, but sometimes the mechanical shock would have dropped out the LiDAR messages, or maybe there was a massive spike in the IMU. They were the things that caused some of the issues.
Okay, so for you, it was more like a kind of a data drop that would cause a drift or something like this?
Yeah.
Yeah. Okay. Okay. What about Team Marvel?
Yeah, we saw one place where there was some pretty significant drift, and we believe it was also because of message dropout and some IMU timing that ended up desyncing PTP on our LiDAR and IMU, and that was pretty catastrophic for that particular place. But with the fog, actually, our LiDAR solution continued operating through the fog. It was just that our Octomap, our mapping solution, ended up thinking that there were large obstacles in front of us that had to be sort of, identified as false positives by the human supervisor and teleop through.
Yeah, so I think maybe I can talk a little bit of Expo, and maybe Lucas can chime in. I think one of the things that we saw is that the fog kind of initially was very heavy. So I think the biggest drift we saw was when our drone flew into the tunnel in the fog. I think we saw a lot of drift basically. It flew into into a big wall of fog, and that kind of got it stuck. and then it backed out of it. And so we saw, I think, like a meter or something like along those lines. Or Lucas, what was that drift?
Just I don't know if there's a separation here between the idea of fog and dust, right? But there was a fog machine from DARPA, and there was the dust that we got from flying the drones, and then it brought up the dust itself. But in that case, I think you're talking about, there was a heavy dust on the tunnels close to the tracks, and then our drones were a little confused by it on the mapping. There was some slant drift there, and it was pretty impressive. I think maybe John shows it later on our team, how the drone actually recovers from that, even though it gets stuck to the wall for a long time, but then finally recovers and doesn't fall out. That's pretty cool. And then when it comes back to the metro area, it just uses the previous map it had, and so it relocalizes and it recovers from that drift. I think another interesting thing where we drift was on our tree, our smaller ground robot, which actually did the most of our exploring, and it kept drifting more and more as it went more along. So I think this is something we see on our SLAM systems, that maybe we worried more about it before the challenge, where we think we're going to see like these really long, large environments, and we're worried that it will drift a lot after a long time. And we mostly didn't see it, but our tree, which were the robots that actually did explore very far, we did have some accumulation at the end, where it was starting to get into more than 5 meters, but it never got to that stage.
So on the two parts, on the fog side and kind of where we had issues. On the fog side, and this comes back to the discussion about using the vision modality. So the spots that everyone was using relies on vision for its locomotion, and that's kind of something that we also drew out from it to use. So it's got its own integrated 5-camera RGBD VIO, using the depth as well, which we found was pretty good at a lot of things, but still not as accurate as LiDAR. But we also relied on that for our local state estimation to be able to be integrated in that traversability loop. And that's where we found issues with the fog, was in fact on the cameras that were on the spot, in getting that state estimate from its internal VIO. But the LiDAR we didn't see issues with. What we did see issues with was falls. So our system was able to get up from falls, which is obviously great, but the testing we'd done was in a much larger environment. And so the falls in larger environments we were able to recover from a mapping sense, but we had a fall in quite a constrained passage, and that led to an accumulation of error in that high dynamic movement. So kind of that area of robust perception over falls, if you've got a platform that can get up, is an interesting area that we're looking at going forward.
Yeah, cool. CTU CRAS, NOLAB?
Yeah. On our side, so we investigated fog many years ago with firefighters, and we quantified that too. You need to have a very high density to make a difference, and typically that's the front edge when the smoke machine is starting. So during the competition, it was really light on our side, and if you want to eyeball it, if you see through fog, the LiDAR will see through fog without any problems. So unless DARPA would just keep the machine on at full power, it would be hard to affect. And our technical solution is that we also have a dynamic point detection and removal. So whether we see that front edge or not, it would have been removed. But in general, on our run, we were very light. And maybe it's because we didn't explore that much, but it was very light on the fog for us.
Cool. Coordinated robotics, any?
Yeah, so I would say that, as I mentioned, our SLAM solution failed during the runs, but in post-processing the data after we returned home, we saw that we were thinking that maybe the fog had a part in that, but we determined that it really wasn't that much of a problem for us, maybe because of the reasons everyone else has mentioned. In the post-event testing, we did see some drift when we transitioned from the tunnel circuit into the cave circuit. We're not really sure why that occurred. Did anyone else see anything like that?
So much. Okay, and then any opinions? And maybe Robotica, do you guys have any code?
I can just quote it, like, we didn't have any problem because we didn't get that far. But yeah, so like we were handling the fog, but the virtual one, which was really kind of easy compared like with the median filters. But what we like observed in the case on, it was like transition of temperatures. That was really deadly. It as we use only the 2D lidars, it basically like closed. So like all readings were suddenly like 20 centimeters. So I think there was no easy filter for that. Yeah, but no issues in finals. Sorry.
Okay, so maybe next one we can just kind of open up to anybody. So, you know, if you had to do the SubT challenge again, you know, what would you do differently in terms of
For me, I asked Timothy to be in the jungle, so something that moves actually, that it's way more dynamics for the environment, because the wall were quite easy to localize with, if you compare to some sort of soft objects or tall grass and so on. I think that would be the next challenge.
Yep, I think from the point of view of the organization, it would be interesting as we train a little bit for this on preparation, where we have multi-level scenarios. So we have 2 floors overlapping, and that would probably create some confusion for some mapping and some other planning stuff, and having the robot needing to go through the stairwells. That would be much harder than we actually saw it.
On that note, how badly would it have messed things up if DARPA decided to put in an escalator or a lift in the course? I know Victor's on the call. Victor probably can answer if he wants to, but just from a theoretical point of view, do you think any of our SLAM solutions would have been robust to that if it was there?
I'll say from the DARPA ideation process, those were both very very possible up until kind of some later stages of the course development. So it's a good, valid question, and one that we were interested in kind of exploring as well. Both the lift, like with the door closing, opening in a new location, and then like a moving floor.
So, I mean, I'll be blunt. When we saw videos for the courses, then we kind of scrambled, right? I'm sure many teams did this. And so if we had seen a lift, then we would have probably added a barometer and started doing filtering. And this had actually been discussed of like, how do we get really accurate floor localization, which floor you're on? And I mean, just to answer the main question though, I think that we would have spent less time on in-house built solutions that were built from the ground up. We would have started using solutions that were built on open source like frameworks much earlier, and that was a good lesson for us.
It's interesting though that some of the open source frameworks came out later in the competition. So we picked up some and started from some open source frameworks at the start of the competition. Actually, first of all, what we changed, the first 6 months, we were doing mainly vision-based solutions for hybrid mobility platforms. And so the dust was a really big challenge there. And then kind of after sticks, that's where we transitioned to LiDAR. So starting again, we'd start with LiDAR and IMU straight away. But yeah, like LAO SAM that a lot of the teams are using, that wasn't out when we started developing our LiDAR solution. And so it's interesting that kind of the community develops things, and there's more open source that comes out as we go forward. But it definitely would start with LiDAR from the get-go. Rather than kind of putting that division with the dust challenges that we had as well.
Yeah, so we started initially with loam, basically, and then actually had a lot of, it took a while for us to be convinced that superodometry is better than low, basically. And so I think in the end we were quite happy. But yeah, it was a process for sure, and it was a risk.
And one perhaps interesting point for this, of a different approach we took for some of our robots, was we got some of the sensors from Emerson with the, I guess, Wildcat under the hood and the rotating hover map. And so it's interesting to think about where there's a solution you can get off the shelf that is a SLAM solution, of thinking about whether that fits into your overall approach in terms of, there's obviously integration questions and challenges that you don't have. It's a black box. But that was an approach that we found what was effective for us for some part of our solution. When there's like a full SLAM package, you can get kind of like the T265, but on a LiDAR sense.
Yeah, so that, and I think there was a question also in the chat on the, you know, about, you know, risk versus innovation in some sense for this challenge, right? Like, you know, use off-the-shelf methods. So I think we saw like a mix of like custom, off-the-shelf, completely new methods. So yeah, it would be good to hear from people what the trade-offs were and thinking.
For CoSTAR, our strategy generally was, if it's something that is reasonable to buy and you can get that capability and it's not a critical part of your solution, and you can focus your time trying to innovate on parts that you think are important to differentiate, then do that. That's kind of the general philosophy that sometimes didn't actually exactly happen that way. But for instance, you get a Boston Dynamics spot and you focus on the autonomy on top of it. You're not building a robot that can do legged mobility. So same thing for the perception side, trying to get as much capability straight away that you can pick up, and then innovate on places that differentiate from what the state of the art is.
We gravitated towards like having this parallel path kind of de-risking and escalation procedure for different technical solutions early on that would then be winnowed down as we got closer to the events. And what that generally resulted in is our team was almost entirely graduate students. So graduate students taking individual packages and seeing what they could do with one, and then sort of having almost like we had literal like bake-offs, we called them, like, oh, you know, we're going to run solution A and solution B side by side and see how they work. And if you didn't build it from an open source package or something that was fairly well developed that could be customized from that, then we ended up, you know, basically removing it. So that's the biggest problem, was that we had this 1 year long sort of delay between instantiation of the award and the first circuit event, which meant that we had 1 year of parallel paths, and that was a lot of wasted effort. So there was sort of pros and cons to it.
From the CSIRO side, you know, we had a solution that we'd started before SubT, based on, you know, a number of years of experience building SLAM solutions, but SubT provided like a perfect use case for the multi-agent side of things, and you know, it really helped us push a lot of features and a lot of the performance into that in-house solution. So, you know, it was just a perfect event to help push the development of that technology for us.
From Cerberus side, we did keep an eye on what was in the open source, but we gravitated towards controlling the full stack because in our opinion, that helped us solve a lot of edge cases. So having full control of the stack, for example, like dust, fog, these cases that you saw, or degeneracy in corridors, if you don't have a full control over your software, for example, if something is just providing you an output and you don't know when it works and when it doesn't, then you spend a lot of time in building a health checker rather than actually solving the problem. So we gravitated towards always like seeing what's out there and then taking the good parts and then bringing back to our stack. That had been our strategy from the get-go.
I think for us, we had the fully not invented here syndrome. So, but I think anyway. So I think one thing that I just wanted to ask, kind of broadly is, I think I saw a lot of low-cost IMUs. Like I didn't see anybody use, hey, let's get a, I don't know, HG 1700 or like a nice IMU, put it into our robot, and then correct a little bit with LiDAR when we have it, or something like this. Any opinions on why? I don't know, like a nicer IMU would have been like 2 Velodynes, I guess, or something like this, or 3.
Question about the Velodynes, especially with CoSTAR, where at least there were some robots with a high density of Velodynes. Were there any issues of interference between Velodynes?
Not that we saw. No, I didn't see issues with interference between Velodynes. There was, yeah, we changed configurations around a little bit. Sometimes there was like direct kind of impacting the other one, but I think we tried to deconflict that, but we didn't experience any issues with interference. On the IMU question, we did actually purchase a laser ring gyro, single dimension, and we're looking at using that as like a tracking heading. So, you're being one of the things that was a big challenge, but we didn't end up doing it, just prioritization of resources, I think, because we'd moved far enough down the LiDAR track that we thought that was going to get us most of the way there. But yeah, we thought it could have been a good idea as kind of really an extra bit of information, but I think we thought the resources were better spent on the LiDAR solution.
Yeah, like
Was there
one
any
point to
teams
the, one point to the IMU, like an INS or whatever, is export control is really difficult for us to fly. So that was a consideration as well.
So when we talk about cheap IMU, it's still in the range of 1,000, 2,000. Was there any with really cheap IMU, like cell phone grade IMU or something like that? So I guess
The
everybody.
The IMU and the D435Is, we use some of those, and those are roughly cell phone grade. And we had to use a different algorithm, but it did work. And we also benchmarked a single axis laser gyro against our relatively nice MEMS IMU. And both of them were getting on the order of a degree an hour. And so that was better than what we were able to use. So.
Okay, cool. So Navina, you had this kind of breakout session. Is that, what was the idea there, or what did you want to do?
What I might do is I'll create a few breakout sessions and just randomly assign people to them just to have conversations in smaller groups. And then we'll convene and we'll try to absorb the delay that we had through the break, through the break, and try our best to kind of come back onto time, if that's okay.
Sure.
Let me know when we're good to go into breakouts. Are we good to go into breakouts now, Sebastian?
Yes, yeah. I wasn't 100% sure. I thought we had some good discussion. So I guess maybe we'll just do a short breakout till 11, and that way we're back on time. Is that the idea?
Yep, that's the plan. So I'll create 10 breakout sessions since we got more than 100 people. Hopefully that'll create smaller groups. So I'm gonna click that now, which means people will be automatically assigned, and then I'll disable the breakouts at the correct time, and we'll all be back on the main session. All right.
Great. See you in the breakout.
Same problem.
Okay, unmuted.
Yeah. Marco, do you want to start the session?
Sure. Hi, everyone. This is Marco from Switzerland. So now we'll start the mobility part. So I'll quickly start with the presentation about Cerberus, and then I will also apply the same method as Sebastian. So I'll ask all the speakers to be to just use 5 minutes and then start the discussion. So I'll quickly share my screen first. This should be it. And then start the presentation here. Let's see. Hope you can see my screen. Yeah, looks good. All right. So then the mobility part about Team Cerberus, the main features on our robots. So the first robot I would like to introduce you today is Animal C, the legged platform deployed by Team Cerberus during the final event of the DARPA SubT Challenge. Animal is a quadrupedal robot produced by Robotics and further customized by the Robotics Systems Lab to create its SubT version. So the robot is equipped with a variety of sensors, including LiDARs, depth, color, mono, zoom, and thermal cameras. During the final event, we deployed 4 animals in the course, namely Cerberus, Chimera, Camel, and Cayman, and they were operating simultaneously during the final event. So then a few main software components that we deployed on the robots are explained in the next slides. So the first component I would like to talk to you about is our GPU-based terrain mapping software that is able to process input point clouds in real time and provide a terrain representation used both for locomotion and planning purposes. In this video, you can see an example of the robot navigating in a narrow environment while the terrain representation is built on board. So the elevation map that you see here is actually composed by multiple layers, namely elevation, traversability, and upper bound, and each of them are used for different purposes, for example, locomotion or local planning. Another main software component is our deep reinforcement learning-based locomotion controller that, as you can see in this video, it was deployed in different scenarios. So I think the video is not playing. Let me try again. Maybe like this. Yeah. So this video shows the perceptive controller used in different scenarios where the animal robot was locomoting over a variety of rough terrains. This controller is trained in simulation and directly deployed on hardware, and it is also one of the main differences with respect to the other teams that deployed legged robots with a model-based locomotion controller approach. To achieve a high level of robustness, we also applied randomization during training. For instance, randomized height scans in the elevation map are applied to handle sensor degradation in extreme conditions and challenging environments. As you can see in this video, and probably as many of you have experienced during the SubT final, there were a few smoke traps in the final course, but despite of that, our robots kept on walking because of this robustness in the pipeline. So the policy was actually deployed on all the animals during the final event and proved to be extremely robust and never failed. The third component we used on our animals was a locomotion, was like a navigation-based planner for reachability. So this was used to generate traversable local paths, and the module is based on a reachability method, which explicitly allows our robots to step over obstacles, and thus it was tailored for the quadrupedal robots of Team Cerberus. So this video shows you an example of how the planner was operating. So it was receiving a post goal, and then it was planning traversable paths while coping with partial and missing map information, as well as significant map noise caused by the onboard odometry system while maintaining a fast update rate. The second robot I would like to show you today is RMF, a resilient microflyer drone developed at the Autonomous Robots Lab that with only 38 centimeters in length and width and a total weight of 1.4 kilos is actually the smallest and lightest drone of Team Cerberus. So this drone features a LiDAR and a camera sensor, and thanks to its agility, small size, and robustness against collisions, it can be deployed in particularly confined environments, as you see in the video here. The third platform is a Gaston Gagarin drone developed by Flightability and also further customized by the Autonomous Robots Lab. That is actually collision resistant as well, and it can be used to autonomously explore narrow and confined environments. So here it's a video from the urban circuit where the drone is autonomously descending a narrow staircase while also being resistant against collision. Another platform is the Charlie Alpha that is based on a DJI frame plus some custom control software. It's a bigger drone, but it can actually carry a variety of sensors and thus can penetrate obscurant and dusty environments, as shown in the video. Then we had a Voliro Colibri. This is like a multi-rotor drone with a higher sensor, with a higher payload for sensors, and it can also like tilt and pitch independently of its state of motion, and thus it's like particularly suited for vertical explorations. Last are rover platforms that was actually teleoperated and used to bring inside the underground environment a high directional antenna. Then this should conclude my part. And I think next team is CSIRO Data61. If I manage to stop sharing my screen.
Awesome. Sorry about that. Just having a setting up our cameras. Can everyone hear me and see my slides?
Yeah.
Great.
You can hear and see your slides.
Awesome. So my name's Ryan Steindl. I was the hardware lead at the end of the DARPA challenge in charge of all of our platforms that we developed and or purchased throughout our competition. And I was just going to run you through what we, sorry, not sure why. So basically, I wanted to run you guys through a timeline of our decisions and or platforms that we ran through the competition. You know, from the very beginning, we had very basic track platforms off the shelf. We had our partners Emerson with the drones, and we played around with many different robot types. And this was one of our paradigms from the very beginning. We already had SLAM, a SLAM solution that we were building upon, and we wanted to keep our navigation agnostic to the platform so that we could trial out, you know, many different platforms in many different scenarios. And of course, we were building our dynamic hexapod robot as we had we thought mobility would be a very big part of the competition. And we had a hexapod hypothesis that, you know, 6 legs may be better on really rough terrain than quadrupeds. But we didn't really get to prove that one out. So as we went along, we discovered that the smaller robots became fouled and or, you know, not able to traverse the terrains that we were starting to be able to traverse. We definitely investigated doing quadrupeds. We partnered with Ghost Robotics, and we were finding the robustness of platforms, ours and external platforms, were really the limiting factor. We couldn't test enough. We were spending a lot of effort on platforms, getting them up and running, especially other people's platforms. And then just before our tunnel event, we partnered with a company from Australia who makes police robots, literally bulletproof robots. And the Titans came into the picture, and we really got a feel for what a robust robot was and how our systems and our and navigation and our SLAM could be used by these platforms to their benefit. So that was kind of a turning point for us, where we developed upon this Titan platform, which is now called an ATR. So the ATR platforms became the backbone of our fleet, which would carry the the drones and the communications nodes. So that's what we competed with in tunnel, and we had great success with traversability with those robots and the robustness of them. And yeah, we deployed drones off those robots as well. And then after urban, we really discovered and made the call to stop our hexapod development in favor of autonomy, which was what we saw to be the key to winning the competition. And then, so we were missing the ability to traverse stairs. So we developed our DTR concept, which is a dynamic tracked robot, a really small and fast robot. And then we used this and deployed this in our own cave event. And after cave event, essentially, we were pretty happy with the concept of the ATRs, the drones, and the small track robots. And we focused on their motor control, and we really wanted to get the low-level control of those really tight so that we could do really slow and precise movements, which led us to be able to, so we redeveloped how those robots did motors and motor control to be a lot more robust and controllable. And then we finalized up our DTR design so that we could get, we could fly with it, and we could also traverse through narrow doorways and up and down stairs with that. And essentially, just as that was ramping up, we ended up running into, we kind of flipped, and Spot became available to us very close to the end. And because of the fantastic work done with SLAM and our navigation, we were able to, adapt our whole pipeline to that platform within 2 months, right? So that's essentially what we ended up competing with. We had the ATR Titans, the Emerson drones, and 2 Spots. And that was, we wanted to bring DTR. We thought we would have competed better if we had that smaller robot in our tunnels, in the final course. But due to travel restrictions, the fleet we sent was pretty much everything we could take. So yeah, just a quick video, we really did get a lot of confidence in our ATR platforms after we did our cave thing, our own cave exploration. And we really, we were, after cave, we were very confident that our ATR could pretty much go anywhere. The caveat being that they pretty much destroy everything. So that didn't really seem to matter. So yeah, again, as I mentioned, the hexapod mobility really didn't seem to be the bigger part of this challenge, and we moved over. I saw a couple of questions online relative to our spots, and did we have to put them in the stair behind climbing behavior to get them to go up and down stairs? In our scenario, we didn't. We took the risk of not putting them into stair behavior, and you might have noticed that our spots walk backwards down slopes. Basically, beyond a certain gradient, we decided to walk backwards because that was the safest way to go down slopes.
Thank you.
I
think
the
5 minutes are over.
Okay. Thank you very much.
Yeah, thanks a lot. Then I think now it's Team Marble's turn.
Hey, can you guys hear me?
Yes.
Great. Okay, so hi everyone. I'm Gene Rush, one of the project engineers on Team Marble. Today I'm going to present the mobility section. I just have a few slides. Most of these are backups. So yeah, there's a lot of people that were involved in the mobility on our team. I'm kind of just presenting on behalf of them. So during the panel, we might have some other team members be able to contribute to the conversation. But on a very high level, first question I wanted to answer is how do we converge on our final robot fleet? A few kind of key things that I want to mention is that we had very few robot classes compared to most teams. So we just had 2 Huskies and 2 Spots. And we also had a smaller fleet size overall. So mainly the reason that we wanted to have fewer classes was to reduce burden of development. And then we want to maintain a small fleet size just because we're a small kind of leaner team, and managing all those assets takes a lot of time and energy. And then lastly, we had a very UGV heavy fleet, and the main reason was to hedge the development risk of UAVs, which I'll discuss in a future slide. And so just kind of down here, I have these little check marks indicating kind of the design and operational goals for the different platforms we had. We have on the left our Husky, which was our comm dropper, could kind of cover moderate terrain and had moderate clearance. It was kind of our workhorse for the tunnel and the circuit event. And for the final event, we were able to acquire 2 spots, one a little bit after urban, and then the second one kind of in the summertime of this year. And so these robots kind of became our workhorses for the final event, just because of their ability to go over stairs, cover a lot rougher terrain, as you guys know, and go through even go through narrower spaces, which was very valuable, and obviously a much higher clearance. So overall, like as most teams probably recognize at this point, like having quadruped robots was really a game changer for kind of the final performance. Just a couple of details in terms of our robots. There was a large effort to kind of customize the kind of drive and power systems on the Huskies. And main reason for doing that was to kind of add an ability to kind of charge the robots and swap off battery and shore power easily. That kind of allowed us to have a higher operational tempo. And on the spots, we had this kind of custom compute case on top of our the back of the robot, which you know, had basically enough compute and enough battery power to get us through the hour-long missions, which was great. In terms of area vehicles, we ended up not deploying area vehicles at the final event, and kind of because I feel like some teams might be wondering why. What happened was we wanted to prioritize UGV development, especially after urban, just because they were kind of seen as kind of the best bang for the buck. And we were hoping to deploy a marsupial kind of operation where we had UAVs taking off on UGVs. But just because of prioritizing UGV development, that was kind of descoped at a certain point in the winter, springtime. And there are some challenges like that other teams had to figure out, of course, like how to localize the UAV relative to the UGVs, as well as kind of having a certain hardware trigger to start up the vehicle to conserve battery power. So we ended up not deploying UAVs at the final event, mainly because the gain loss solution kind of had a low marginal benefit. Just because of the environment didn't have many large cavernous areas, it ended up being kind of an advantageous part of our performance. So just to summarize, we felt like in hindsight, having a smaller fleet was really beneficial because they're obviously in a very constrained small environment. It reduced the number of traffic jams you could have between robots. It also, having a smaller fleet, allowed the human supervisor to intervene and kind of manage all the robots without being overloaded. And then finally, the spot robots were really instrumental in kind of the rocky, uneven terrain that the final event presented. Thank you all.
Thanks a lot. I think now we have Team Explorer.
Hi everyone, can you guys hear me?
Yeah, we can. Yeah.
Cool. Yeah, so welcome everyone. My name is Chao. I'm in charge of the ground robots planning at Team Explorer. Today I'm gonna talk a little bit about the system design and also the mobility and also the local planning stuff on our team. So this is an overview of the robots that we used for the competition, including 3 ground robots, 1 Legate robots, the Spot, and also 7 drones, including larger drones we call Canary, and also 4 smaller drones that can take off from the back of the ground robots. So I'm gonna talk a bit about the ground robots local planning, and then I think John, we're gonna talk about the ones on the drone side. So here's the system diagram of the planning or autonomy stack on the ground robots. It's like divided into 4 layers. The top layer will be the coordination or behavior executive and coordination planner that will coordinate with different robots and share information among the robots. And then there's those task planners like exploration planners, route planners, and other like recovery behavior planners. And then there's this level of local planning, terrain analysis, all those low-level autonomy, which is the focus of this session or this talk. So for the ground robots, local planner were used is using like a pre-generated motion primitive libraries. And then on real time, the robot will determine like the collision-free paths or collision-free motion primitives to follow. And then it will choose those with like higher scores to follow, which avoids obstacles as well as following the waypoints or the paths. And here also it shows a video of we utilize this kind of local planner and also the recovery behavior to kind of get the robot unstuck from this situation where one of our robots got like stuck by this shelf, that is moving shelf. So you can see here that the robot's computing those collision-free paths on the real time, and then it can get out by choosing those like paths leading to free space, and then eventually getting itself out of stuck. And then here shows our terrain analysis functionalities, which we are using this LiDAR-based or point cloud-based representation that the algorithm will classify the points into like traversable and non-traversable. Here, the green one shows those traversable points, and then the red one shows those non-traversable points. This is based on some like cost functions that we assign to each point, some traversal cost, depending on the mobility of the robots. And now I'm gonna hand over to John to talk about the drone parts. John, are you there? Or so
can you hear me?
Yes, yes.
Can you hear me?
Yes, I can hear you.
Okay, yeah, so for our drone, we want to navigate through tight spaces safely, but also go through wide open spaces as quick as possible. So we use a Euclidean distance transform to measure distance to obstacles. And when we are farther away from obstacles, the drone is allowed to go faster. And when it's going faster, it also increases its robot radius to stay farther away from obstacles. And there's a video on the next slide that you can play. Yeah, so our drone receives a destination from a global planner, and our local planner then plans an A-star path through the distance transform and has a penalty on getting too close to obstacles. So it only goes through narrow spaces when it has to, and it detects that. And then it will try to align its yaw and go through those kind of tight spaces. But in open space here, it knows it's an open space, so then it's allowed to go faster. So here is the cave area in the final competition. It's going over 2 meters per second. And then the next slide, some recovery behaviors. So if it gets stuck in like fog that it can't filter out, it'll just blindly backtrack along the path it's flown to get itself away from there. And also while it's flying, it's always looking underneath it to evaluate safe landing spots. So if it runs out of battery and can't make it home, it'll go to the nearest safe landing spot. And the next video is too long, so that's it.
Great, thank you very much. And I think it's CoSTAR turn.
はい。Do you hear me and see the screen?
Yeah, both. Yeah.
Okay, thank you. So I am Kevin Otu from the team CoSTAR. There are a couple of people in this call who are working on this mobility domain. And I was working on the ground vehicle traversability part of this project, but as well as I was working as a human supervisor. And from my experience as a human supervisor, it was very difficult to know the mobility challenges that the robots are currently facing once they were inside the course. So the mobility subsystem has to be really robust and autonomous so that we can use the robot as a tool. This diagram illustrates our process to tackle, these challenging mobility problems. There are a mixture of known and unknown mobility challenges in the subterranean domain. And to address those complex problems, our hardware team, software team, and field testing will closely work together to develop a solution that works in generic subterranean environment. From the hardware standpoint, we have worked on a variety of mobility platforms with different. Sorry, I got this. Yes, from the standpoint, hardware standpoint, we have worked on a variety of mobility platforms. We worked on the wheel robot, we worked on the leg robot, we worked on drone truck vehicles, and also we worked on the hybrid ground and aerial vehicles at the in the early phase of the project. So our approach was to have heterogeneous robot team ready, and depending on the mission and terrain configuration, we deploy the best team among them that suits the environment and mission specification. And that our field experience over 20 different sites proved this approach in the real world scenarios. And this video shows some of our mobility system, like hybrid rollercoopter that can fly if you find obstacles, and roll normally to reduce energy consumption. And most of the team has the spot quadruped. And one challenge of using many robots is the complexity of manufacturing and maintenance. Our hardware team did an amazing job designing a unified payload system among different platforms. We share the same electronics and control board, and depending on the mass volume power constraints, based on the platforms, we configure it in a different way. These these payloads are designed to keep the center of mass low, so that we can improve the mobility performance, and also ruggedized to be resilient from fall and collisions. Next, software is obviously a critical part to safely navigate the robot in an unstructured subterranean terrain. Because of the difference in the mobility system, we use a different software stack for ground vehicles and aerial vehicles. For ground vehicles, we use a LiDAR-based mapping and traversability analysis. From the 2.5D elevation map and occupancy map, we estimate the probability distribution of the mobility failure event from the different mobility hazards. Those distributions are fused and converted to a traversability cost using the C-bar metric, which can be adjusted with a single parameter based on the user's risk tolerance. We extensively tested this in the real world. This video shows our deployment of the Boston Dynamics spot in one of the rubber tube cave, and you can see the different traversability cost map generated. The generated risk-aware cost map is used by our MPC-based motion planner. We combine the sampling-based and optimization-based approach to generate kinodynamically feasible but complex maneuver to go through the complex subterranean environment. For the drone navigation software, unlike the ground vehicle, we use a 3D representation. We constructed a voxel occupancy grid map that captures the occupied and free and unknown state of the environment. We employ the motion primitive-based path planning that considers XY motion, height changes, and velocity changes. Motion primitives are evaluated against the voxel grid map and the latest LiDAR scans for collisions. This video shows the drone autonomous navigation in a limestone mine in Kentucky. The drone successfully explored the mine while flying over debris that are difficult for a vehicle to traverse. So yeah, I think this is all of our platform, and it's just 5 minutes. So yeah, thank you for listening.
Great, thank you very much. Now it's the turn of CTU CRAS Norlab.
Hello, can you hear me? Hello.
Yeah, we can hear you.
All right, nice.
I think not yet.
Can you see my screen?
Not yet.
Okay. Share screen. That's done.
Yeah, perfect.
Right. I prefer to keep it a bit less formal, a formal discussion where one can see the video for details.
Yep, now we can see it.
So I have the stopwatch going. The drone guys are also gonna say something about the mobility of the drone. So I'll be probably 2 minutes. So we had various types of platforms, tracked robots, Husky, and Spot. Unfortunately, as Thomas said, we got most of our platforms literally days or weeks before the competition. So there are many things that weren't integrated, but I'd like to talk, for example, about the Spot platforms. One thing that I noticed when testing in the caves in the Czech Republic is that there's a layer of autonomy that was a bit lacking in the sense of navigation, a locomotion, basically a Spot in very difficult environments. So in urban, it's fine, but if you're in very slippery environments in the cave, then you really have to do some special setting, the correct mode, the correct terrain mobility parameters that are called in Spot, gate height, etc. For example, going up very slippery hills, the slippery rocks, is only possible if you set the gate correctly. So that's one thing that I was trying to do. I'm curious if other people were like literally writing the mobility parameters through ROS or through other means. So that's maybe something that we can talk about. Then for our planning, we didn't do anything too special. It was just a planner following waypoints. I was doing waypoint look ahead because like if the plan is going through relatively free area, you can go really fast. If there are obstacles, you have to slow down. And for example, I was switching the Spot's gate depending on the difficulty of the terrain ahead. But again, that's something that we didn't manage to test. We also do some learnable terrain estimation for example, for soft terrain based on multimodal learning. I talked about this. Also, some other things about the mobility is that the operator, because of the very large delays, we had special modes where the operator just sends like deltas for the robot to perform, but didn't actually do real-time control because it wasn't feasible. And yeah, for stairs, for Spot, we basically rolled our own tracker and all that stuff. We did switch stairs mode, but we didn't distinguish between stairs and ramps, which was quite an issue because it's fine on stairs, but on ramps it gets wrecked if the angle is too high. And I'm past the 3-minute mark. I prefer to give it over to my my colleagues from the drones. Are they there? You guys there?
Thank you.
Okay, I'll stop sharing. I'm sorry, I didn't finish, but I prefer to give it over.
All right, can you see my screen and hear me?
Yes.
Hello?
Yes.
Oh, good,
Yeah.
okay.
Yes.
So just briefly about the hardware, we used just one UAV platform, the X500, which just the most important thing probably is that we had a flight time of around 20 minutes and the usual sensor loadout. We separated the navigation into high-level planning and low-level planning, as others did. For the high-level planning, we wanted to not only plan the shortest possible distances given some minimal obstacle distance, but to also minimize how often and how close the UAV gets to obstacles, because tuning the minimal distance is just difficult. And for this reason, we developed a structure sphere map, which is basically filling the free space of the octo map with spheres, connecting them, and then creating a graph over which we then planned long distance paths, which was then quite fast, and we had information about the safety of these paths. And then for short distance planning, we just used an A-star planner over the occupancy grid, which also pushed the paths away from obstacles whenever possible, so that the UAVs wouldn't fly unnecessarily close to obstacles. And then we gave these paths to a trajectory planner. And here you can see how in the end we were able to fly through very, very narrow passages in the post-event testing. And I don't know about time, but I guess my time is up.
You have 40 seconds if you want, otherwise
40 seconds. All right, okay, so I made it too fast, but Yeah.
Great.
Okay.
Thank you.
Yeah, I'll give the word to the others.
Sure.
Thank you.
Thank you very much. Then coordinator robotics.
Everyone hear me all right?
Yeah.
Just waiting to be able to share my screen.
Mashi, you had to stop sharing your screen.
Good.
Perfect.
So I'm Q Quintero. I'm going to be presenting on mobility on behalf of Coordinated Robotics. Our approach was pretty simple. Our plan was to use track robots to go upstairs, drones to search large vertical rooms, and our ground platforms to really search the majority of the ground space. For our ground platforms, we had the one on the left here, which is what we call a Joe. We had a total of 5 of these. They're small hoverboard wheel platforms, and they're a refinement of the platform that we had in Urban Circuit that we made the night before the competition. These were worked on, and the reason we chose to go a lot smaller was because in Urban Circuit, with the big Ackerman steer platforms, we had difficulty getting into the tight rooms. So we invested our time into smaller, more robust platforms. On the right, we have a larger skid steer vehicle. They're Alley and Ames. This platform uses snowblower wheels, and they're basically an identical copy, just one's a little longer, and they have different motor controllers. On the left here, we have 2 track platforms, which are Cornelius and Julius. These were what we were expecting to do most of our heavy lifting, going up the stairs, searching a lot of the urban environment, mainly because they're very robust and they can travel basically through anything that we tested at least on. And then on the right, we have our large Ackerman steer vehicle that we had in Urban Circuit. It didn't really change that much, mainly because it was locked in a lab up until about June of this year. So until then, we didn't really do any development on that. And then on the left here, we have Mike, which is our center pivot platform. A big issue we faced was that in the final round was that everything was a lot smaller than we were prepared for. We were expecting large rooms like the mega cavern is known for, and not these small passageways. So we didn't really use Mike as much as we would have liked, but its center pivot allows it to do some pretty smooth mapping, as well as the big wheel diameter also smooths into the mapping a lot compared to the tanks that just vibrate a lot. And then on the right here, we have the small Ackerman steer vehicles. They're a little RC car that didn't have localization on them. We were intending them more as communication nodes or to go into really small rooms to search little nooks and crannies. They use a Jetson mainly and 2 cameras, and that's basically all you got on them. As for drones, we had a total of 8 custom drones, 2 of which used Ouster lidars, which we never flew because we didn't want to risk the lidars, and we didn't see a benefit in flying a drone in such small areas. And our intended use was for them to be carried in with the larger Alley and Ames platforms. That way we didn't have to close the gate and walk out, losing time to set up other platforms. But they all use RGBD cameras. So that is all for my part.
Thank you very much. Then I think it's Robotica's turn.
Robotica developed, tested, and qualified 8 different custom-made ground platforms for the finals. In this section, we present our articulated robot Clawback K2 with 2 joints. The joint in the middle of the platform allows to bend the robot ± 80 degrees. The rear axle allows turns of up to 30 degrees up and down. The motivation for this design comes from agriculture applications, where it is required for all the wheels to be in the contact with the surface to avoid skidding. Note that both joints are passive at the moment, but are designed to be potentially extended with an extra actuator. In the finals we used the four-wheel drive all the time, but there was also an option to switch to front-wheel driving only, and to use rear wheels to gather precise passive odometry. This was used in Tunnels Pittsburgh, and with precise IMUS it provided quite reliable position estimation. Clawback K2 fits into the symmetric robot category, although the symmetry is not perfect as the up-down joint is only in the rear. In the final competition we used this symmetry, not only to guarantee a return from tight spaces, but also to swap the front and back of the robot in situations where the turn was more than 90 degrees. Now enjoy the video of clawback captured primarily in post-event.
Sorry. I hope I will be able to play the video of clawback. I will cut the video short. If you are interested, you can see it on YouTube.
Testing, where we could exercise.
Sorry, the machines took over. So I think that's all for Team Robotica, where the K2 was like, I think, slightly different robot to other platforms, as it was really articulated and like all the wheels were in contact with the ground all the time. Yeah. And if you have any questions later on, we can return to that. Thank you very much.
Thank you. Then I guess we can start the discussion. Maybe I can kick it off with one question, mostly like a general, and also should apply to most of the teams. So since the challenge was a big win for Lego robots, the question is like how this will affect our expectations over what ground robots are capable for future research, and are the Lego robots almost always better than wheeled? So maybe one comment from our side, Team Cerberus. So we betted on Lego robots since the very beginning of the competition. And I think it was a big bet, and we show also good progress over the last 3 years. But it would be also interesting to know what other teams that switched to Lego robots in a second or third phase during the SubT Challenge think about this, and how they see the future in this direction. I don't know who wants to address the question.
I think I can go. From Team CoSTAR. So yeah, we'll be using the wheel vehicle from the tunnel circuit, and we started using the Boston Dynamics spot robot from Urban, and yeah, both are good at certain environment, and there are some environment that we love Husky a lot. For example, in the huge limestone mine that we are testing in Kentucky, that mine is really muddy, slippery terrain, which was difficult for wrecked platform to safely navigate. On that terrain, the wheel robot is much better to stably traverse a longer distance. But in the environment such as the SubT final competition, where the environment is small and there are a lot of small steps and stairs, for that complex environment, the wrecked platform did a better job.
Yeah, I think from our side, so this is Sebastian from Explorer, Leggett didn't really play a big role. We put a big bet on flying and ground robots, and during the final competition, actually, I think our walking robot only ran for 5 minutes or something like this, so actually didn't really add a lot.
I can give a kind of maybe contrasting perspective. For Team Marble, our 2 spot robots, I believe, scored like the outstanding majority of our points. Compared to the Husky platforms, they were just able to like cover a lot more of the terrain, and they also had like a faster tempo, so they were able to just explore the environment faster. There was like one area, I think in the cave section, that had like this really kind of pointy, slippery rock, or fake rock. And during the preliminary runs, like our robot was at one of our spots actually like stumbled there, but then recovered. But I think during the final event, it actually fell over there. So I definitely think that there's probably progress that can continue to be made in terms of making sure that the legged platforms, don't fall over like that. And I think if we had more time for development, we would have implemented similar to what CoSTAR did, where it could like self-write itself. But we just ran out of time, so we weren't able to add that to our autonomy stack. Yeah, so I guess I would say in general, kind of slippery surfaces, and maybe just having greater stability for the legged platforms could make them even more effective. But overall, they seem to be pretty important to our success.
Yeah, I want to add to Gene's comment. I'm Shakib from Team Marble. Is that most of the performances where we saw legged robots outperforming the wheeled robots or UAVs, I think they also reflect the fact that we had good comms in the area in the final SubT course. So I mean, the wheeled robots definitely could carry more payload for us. So that was our main motivation to take them into the field. Like even if you have a beacon on that first junction, like it gains it if the area is covered with concrete walls, then you gain a lot of like communication strength over that. So I think there is a benefit to that, but it's always like complementing the benefit of the legged robots in terms of like speed of exploration. So you don't have to come back to report artifacts if you have longer communication range, things like that.
Jason here from CSIRO. I guess our experience, particularly in cave, like in the testing that we did there was some really extreme terrain where the tracked platforms were amazing in what they could do, right? I mean, they were able to go up slopes that, like even for us to walk was difficult. So we didn't have a leg platform there to do a direct A/B test, but I mean, I guess the intuition is that it probably wouldn't have been able to do some of that. I mean, there's certainly lots of advantages, but I mean, I don't think it's a kind of a clear domination.
Steve.
Sorry.
Steve from Marble here. Just regarding the performance of tracked vehicles, I think it was CSIRO had autonomous flipper control for doing stair navigation. That was a direction that we had started to look at because of the value of taking tracked vehicles downstairs that can go, at least for us, we were using the SuperDroid platforms as well, and they could take stairs at full tilt. And it was a pretty high shock and vibe environment, but the platform could handle it. But the part that was missing was the part that you added, at least for us, the autonomous flipper control, to be able to do that little bit of leverage. And that was something we just ran out of time to implement.
This is Chow from Team Explorer. So I think I want to add some comments aside from Basti's comments. So I think the main concern or main purpose for us to take in the spot robot is to like tackle some specific terrains like the staircase and some as the cave terrains. But then I think the main concerns or the main challenges for us to use spot, I think first I think it's the falling recovery. So we are afraid that like if the legged robot kind of falls on the ground, then the slam will go bad, and then it's difficult to recover actually. And that's also my questions. That's my question to some of the teams that they're using spot, because I saw from the video that the robots kind of fell on the ground and then was able to recover. And then I was like curious, are the slams are like doing good from that? And also the other thing is I think the battery life for the endurance, because as we are putting more computation and sensors on top of the robot, the battery life is like not like as long as our like wheel robots, and which essentially just becomes like a drone kind of, because the robot can only like walk for like 20 minutes maybe with all those payloads. So actually that's another question. If you're gonna do like some long-term mission or something, or how are you gonna tackle the battery life problem? Nope, that's it.
Maybe I can comment in the SRAM performance. Oh. Sorry, go ahead.
Sorry, we were just going to add that we put a pretty significant effort into reducing our payload mass on our spots for that exact reason. You know, battery life was a main concern, whether it'd be useful for the whole period of the competition. So yeah, we really tried to reduce the amount of mass we put on the back, and that was essentially the answer and the trade-off. So our spots didn't carry comms nodes, but they essentially had the rest, and obviously it didn't carry a drone. So yeah.
Yeah,
and
sorry. Good.
Okay, just a small comment about the how good are the legged robots. Although I like them, I'm still on the side of the tracked robot with articulated flippers. I think that the tracked robots can really do amazing terrain traversal, especially when the flippers are controlled in a good way. And we also to the spot and payload, we also realized the problem with the power. So at the end we opted to add the additional batteries to the payload. So the payload was kind of independent of the rest of the robot.
We ended up doing the same thing with our spots, where the belly battery was only used for propulsion, and then the payload component on the back had its own power source that was completely separate, where the only link between the two is just an Ethernet cable for control. There was one question I had regarding legged robots. How does the group feel about how much of a legged robot performance is due to the walking algorithms versus the physical mechanisms? And that's something where I'd be interested in Cerberus's sort of outlook of how they feel the animals did with respect to the spots.
So maybe a comment also addressing the previous answers is that we did a quite tight integration within the robots itself. So whatever like sensors and payload we integrate on top, we're actually also highly integrating this with the electronics and the onboard system of the robots. Then coming to the specific question, I think that the main differences that were developed internally within Team Cerberus made a huge difference in the last huge steps in the last 2 or 3 years, especially with the injection of these learning-based methods that really brought a big difference. But then what was your exact question about the difference? I think I missed the last part due to audio problems.
Sure. No, it's not just the mechanisms, right? But it's also the software, the walking algorithms. And that was something where essentially all of the teams that used spots, we were able to outsource the walking algorithms to Boston Dynamics, which is great, but also comes at a price of customizability and ceding control of a portion of our system. And as I think the only other team who used a legged robot that wasn't a spot, I'd be interested in Cerberus's sort of view on that design trade-off.
Yeah, so I would also actually link to the reply that one work colleague of mine gave before about the mapping, is that we actually could put our hands in the detailed implementation of in this case, the perceptive controller, let's say, and then we had a few people working on different iterations and versions, and then the latest one also incorporates terrain perception mapping. But then the point is that we could really go in the field, test, see what was not working, and then really address these problems. Of course, like we don't have the same capacity as Boston Dynamics, but then we could actually change or like develop what we needed. And I think also in terms of robustness, we're like deploying the robots in more than 30 field tests just in Switzerland to test and improve this. So I think this made a huge difference. Of course, outsourcing, it's better on the short-term run probably because we invest a lot of engineering time for this. But then otherwise we could like really steer in the direction we wanted. So addressing the specific SubT challenges for our legged robots.
I can also answer from the
yes,
locomotion side. So I developed the locomotion controller for animal. And as I was working on locomotion controller, like the algorithm was quite important. Like even if we are using the same robot, like depending on which controller we use, the ability of the robot is quite different. Like if we use some non-robust controller, the robot is very easily falling. While when we use a proper like algorithm and controller, the robot is very robust and could adapt to most of the terrain. And on the DARPA SubT Challenge course, like it was okay, like the robot could handle all terrains and could go over every like areas without any falling.
And maybe to also answer Eugene's question from the chat, I don't know how serious it was, but we believe that our robustness did not come from the lower center of gravity that animal has, but it comes from the locomotion algorithm. Yeah.
I would like to then inject another question, maybe moving a bit towards the UAV part. So then there is one question about, it seems no team ended up with a UAV only solution and use UGVs as main vehicles. So what was the reason? And I might add also like maybe this like fairing approach, like actually it's a better trade-off and better solution to actually deploy the drones farther inside the course. So if anybody has a comment on that, I think it would be also very interesting to know.
Yeah, so I think we deployed drones quite a bit, I think. And one of the things that was interesting, the flight time of the drones, of course, shorter because of the because of the heavy payload we have, because we carry the same SLAM system. But actually, the traversal distance for the drones versus ground robots was roughly the same, which is kind of interesting. Like around 600 meters for each of them. And so that was kind of surprising to us because typically when we're in more bigger environments, drones would have a shorter traversal distance than several factors than the ground robots. But it kind of really depends on the scale of the course, I think, where these come into play. And of course, the drones for us were a little wider. Even our smaller drones were wider than like the narrow ground robot or a spot. So there's some access limitations.
I just want to add that the testing made a big difference. The ground robots were a lot safer and easier to test, could be tested indoors, outdoors, didn't have to worry about flying restrictions. Whereas the drones took more safety precautions and were just generally harder to test with. And so that was one of the big things that pushed us more towards the ground robots. I tried the all UAV approach with very little success at the tunnel circuit. And so that's really one of the things that pushed us to the ground robots.
Yeah. I saw also like one question from Victor. It would be also interesting to address, like what would be the biggest limitation for increasing speeds to, let's say, 5 times what we saw in the finals. I think this also could apply to drones if they could fly faster. So then I think what are the main components that would start not working reliably if we increase the speed?
Yeah, we team says CSIRO. I'll give that one a crack to begin with. Our limitation for speed came up against computation. That was pretty much our limit. So planning and computation really was the thing that limited us in speed.
Yeah, I would second that.
For all the types of robots. Sorry to interrupt, but like for the Titans, the spots, and the
Yeah, correct. Because we had the common pipeline for navigation, yeah, that we had a certain horizon based upon computation.
Thank you.
Maybe from the Cerberus side, I also, I think computation is a big one. Just planning for much faster vehicles is much more difficult and needs more compute. And also then sensing becomes an issue. So if you rely, for example, on depth sensors to your local collision avoidance and they only see 2 or 3 meters, then as you go faster, obviously you also kind of, there's a much, you're more short-sighted in that regard. And then for legged machines, obviously they have a maximum locomotion speed. So we were maybe like half the way there for the towards the just mechanical limitation in terms of leg length and power for the robot. So that's also then for the legged machines. Obviously, they can only run so fast. So 5 times faster with the current machines probably wouldn't work in terms of legs.
Maybe if I may add a bit of let's say history. So we started at sticks with like a locomotion velocity of 0.13 meters per second. Then we went to tunnel to 0.3 meters per second, urban 0.45 meters per second, and then final with 0.7 meters per second. But actually the controllers could go faster than that. We had to find a trade-off with also the other modules mentioned, like perception, locomotion, and also at the end we wanted to score artifacts. So we also had to account for that when setting the speed. I think before
on that point, one of the things that we can.
Sorry, go ahead.
Briefly, one of the things we considered as a speed limitation was artifacts. So depending on the camera and the frame rate that you're running, and the lighting, and how much exposure you have to get a good image, that can often be a limiting factor for the speed. Because if you go too fast, you may not get good quality images and then not be able to detect anything. So sometimes, some stages during the competition, that was a factor that we reduced our speed because of.
Actually, I also believe that the fact that we needed to see the artifact is probably one of the reasons for opting for ground robots more, because bigger cameras give you better image, and more cameras allow you to see completely around, which is typically not possible for the drones because of the trade-off between payload and flight time.
I was just going to add that I kind of agree with what everyone else is saying, and that maybe the biggest limitation would be the trade-off between like having enough vision in terms of meters ahead that you're looking as you approach faster and faster speeds with the computation. One other thought I just had is like dynamic obstacles also become a lot more challenging, especially if there are like other robots in the environment. So that could, if you were to go 5 times faster, that would lead to a lot kind of more, maybe more high stakes kind of potential collisions.
Yeah, I can add to that, dynamic obstacle avoidance. In the finals, there was a big traffic jam in our team deployment because of the number of robots we deployed, and the robots driving, toward each other, collided because our perception system could not keep up with the 2 meter per sec relative speed. So yeah, that's one of the consideration from the limiting factor.
Then I think before there was also a question about whether the, let's say, traversability analysis was actually robot dependent, or if teams that were using this on different UGV types could actually reuse or directly deploy the pipeline from one robot to another type.
So from the CSIRO point of view, it was the same method. There was some slightly different, tuning parameters that were used in there. When we communicated it from one platform to another, like we were in effect communicating a height map and, a processed cost map that used some of those parameters. We do, kind of further processing on that for the global map that, took into account the footprint. So that just naturally, like if it was a larger platform, that would be taken into account. We kind of did the work to completely re-cost that, but it, didn't really turn out to be necessary, and it was just extra load on the hardware. So we didn't end up like actually using that.
Yeah, we are also using, the same software, JavaScript analysis stack for the ground vehicles, but with a different parameters. Obviously, wheel robot and electric vehicle has a, different mobility capabilities. So yeah, for wheel robot, we penalize a lot on the small steps, but electric robot, those are close to non-obstacles. So yeah, we made those parameter changes, but overall the basic software is the same.
This is Chao from Team Explorer, and I have quite of a embarrassing question to ask, because one of our robots kind of fell from the cliff at the very end of the competition site. So I was curious, how confident are you guys with your robots to say if the robots were there, then they will not fall over with like proper negative obstacle detection?
Obstacles. Go ahead. So, I mean, when I looked at that, the nastiest part about it that I could see is that it wasn't a hard cliff, and so it would, like, once you recognized the slope going down, it was, like in a sense probably too late. So trying to get back up, would be difficult. So like we were, fairly confident in like the, subway platform kind of environment where it's a sheer drop, right? So that's, fairly clear. I think that particular case that you guys found, the way that curved down, that's one of those things that it's really hard to, not be in the situation that you can't get out of by the time you recognize that.
So we didn't fall off a cliff, but still our robots fell in that location. So I'm sharing the screen showing the demise of one of our spots in a very similar location, not exactly falling off the ledge there, but quite close to that location.
Yeah, so from our side is I personally was reasonably confident that negative obstacles, especially sharp drops, would be handled well, but we didn't know until the final competition because we were always kind of too scared to really let it go and let it figure out, like, to actually see whether it would fall or not. Usually there was an operator there, a safety operator, when we tested, and they got too nervous when we got close and then pulled the robot back. So I could see in the data afterwards that probably would have been fine, but we really didn't see until the first practice run that the robot was fine and didn't fall off the subway platform. And then also maybe a side note towards CSIRO. You guys did this virtual surface stuff to kind of figure out the kind of possible slope that could hide behind a ledge or something. We also tried that, but actually abandoned that concept afterwards because it turned out that as you go closer, because the sensor is fairly low, you need to be quite close to actually see that the cliff is dangerous. So there it turned out for us to be a bit too dangerous and uncomfortable to try and kind of get close, and only as you get closer assume that's a negative obstacle. So in the end, really anywhere we didn't see, we assumed it's a hard drop and just could stay away from there.
Not exactly a negative obstacle, but related to something that Ryan mentioned about our track robots destroying everything. This is not from the finals. This is from, I think, preliminary run 2. So I'll just let the video play and you can figure out what happened. So with apologies to DARPA.
While this is playing, I've got a question for the group around how many times did you roll your robots or have them fall in practice? So was that something you guys babied or did you accept it? Because in our paradigm, we accepted that, essentially, like not dropping off a cliff, but rolling a robot was not an unheard of thing.
So maybe for Team Cerberus, whenever we were testing our animals in the field, we were always coming back to the lab with at least something broken or like a few faults for sure. Something to fix the day after, 100% guaranteed.
We broke a lot of Wi-Fi antennas off the top, so the things that stick out.
I kind of answer for Team Marbles. I was actually really curious about this too, so thanks for asking the question. We definitely let our robots kind of go up against kind of maybe the cusp of what we would consider dangerous or really treacherous terrain, and we kind of, I would say, in the early to midsummer, were more permissive of that kind of risk to kind of see what happens in those really sparse but really important edge cases. But I think by the final month or month and a half of the competition, we were being more conservative and not letting our robots do those kinds of things. Just because we didn't want to have to be down for a spot, for a week or two at a time. But having 2 spots definitely helped in that scenario where we did accidentally have things happen. So.
Maybe also another interesting general question was posed by Sebastian about the point distribution per robot type, if people can comment on that, given the mobility of the different platforms.
We're just having a quick discussion on that. We don't have a specific breakdown, but mostly spots is the answer that we got for point distribution.
Okay. For Cerberus' point of view, was only animal for the finals, but then this was we had an issue in deploying the drones, so they were actually exploring upwards because they saw free space. So we should have actually crossed the gate and then triggered the expression planner. So that's why we actually didn't manage to deploy the drones. But then actually in the circuits before, we also scored with our UGV, but mostly with the Lego robots for our case.
Yeah, I don't have the point distribution breakdown exactly right now, but I think it's safe to say that in terms of I think our spot scored probably 70 or more of our artifacts, and then there was maybe a 20% that both spots and huskies scored, and then maybe like only 1 or 2 artifacts that.
Yeah, so I don't know the exact numbers, but as I recall from the top of my head, for us the distribution was sort of pretty uniform. And yeah, we also scored by drone. I see some question in the chat. So yeah, our drone scored.
Since there was a question about the negative obstacles, this is not again from the final event. This is from our cave event. This is one of our track robots avoiding a negative obstacle. And on the left, you'd see the cost map and how we identifying the negative obstacles. On the right, I know the resolution is not that great, but that's actually a ledge. The robot goes very close to falling over, but avoids doing so.
I don't know if you answered this already or not, but I'm curious if because your platforms were so long but had a lot of mass that you were able to get to the edge, or even over the edge in some cases, whereas like you wouldn't necessarily do that with a spot.
So I don't fully understand the question, but yeah, they have the Titans, the ATR platforms are unbelievably stable for their size and mass. The distribution is fantastic.
We can hang their tracks over a ledge a little bit.
Yeah, they can. And they don't. Their tipping point is like a good set of stairs. They're fine to do whatever they want on a set of stairs. So that's why they, like we said in cave, we were very impressed with their traversability to the point where we really lent into them. Their biggest problem was they couldn't get up a spiral staircase because they wouldn't turn around on the platform to get to the next set of stairs. That's why we went for spots in that. But yeah. We did have a question here. Spot has its own local sensors. Did anyone do local sensors for things like huskies, specific sensors for ledges and or drops? For a robot, was that something people implemented?
I can answer for Team Marble. We had these 2 PicoFlex kind of flash LiDAR sensors that were pointing down on the huskies, and we were using that at a certain point for kind of terrain awareness and negative obstacle, or at least like kind of cliffs. But I think due to a number of factors involving like false artifacts and like just like more computational burden on the robot, we decided to just remove them completely. And we didn't have any issues, fortunately, but it was something that was somewhat of a liability.
For CoSTAR, we tried different things like a real sense facing down, even just like a little kind of 8x8 step sensor facing down just for negative obstacles. But in the end, the 3 LiDAR configuration was in a large part driven by the ability to see close to the rover. And so essentially we had multiple velodynes to give us that visibility of negative obstacles, both in front and behind.
Maybe a question for the teams deploying UGVs in general, like how many different types of tires did you evaluate or did you develop? Was there a big ongoing research in that direction, or did you just take a few samples and then use whatever was working best?
And quickly, for those who did wonder whether our track robots fell over ledges, they did during our cave event. So that's an image of one of our track robots having fallen off a ledge.
Oh, sorry, this is Chao from Team Explorer. I think for the tires question, myself, I don't do like hardware, I'm a software guy. but as the one sitting besides our storage room, I can tell that we're like trying a lot of the tires, like just tons of the tires, just to trying to get one of our robots, one of our wheel robots to be able to go upstairs, go up and downstairs. And then we finally was able to like converge to a kind of type of tires to be able to make it to go up and downstairs. But then the problem with that is I think it also travels slower on the flat ground than usual. So we ended up not using that for the final competition, I think. But for us, I think we are not actively pursuing this path for like research of like trying different tires. But I think it would be like a very interesting question to consider for on the engineering side of how to get like a wheel robot go up and down stairs. Yep.
So for coordinated robotics, we at the urban circuit, our small Joe platform had really slick hoverboard wheel tires, and we switched those out for a beefier tread on our tire, and it gave it a lot more maneuverability. Mike, the big center pivot platform, can go upstairs because it can center pivot. But the problem with his tires are that two of them, the opposite tires, will get stuck down to the ground, where the other ones will spin freely. So we didn't have time to address the tire issue there. To answer the question of free falls, we did not have anything in place for free falls or subway ledges or anything like that. So that's partially why we brought more platforms than we needed in case some fell, and we were hoping none fell, but expecting some to fall down and get broken. But our intended solution would have been a real sense camera, but we didn't have the time to implement anything like that.
But then maybe I would also adopt the same question, ask for the teams that deployed spots, whether they had to also work on the type of feet or rubber they actually attached there, because we actually did try a few different solutions until we converged to what we deployed for the final event.
Yeah, for Team CoSTAR, during our field testing in the limestone cave, we saw many spot slips. So we tried out, we made the custom shoes for spot using the mountain bike tire, and that seems to work pretty well. That give increase the grip to the ground on the loose terrain, and yeah, maintain the stability.
Did you actually deploy this for the final?
Yes, for the final we were using that configuration.
Cool. So mountain bike tires. Cool.
Can I add a question around how did every team deal with water? Were your platforms robust to getting wet? From CSIRO's point of view, we weren't. In a short, a spurious drip of water could have shut down our robots if we got unlucky, and we didn't get unlucky, so we were grateful for that.
I would say that for Team Marble, we loosely tried to make our platforms like drip proof, but definitely not like it was definitely kind of like a kind of off the cuff kind of a get this thing covered so that we're not going to short any electronics. So we were also, I think, fortunate in that sense.
So then I would actually quickly share my screen to show you maybe. I think it's a very cool video. So actually the platform we got, I think you can see my screen.
There you go. Yeah, very jealous.
So it's actually, the animal is IP67, so it's water and dust proof, and it can go underwater up to 1 meter. So we only had to be careful when doing like our system integration to fulfill the IP requirements, but basically the platform itself was already watertight and waterproof. So this was also a big advantage. how to stop sharing screen. Thank you.
It's cool. Can you elaborate on if this already contains all the sensor stack and everything? Also, like able to go underwater, or was it just the platform?
So the basic version contains the LiDAR and depth cameras and the inspection head, and then we actually developed integrated on top a few more other sensors, because we actually noticed that the real sensors were not suitable for some types of terrain, especially if they were like water puddles or a different reflectivity on the ground. So if maybe the ground was like a surface shiny metal with some actually black objects on top, actually those things are not seen by the real senses. So we decided to have two robots with like dome LiDAR in the front, in the back, to then use these point clouds to create the terrain representation. And so we had two robots in this configuration and two robots in the standard configuration with real senses. But then we actually saw the sensing capabilities of these like modified robots were superior compared to the basic version. So that's where we did a lot of integration work and research to make this more suitable for underground environments.
And would that be also like waterproof, or it was just a payload that wouldn't be able to swim?
No, we were always looking for sensors that would actually respect the IP rating of the robot itself.
That's impressive.
And also the connectors.
Mm-hmm. For CTU, I remember the guys in Prague were thinking about putting water sensors to the bottom parts of the tracks, not for the water robots, but for the track robots. I guess that wasn't finished, but there was an idea to stop the robots. And for NORLAB, at least for the Marmot, we did some effort to hide the most sensitive electronics inside IP rated boxes. But there was then this issue having the computer, NVIDIA Xavier, everything in one box. So we found the necessity of having airflow going through. Otherwise, you bake the thing in like 5-10 minutes. What was on your side, Marco? Did you use some radiation outside to get the heat out? Marco? No.
Yeah, sorry, there was like a problem.
So for the cooling, what we
No, you need to come here. Sorry, one moment. There's a colleague of mine, Samuel.
Yeah, so I guess your question was regarding cooling, right? So like how you get the heat out.
Yep.
So
yes, exactly.
Inside this version, there is heat pipes that are directly connected to the CPUs of the PCs, and those go to a heat exchanger that is like in the front of the robot, and there is a fan on top that basically removes the heat. Okay. Yeah, and then other parts were just directly connected to the housing of the robot, that you can basically use the housing is out of aluminium, so you can basically use it as a giant heat sink. So for other sensors, we use that approach to cool them.
Yeah. Okay. Thank you. Because that the new tracked robots we built last year that was actually not deployed is kind of designed to be waterproof completely, but we definitely struggled with the heat dissipation. At the end, we simply had to make a small hole to let the heat go out. So it unfortunately it's not that waterproof at the end.
One solution that also helps a lot is if you basically attach whatever produces heat to the outside of your housing. So let's say you have like a box size housing, then you just attach all the CPUs to the outside of the housing, and you directly use the case as heatsink basically.
Yeah, I think the construction somehow keeps this idea in mind, but still, too many heat sources inside.
Yeah, I think the session went a bit over time, so if you don't mind, I would like to then wrap it up. I don't know how do we proceed, Navinda, from this point.
Yeah, thanks, Marco. I think there was some really great discussion. So I'll do the same thing that I did for the previous break. I'll assign people into breakout rooms. I think the way it works is people will probably go into the same breakout rooms that we were in before. Or let me try to recreate. It's probably better to, yeah, I'll recreate the breakout rooms. And people will be assigned to them. And I think we'll reconvene in about 25 minutes time. So I'll close the breakout rooms, meaning that everybody comes back to the main session. So thanks everyone. So I'll send people to the breakout rooms now.
While folks are waiting to get back from breakout rooms, one thing I saw that other folks have done in the participants is add the team that they're part of to their username. And that is really helpful in the breakout so that we can tell whose viewpoints we are being represented.
Yeah, that's a good idea. We should post this on the messaging so people do it.
Where there's a greater probability that people will do it.
Or maybe Navida or whoever is sharing, maybe you can just put one slide and just say, please add your team name in your Zoom name. Or I can do it.
Should we go ahead and start the autonomy panel, or are we waiting? Navinda?
Okay,
there we go.
Now, you do.
Yeah.
Hey, Shakib, sorry about that. The floor is yours, so you can start the session.
Okay, thanks, Navinda. I'm Shakib from Team Marble. I'm a PhD student at University of Colorado Boulder, working with Professor Sean Humbert. I've been leading the autonomy efforts from the Team Marble and CU Boulder. Yeah, I'm excited to hear all of you guys' autonomy solutions and then have a panel discussion at the end. So yeah, I'll remind every presenter when it's 5 minutes. Yeah, be ready for that reminder so that we are on time. So without further ado, let's start with CTU CRAS lab. Who is going to present from? Okay. Thanks.
Okay, hello everyone. Do you hear me? Okay, so it should be fine. Hello everyone. My name is Jan Bayer. I'm from team CTU CRAS lab, and I will briefly present you our approach to autonomy on the ground vehicles. So our operator has 4 ground vehicles and also for UAVs 3 main options to teleoperate the robot or to navigate them to a certain goal, or he can also let the robots to explore fully autonomously. So I will mainly talk about the autonomy, and it requires, at least for the ground vehicles, traversability estimation, which we do on a fine resolution, and to use 3D maps with a fine resolution. And this resolution of the maps basically force us to use really dense representations, and these dense representations not allow us to cover the whole environment, and they also don't allow us to to be shared between the robots. So basically we use these local maps for local mapping, and we combine them with topological maps, which we designed specifically for the ground vehicles so that these topological maps can be shared via our low bandwidth communication system. And we measured that our topological maps can be shared via communication system that allows only broadcasting 100 bytes per second from each robot, which is enough for our low bandwidth communication. And we tested these communication and topological maps in different environments, including underground base or office buildings, and also outdoor areas right before the SubT finals. And since we were able to share these topological maps between the robots, we basically can deploy our coordination strategy, which is decentralized and ranks the waypoints that a certain robot can try to follow. And these coordination strategies that we deployed for the ground vehicles are based on 2 main ideas. The first idea is that we are trying to spread the robots uniformly at the crossroads, and the secondary idea that we use if the first idea doesn't distinguish which waypoint is the best. The second idea is that we are trying to spread the robots as far from each other as possible. And we tested this coordination approach during the post-event testing, and we tested it on 3 spot robots, which we deployed from the staging area. And basically in 20 minutes, they managed to explore the sectors that are marked in the picture on the right side. So thanks for the attention, and I will let speak my colleagues, and they will tell you something about our approach to flying vehicles.
Right, thank you. I'll take it from here. Can you see it? Can you see the presentation?
Yes.
Yes. All right, thank you. Okay, so our approach for the UAVs was to make them as independent on other robots and the operator as possible, which we implemented by basically having just 2 states for the UAV, which was to autonomously explore or to return, which could be interrupted by the operator at any time, we, for example, used to stop the UAV at outside some narrow passage to get other robots through, but then it switched back to autonomous exploration. We also put a lot of focus on making the startup sequence as quick as possible, which in the end, it was just connecting the batteries, switching a few buttons, and then the UAV would go and switch into the autonomous exploration state, which I think solved, well, prevented a lot of problems for us. And then for the exploration itself, we just used frontier exploration, which we modified heavily to, we computed the cost functions for frontier viewpoints based on not just their distance, but the safety of going to these viewpoints computed from the sphere map mentioned in the mobility. And then also we decreased the value of already visited areas because we sometimes encountered the problem that some viewpoints did not uncover frontiers. For example, when there was the dark non-reflective ceiling. And for multiple robots, we took a decentralized approach in which the UAVs would share these lightweight topological maps with each other, and then they would autonomously make decisions about which frontier to explore. Homing strategy. And here I'll show you an example of how our approach was also usable for outdoor environments where the UAV was able to fly out of a garage and explore around the house in which we stayed in Kentucky, and then over a bridge and into a field. So yeah, it was usable for this as well. So that is all from me. I will now pass my word to the others. Thank you for your attention.
Thank you. I'm stepping in for Shakib because apparently there was just a power outage in Boulder. Shakib, are you still online? Okay then. So if we could pass it next to, in no particular order, I'm just going down the list of the team events to Explorer.
Cool, so Team Explorer, hold on. Okay, you can see your screen. Oops, wrong button. Okay, good morning, everyone. My name is Graham. We also have Chow with us here. So we're from Team Explorer. So first, I thought I'd just reflect on some of our design considerations. These might seem fairly obvious, but I think they're worth kind of explicitly stating. So firstly, really pushing and trying to get redundancy to always keep the robots moving. So no matter what happens, if you're stuck in fog or something like that, we're really trying to push the robot should never be stationary for much time. Second one here is that we're really pushing having minimal operating input, so aiming for a fully autonomous system. I think in the final competition, we kind of regretted that decision a little bit. We wish we had a bit more input from the operator, but that's what we went for to begin with. We wanted an adaptive strategy that changes based on what communication is available. We wanted to exploit different hardware differences between particularly the flying robots and the ground robots. So there's actually different strategies evolved for those two systems. And the last point here, I think we really learned from from the urban circuit is we wanted to explicitly plan to observe objects rather than just mapping only. We needed to make sure that our cameras observed what we want them to see. So a little bit about our coordination. So we had in the final competition, I think about 8 to 10 robots on the competition course at once. Each robot was independently making their own decisions, but there's lots of different communication that shared information between them. So some examples on the right there, as we just saw in the previous talk, we had these road maps that allowed different robots to reach areas that other robots had been to. This one down here is exploration maps. It's basically told us which areas had already been seen by other robots. So if another robot revisited that area, then it would know to say move on, or is it worth spending more time there? And odometry was shared for local collision avoidance. So our autonomy really depended on this concept called behavior trees. This is kind of like a high level picture. And this example here is what was running on our aerial robots. Ground robots had a different thing, but a different behavior tree. And if you haven't seen a behavior tree before, basically what's happening here is you have conditions, which are these circles, and actions, which are different behaviors, which are the squares. And all the internal nodes describe some kind of logic that tell you which thing should be running at one point. And you kind of read it from left to right. So we had all these diagnostic tools on the left here. So things like if sensors timed out, then there'll be particular actions. There's a takeoff sequence. There's a few more things here that I took out of this diagram. In the main exploration mode, we actually had a few different kind of backup explore modes, depending on what was going on in the environment. Then finally, landing sequence over on the right here. And so at this, based on the colors, you can see it, the logic that has determined that we'd be doing this particular behavior, the roadmap explorer at this point in time. So for our aerial robots, obviously most of the time it was performing exploration. But we basically took a frontier-based exploration approach, but with a lot of extra kind of layers on top of that. So what's happening in this picture, we have a robot in the middle here. It has explored this room on the left, which means it's shaded green, which thinks it's been observed by the cameras. And then it plans a path through to some frontiers over in the next room on the right through this big hole in the wall that you see here. There's kind of two layers to the autonomy. We have this local planner, and then this global planner, which plans from basically this planning point out to a frontier. And we have these two distinctions here. So each one has different information and basically has different guarantees of safety, which is why we kind of broke it up like this. I'm now going to pass it over to Chow. He's going to talk a bit more about the ground robots.
So hi everyone, I'm Chow, first year PhD at Carnegie Mellon University. I've talked a little bit about the local planning stuff in the previous section. So this one, I'm gonna talk about a little bit about the task planner, including the exploration planner and the route planning planner used on the ground robots. Next slide, please. So this is the exploration planner that we used on the ground robots. It's called TARE. And then the special thing about it is it's trying to like maintain like a hierarchical data representation of the environment. So then it can optimize the full exploration path instead of being greedy, trying to go to like, say, the biggest frontiers or something. It's like computing like a TSP tour amount or in the environments to try to make the robot to go the shortest path to be able to explore the whole area. And then this planner is open sourced, and then we have also open sourced the benchmarking environment. So everyone is welcome to try out and then compare it to our methods. Next slide, please. And then this one is the major route planning algorithm that we're using. So this, as you can see the map, this is the map built from all the 3 robots. And then we're like using TARE planner, exploration planner, and FAR planner interleavingly, so then the robot can coordinate with each other. Say, for example, the robot uses TARE planner to go to the B point, and then the operator sends a command to the C point. So then the robot can use the route planner to plan a global path, or like presumably the shortest global path to traverse from B to C. And then accordingly, the robot also like use the FAR planner to go to A points, and then uses the TARE planner to explore the environment for the rest of the time. And then that's how they cooperated to kind of majorly contributed to our winning of the most sectors explored award. Yep, next slide.
Cool, if we have a little bit more time, I'll just comment on some challenges. So these are kind of some lessons learned, and maybe we can bring these up back in the question time. So firstly, as I said at the start, I think one thing that we struggled with was in the competition was having ways for the operator to express intentions to the autonomy. There's kind of a bit of backfighting between the autonomy wanting to do one thing, the operator wanting to do something else. And so I think we could have spent a bit more time trying to figure out better strategies for that. Second point here, coordination sometimes hurt. Overall, it was definitely a positive thing, but there were some cases, for example, if the maps drifted or something, that actually made things a bit worse. And so being able to identify that and switch it on and off would have been good. This next point's more about communication. I guess we'll talk about that in the next session, but I think one thing that would be interesting is to actually explicitly plan behaviors to communicate and pass information between robots. And a couple other things here, but I think we might leave it there and pass it over to the next team. Cool, that's it from us.
Thank you. Thank you. And
Okay.
Shakib is back online, so turn it back over to him.
Thanks, Steve. Yeah, sorry, my power went out and then went in. Okay, I can go next from Team Marble. Do you guys hear me and see my presentation? Okay, cool. So yeah, Steve, could you please keep track of my time and remind me if I'm over?
Sure.
Thanks. So yeah, our autonomy, basically the guiding principles for our autonomy varied over time. Like we were a team who aimed for 100% autonomy throughout the competition. But when we went to the final challenge, we used the robots as tools because our autonomy was robust enough to do things, but our human was better to reason over pieces semantically and then to guide the robots in some instances. So which was better for us than relying 100% on autonomy. And moving forward, our research more is about how to get the semantic information from the maps and how to make decision making on that. So to give an intuition to the robots about what's going on. Our planner is basically a graph-based planner. So I'll highlight our main contributions to this planner. So firstly, the legged robots don't need a very high resolution point cloud information for terrain traversability. So we used a 15 centimeter octomap, and then we use a sample and project sort of approach to assess the terrain and perform the elevation checks. So that way we don't have to explicitly get an elevation map, but we only have to check for elevations changes below samples and the lines connecting the samples. Our solution search does not rely on a single optimization objective. What we basically do is divide regions into the low volumetric gain and low neighbor separation. So a little bit about low neighbor separation. We also have another thing in equation, which is the pose graphs of the other robots, labeled as neighbor pose graphs here. So we want to move as far away from all the other robots' pose graphs while also maintaining a high enough volumetric gain. So we basically divide the solution space into these regions, and ideally a solution would avoid a low volumetric gain area and a low neighbor separation area. And if that's not possible, then a high enough volumetric gain area is good enough. So we go for a good enough solution instead of optimizing for best solution. In a lot of cases, going straight into a smaller room is more beneficial than maximizing the volumetric gain and going to larger areas. So post-graph coordination I talked to you about, we did not use the map merged coordination in our last event. We relied on the other robots' pose histories or pose graphs to push robots away from them. So to provide basically resiliency to map misalignments as well. We also incorporated dynamic obstacle avoidance. So we would label the graph edges as occupied and unoccupied, and we would only traverse the unoccupied graph edges. Above all is our high-level mission management, which basically has monitors, objectives, and behaviors. So through monitors, we deduce the binary form of what objective we need to accomplish. And then we choose the behavior, go home, explore. For instance, if we report we are reporting an artifact, or how to deploy a beacon. This is all signaled by the higher level mission management. This video basically shows how the graph and the tree is being built for one of our robot. This is from a spot run. So green edges are the graph edges and blue ones are the local tree edges. So the dark black line is the path that is being planned at every instance. So this is where the graph does not propagate over negative obstacles. So to check for negative obstacles, we basically extrapolate the path and project it down on the ground. If we don't receive any projections, we stop right away. So if it's a cliff later on, or like right after the end of the path, then we stop before even reaching the end of the path. Here you can see that the robot is planning into that warehouse area in the urban. And that's where our robot lost localization because of a lot of similar features in the environment. And the robot started drifting. And you'll see a lot of graph edges would turn red, which means that the robot is seeing them as dynamic obstacles and it will not traverse over them. But the robustness is shown here, like the planner kept planning shorter paths to maintain the heading and get out of that situation. And it didn't get stuck. So we were happy with the performance overall from that perspective. Here, the human supervisor found it beneficial to basically maneuver the robot into the tunnel area rather than the urban area. And the robot was trying to go back to the urban area to see an unexplored frontier, a frontier which has a good neighbor separation. So this is where our human supervisor is actually teleoperating the robot just to pump it through the initial section of the tunnel so that it keeps exploring the tunnel area, which we thought was better at that point. And here, basically, the human supervisor gave the control back to the robot. And then the planner kept going from there. So yeah, overall, we could explore this area. You can see like the DO1 and DO2 are legged robots, which did most of the exploration for us. DO2 went into the cave section, which was the first robot that we launched. And it preferred to go straight, mostly straight. So in the cave area. And DO2 basically, DO1 basically was the second robot. And it went into that tunnel area. And urban area was okay, thanks. Yeah, so that's it. Thanks for listening. So let me stop sharing. And then the next presenter would be Mihir from Cerberus.
Thank you, Shakib. I'll share my screen.
Yeah.
I hope you can see my screen. So hello everyone, I am Mihir Dharmadikari and I will be presenting the main autonomy features of Team Cerberus. Our approach is mainly driven by all the challenges that the subterranean environments present, which include very large-scale environments, difficult terrain, narrow passages, and multi-branching and multi-level topologies. In our approach, the human supervisor plays the role of a higher level coordination, assigning areas for the robots to explore, whereas each of these robots perform the given exploration tasks on their own fully autonomously. We have the philosophy of having a unified exploration planner for a higher level exploration across all types of robots, including both legged and aerial. But at the same time, having robot-specific navigation capabilities for following these high-level paths. At the core of our autonomy, we have the graph-based exploration planner, which we call GB Planner. This has a bifurcated local and global planning architecture, in which the local planner is used for rapid exploration within a local space around the robot. So in that step, the planner first builds a graph in this volume around the robot. For aerial robot, the edges and vertices of these graphs only need to be in free space of the volumetric map. However, for ground robots, we also check if there is a supporting ground below in the map by projecting each of these samples downwards. And this ground also needs to have its inclination within feasible limits for the robot to track. To handle negative obstacles, we introduce the concept of hanging vertices. These are vertices in free space, but they don't have any supporting ground below them. We keep these vertices in the graph for information gain evaluation. However, the edges going to them are not commanded to the robot. Once we have the graph, we calculate a volumetric gain for each vertices in these graphs, which relates to how much unknown volume the robot will see from each of these vertices. And then we accumulate these gains over all possible shortest paths in this graph, starting from the robot location. And the path with the highest gain is then commanded to the robot. Since this gain calculation is most expensive, we have the function to calculate the gain only at the leaf vertices of these shortest paths, as well as cluster them to reduce the computation cost. In the global planning layer, we build a sparse graph, which is built from the high exploration gain paths from the local planning steps. And this is used to redirect the robot to unexplored areas if the local planner cannot find any feasible informative path. At the same time, this global planner also gives paths to return the robot to the home location when the robot reaches its endurance limit or the mission time ends. Here, I would like to summarize the autonomy stack of each category of robots. In case of aerial robots, we have a relatively simple architecture, with GB Planner being the main autonomy module. However, for animal, we use a behavior tree that coordinates different functionalities of the robot, which include autonomous exploration, inspection using the pan tilt head, as well as handling the commands that the operator gives. If the robot loses communication with the ground station, it is allowed to explore independently for a given time, but after that, it queries GB Planner to return to a known communication point. In case if any of these high-level modules fail and the robot is idle for some time, then there is a recovery behavior where the robot backtracks its path to the previously known communication point. Finally, any of these paths have to go through a navigation planner, which was described in the mobility section, which slightly optimizes them locally for better safety. Here, I would like to show an instance in the final prize run where animal is going through a narrow section in the tunnel and then finally enters the cave section over here. If we fast forward a little, this is the small cave section that was near that huge room. Towards the end, we can also see the planner planning over that very steep slope in the cave. And here finally, I would like to show the paths that were taken by all the robots, all the 4 animals in the final prize run. With this, I would like to end my presentation. Thank you.
Thank you, Mihir. 5 seconds. Oh, actually, time's up. Okay. The next presenter is Martin Elohi from Robotica.
Hello. It's going to be trouble again. Video.
We can't actually hear that presentation audio.
Sorry again.
Tested in the Cloud Sim virtual test.
I will restart. Very sorry for this.
All Robotica robots have been fully autonomous from the very beginning at Styx in Colorado. It is also the Robotica International motto self-drive anything. We aim to develop deep exploration techniques, not just for Earthbound solutions, but perhaps also for other celestial bodies. There the communication between robots and the operator is very limited if not impossible. Moreover, lack of communication could have benefits in certain scenarios, such as military. The robots operate mostly offline, and are instructed to follow initial exploration plan. This was extensively tested in the CloudSim virtual testbed, where the main parameters are the preference of the side, left and right, duration of exploration, traversability parameters, minimal width of gaps the robot can enter, maximal allowed pitch and roll angles, recommended distance from the wall, and speed. Most of our robots can move up to 2.5 meters per second, but due to complex unknown environments and relatively small and tight final world we traveled much slower. The selection of which robots to bring with us to Kentucky was based on the fact it was taking place in the mega cavern. We expected to have to travel really far. Well, wrong assumption. Regarding terrain handling, we used our own traversability module running as a RAS node. It uses data from both depth cameras and 2D lidars and evaluates feasible direction of travel. We also developed an experimental obstacle position estimation from mono cameras, but later we dropped this functionality as the Intel Reolsen's cameras provided much more reliable data. This code is one running in Robotica solution used for the finals and virtual track. It is maybe worth mentioning that all the source code is open source, and it is part of our Oscar, open source generic autonomous robot, available on GitHub. Regarding the performance of robots in finals, Clawback ended in the urban storage room you see in the slides, and was not able to leave it. Our solution was not taking into account the possibility to move obstacles, here the traffic cones, but later I learned that they were glued to the ground. Is it true? Moreover, if we could manage to return the same narrow door, it would not be able to return home anyway since a blocking dynamic obstacle was introduced meanwhile. I forgot to mention that operator had 4 controls barely visible in the upper screenshot. He or she could pause and resume the mission any time. This was mainly for coordination of start of multiple robots, return home and finally abort the mission or the program, similarly to DARPA stop. The operator could send these commands to all robots, or to the one selected.
Okay, so this is it for the main. And I would be really curious if any of the team was capable to recognize obstacles which could be moved and really move them in autonomy mode. Thank you.
We have 2 minutes.
That's fine. Go ahead with other teams.
Okay, we'll stack this question up for later then. So the next presenter is from the team coordinated robotics, Andrew Herdering.
Okay, I am Andrew Herdering from Team Coordinated Robotics. I am a senior mechatronics engineering student at California State University, Channel Islands. For our autonomy methods, we plan to do manual operation or wall following into the different sectors. And then after that, switch to a deep reinforcement learning exploration system that had been trained with a sparse LiDAR input and pose history, and then outputs direct twist drive commands. This exploration would stop when it finds an artifact, and then it waits for the operator to give it input, whether to continue exploration or to come back to the home base. The exploration relied on a valid SLAM solution, and our SLAM disintegrated very quickly at the start after the ramp, and without the SLAM solution, we could not run our autonomy. So for the competition runs, we relied on teleoperation due to the SLAM. For our main autonomy solution, we used reinforcement learning, which was trained on an open source simulator called the RobLearn simulator. This trained the reinforcement learning network in a sparse 2D world. This simulator was originally intended to train for meant for waypoint navigation, and we were able to change its optimization function to optimize for the ability to maximize camera view area, which was generated by a method of using a partial laser scan from either a depth camera or LiDAR, and then optimizing and maximizing that value as is shown in the optimization function of the reinforcement learning. So to train this simulator, we then used 3 of the worlds from one from DARPA's simulator and the 2 from Urban Course, this being alpha in its representation. And then we evaluated our test runs in both simulation rounds and within the 2D world and in real test areas. So here you can see the progression over time of training episodes. And this is what the world looked like after, with the training commencing, with the magenta being camera view and green being the current LiDAR and blue being all obstacles. So then we were able to test on one of our small ground vehicles, with this being a view of the occupancy grid with where the robot traversed. And with that solution, we seemed to, with just reinforcement learning, it seemed to be able to outperform traditional forms of frontier exploration, and considering purely area searched with the camera. So we did not optimize for mapping at all, with being able to just search with the camera, since that would seem to be what mattered. And then in the case of finding an obstacle, yeah, we would switch to teleoperation or going home. Thank you.
Thanks, Andrew. Let's move to the next presenter, Marcel from Team CoSTAR.
Okay, I guess you can hear me. So I'm Sung Kim from Team CoSTAR, and Marcel and I will present about our autonomy solution for Team CoSTAR. So given our autonomy architecture, we have a series of hierarchical layers, which is human autonomy interface, mission autonomy, global planning, traversability, and local planning. For this session, we'll be focusing on global planning and human autonomy interface. So for global planning, we formalized our problem as a maximization of the coverage and minimization of the traversal risk at the same time. So our main ideas are in threefold: longer horizon planning under uncertainty, compact environmental representation, and hierarchical framework to scale up to large problems. More specifically, we employed a PALM-DP solver for simultaneous optimization over info gain and action codes, which provides us a great flexibility to change the behaviors, unlike frontier-based approaches or some TSP formulation. And for representation, we devised a scalable semantic encoding infrastructure, which is called information roadmap or IRMs. And we pursued local optimality and the global completeness at the same time by leveraging the hierarchical structure. To give a little more illustration of our solution, so this is the representation framework. So given a photograph, the trajectory and the risk map or the occupancy map, we maintain a semantic rolling window style local IRM, and we maintain global IRM in a generic graph structure. For local coverage planning, we leveraged the PALM-HDP algorithm, which uses an ensemble of heuristics to perform some multi-objective optimization like coverage and communications. And for global coverage planning, we used some front-loaded input-gain orienteering formulation to scale up to large problems. And on top of this, we have some meta-level switching and adaptation behaviors. So we evaluate the feasibility of the current policy of local and global level, and then we pick the best one. And then we also dynamically adapt our hyperparameters, such as coverage range, based on the environmental characteristics like spaciousness. To share some our design philosophy of the autonomy, for the representation, we try to balance between pessimism and optimism. So we want to guarantee by being pessimistic, we guarantee that the safety of the robot, and then we want to be a bit optimistic at some higher levels so that we don't miss out some small openings which connect to some larger openings. And for decision makings, we focus on performance and scalability and adaptability in different hierarchical layers. Among our many results, I picked this video to show. So this is an Kintucky Underground, which shows nice and resilient behavior of the coverage in very tight, risky environment. And then this corridor is connected to a wide opening suddenly. And then we adapt our coverage behaviors, then switch to some more general wide open space exploration, and then try to drive the robot along the center of the environment. And also among these two options, it picked the right way because we have some communication area on the right edge of the environment. So we have some very soft optimization characteristics for exploration. Yeah, now it's time for Marcel to present the mission autonomy.
Excellent. So now that we learned how our robots traverse these spaces, we also have to take into account that there's other phases to a typical SubT mission, being the setup and preparation phase with the deployment itself, the in-communications operations, and the out-of-communications operations. To achieve this and make all of these as autonomous as possible, we developed something called Copilot that would help our main operator to operate more than 3 robots at a time. And in fact, we tested it with 8 to 11 robots successfully, and all based on the autonomy features that we implemented there. Copilot allows for flexible task planning and execution, whereas autopilot augments what Sung just presented with some health monitors and other capabilities. Next slide, please. Yeah, if we look at the history of the autonomy teaming, 2019, our interfaces were very much console driven and required a lot of interactions by the operator. But we now tightly integrated our checklists, automated procedures, replaced ARVIS as an interface for the human operator, and added custom interaction modalities so that we could, in communications, interfere with the autonomous robot planning, and still out of communications, or when some information came back, be aware of what the robots are actually doing.
Marcel, you're out of time.
I'm out of time. Oh, sorry. Yeah, just that's the last slide is that we have a cohesive user interface, and our model is based on a BPMN, basically a state machine. So thanks.
Thanks to all the presenters. Great presentations. I would like to start the discussion with one question, and then we'll keep
so if I can jump in, we haven't presented yet, so Team CSIRO still needs to go.
Sorry.
CSIRO.
Oh, okay. Sorry about that. Yeah, you can go ahead now.
All right.
Are you talking through this mic, Jason?
Yeah, so I'll talk through that mic. I just need to share the presentation. Okay, so is that coming up?
Yep.
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 Yeah, so I'm Jason Williams. I'll just talk through what we're doing in Team CSIRO for Autonomy. And I'll do that to begin with here by going through like this overall block diagram. And so we've already talked about a number of the modules. So we've talked about SLAM quite a bit here. The object detector, I think we'll get to in one of the later ones. In terms of autonomy, so the first big block here is OHM, which is our occupancy map. And so that's a GPU-based implementation, which is able to process in real time on a fairly lightweight, like the Intel GPU that's built in. So it's able to process real time the LiDAR data and also a downsample version of the spot data that we have for the depth cameras. And then so that gives us the virtual surfaces, all of that kind of thing. And so then that then feeds into traversability analysis, which is done using two parallel pipelines here, which are running more or less the same code. It's just at a shorter range, higher rate, and a longer range and slightly lower rate. And so that's classifying ground as traversable or not based on steps and slopes for the most part. And so sticking with the global path, that then goes into a topometric map, which extracts a graph, which we do that, that kind of long range planning on. And so basically what this is doing is trying to construct a graph of all of the space that the agents have visited that they know is traversable. So that grows over time. Submaps are this, which are constructed by the Wildcat SLAM. So this traversability data is tied to each one of those. And just as those Wildcat submaps are shared in between agents, this data is also shared in between agents. And so the boundaries of the space which we've identified as being traversable then drives exploration. So at the lower level, once we get like those waypoints, we plan using a combination of hybrid A-star and a dedicated gaps planner, which was how we were able to get quite large agents through very tight spaces. At the higher level, the coordination in between robots aided by Wildcat and by this shared global map is then done through multi-robot task allocation, where agents bid on tasks and come to a solution of which agent will execute which task through consensus. So just to provide an example of all of this working together, this is a mission on our spot in the final run. So there's nothing kind of explicitly detecting stairs there. So it identifies that as a traversable terrain. It issues a waypoint close to the top. When it gets to that waypoint, it can see the top, so it just continues executing more waypoints. It gets to the boundary here, sees that it can't go any further, and so constructs a plan around there. So here you've got the downstairs, they're high traversal cost, so it puts that off. It goes and executes all of the tasks or the frontiers that it has on the top platform. It gets to the end of those and then executes a path down. So again, we don't have any explicit stair detection in there. So on the basis of that waypoint, it works out that the slope is going down, and so therefore it's going to command the robot down backwards, and on it goes. And so I showed the overall run overview at the beginning as the operator saw it. This is a slightly different view that recovers the information from all of the agents. The lines in between them are communication. So we'll see this again and talk more about those details in the next session. But the thing that I really want to point out here is that we've got this spot now which is completely out of comms, right? There's no link to that. So at this point, these other robots are within comms. But soon after. Okay. All right.
Thumbs up, sorry. But you can finish your thought.
Yeah, so basically what happens after this is that this robot comes out of comms, regains comms with this one, and yeah, so it's just interesting to see how that runs, but you can see more details of that on the pre-recorded presentation.
Cool. Thanks, everyone. I think everyone has gone once. So yeah, I'll kick off the discussion with the question that Sebastian made a really good point in the mapping session, that a lot of things converge to a LiDAR inertial odometry solution or some family of it. But like as far as planning goes, unlike that concept, we have like very different planners from very different perspective and very different nature of planners that we are seeing here. So I guess my question is that, are we converging to a point where we can say this family of planner can work better than this family of planner?
I would like to comment on that. And my comment will be that we need better ways to answer this question. We need better ways to do systematic evaluation between our different methods. This is something that is achieved on SLAM, and this is not something that is achieved equally well here. So we need both the new host of open sourcing that we have seen in SLAM, which is very impressive, and also systematic means to do comprehensive evaluation, same simulation environments possibly, but honestly not tuning things for the simulation environments, etc., etc.
Yeah, that's a good point. Yeah, I feel if you guys from the panel have any question, then feel free to jump in. I'll go through the questions that I have so far, and then we'll discuss on those topics. One of the questions is that, did we all try to rapidly explore the environment, or we also like incorporate the visual cues or semantic nature of the environment, and maybe the fact that maybe a little bit of an intuition that an artifact could be located on your left, so you should go to the left to get more information gained on that artifact, things of that nature. Did we incorporate that level of smartness in our planners?
Maybe I can answer that. So it's Graham from Team Explorer. Yeah, so particularly for aerial robots, since we had a very limited camera field of view, so that meant that we were explicitly planning for what was seen by the camera. So if you just drive down the center of a corridor, it means you might actually miss half of what's actually going in that corridor. And so I guess our solution to that was we explicitly had viewpoints that had orientation as well, that particularly looked at what the camera could see. So not just pointing what the Velodyne could see, but actually covering what you saw from a Velodyne, then again by the camera. I think to answer the second part of your question, I think we didn't really go and re-explore areas. So for example, if you saw an artifact, or you think you saw an artifact and go, you might want to go and see it again. We didn't really do that part of it. We're a little bit blind in that aspect there. I think for our ground robots, our ground robots had a much wider field of view. We had like multiple cameras in every direction, so there's a little bit less of an issue. So generally, if you drove down a corridor, you expected to see most things. Yeah, that's our approach.
What about semantic information, in a sense that maybe UAVs are better exploring some sort of an environment structure than a ground vehicle, for instance? Did we target certain sections in the environment?
We tried doing that. That didn't really come together, unfortunately for us. we definitely had a few different definitions of frontiers. So some frontiers, for example, like we had things that could identify doorways and that kind of thing. In terms of trading off between what an aerial robot can do and a ground robot, we wish we went further down that track, and we have research that's kind of ongoing in that area. Didn't quite make it to the competition though.
I think it is probably the case for most teams that certain ideas like that were explored, but did not make it to the level of maturity required.
Yeah, if I comment a little, so our team have established some soft optimization behaviors in general. So we tried several semantics, like some return to come behavior, as I showed in the video, or some active artifact search behavior. So if we have some artifact module detects something reasonably, then we add it to our global IRM representation and try to guide the local coverage behavior toward it. We deploy the communication awareness soft coverage in the competition, but for artifacting, mainly the challenge was the confidence level of the detection. So especially in challenging environments. So we try like some signal-based artifact, active artifacts searching or some visual things. But we decided to not to deploy. But yeah, it was a pretty very promising research venue, I think.
I can also add a comment for Team Cerberus. In our planner, it was mostly focused on exploration. However, on the animals, we also annotated the surfaces that all the cameras had seen. And on two of the animals, we had this pan tilt head, which also had a zoom in camera. And wherever we encountered region where a lot of this surface is not covered by camera, then we had a maneuver where the inspection head would zoom into specific areas to cover those parts.
Cool. Okay. There is another question. Did anyone has different autonomy modes based on mission progress? Like depending where you are in the mission, or depending on the time passed or where you are located, do you guys change modes? Like maybe have different parameters or something?
Here, I'll jump in. For CSIRO's, hi, I'm Matt from CSIRO, the Georgia Tech part. Ours was simple, but we had a curfew so that I think roughly 10 minutes before the mission ends, the agent would hit this time curfew, which doesn't make it immediately go back, but basically adjust the parameters for how long it can stay out of sync to make it very, very short. So essentially, once we get to that in-game time, the agents would heavily prioritize returning home to get that data over doing anything else. Although in the final run, the agents went down before they were able to actually execute that behavior, but that was the plan.
Yeah, and our team related to COM awareness, yeah, we have some such active behavior related to mission time. So if the robot leaves the COM area, then we set up a timer. And then for different robots, they have like a different time, like a configuration when to return. So if it is getting closer to the end of the run, then the return to COM behavior is invoked a bit earlier, so that we can come back to the communication and transfer the data. And once you get to the communication area, we want to release it to some out of COM area again. And then for selecting where to start the exploration again, it was another like a problem we wanted to handle, and then we have some like an approach for that. So yeah, so we have some established some COM aspects for that mission time context.
Yeah, I know we in our team, especially, we talked a lot about this problem as well, like other problems, and then never there was never enough time. that we would have different autonomy modes, like if later in the mission there would be a curfew scenario or something.
I just want to say we had similar actually behavior also from our side, and I think there was also a little bit of human factor there. For example, how do you explore? Do you go as deeply as possible, or do you maximize your span in the beginning? And this functionality that was described before by CoSTAR is exactly what will allow you to think: do I want to go one way or the other? And for example, from our side, we opted for this initial spanning across all branches early on, losing communication, coming back to communication, and picking again.
Yeah, actually, very good point. So how to capture the overall geometrical characteristics is also important for like an operation perspective. So we configured some different robots, in the order, like considering the order of deployment. So let's say we spent a spot 1 first, then we want to get it deeper to the environment. So in that case, we just let it go until like some time limit, and then try to give the information back. So yeah, the operation is another important factor, yeah, for that configurations. Thanks.
So related to talking about the human intervention as well, how much, I'm curious, like we can go through like each of the panelists, and who did rely more on human interaction than the autonomy, and like where would you lean towards moving forward on the scale from human intervention to autonomy? Like where would you lie moving forward, and where have you lied so far?
So I guess I can answer that from the CSIRO point of view. So I mean, we had a pretty interesting journey with that, where we started off, quite manual. Like the design was waypoints and all that kind of thing, and so then we moved to autonomous exploration in urban, and so that was interesting because as we deployed that, we really started to learn that autonomous operation is like having that kind of working purely that way is not really what we wanted. The operator wanted the ability to put their preferences in, and so from there we tried to aim for this semi-autonomous kind of mode where we gave the operator flexibility to insert their intent, their preferences and priorities and all of that kind of thing in the most kind of high level way that they possibly could, so that they can express preferences but not be kind of like just micromanaging waypoints and all of that kind of stuff. But like, I mean, we also kept all of those other things in there as fallback modes, and so like in that race in the final run, where there was an agent that like needed to get from A to B very, very quickly. I mean, that was where those kinds of fallbacks came in very useful.
Yeah, for Team CoSTAR, we reduced the human interventions as much as possible by introducing our autonomy assistant there. And that not only during the exploration phase of a robot, but also especially during setup, deployment, and the initial phase of everything. That helped us to deploy the robots very quickly and swiftly without overwhelming the single human operator. The operator would quickly hit like capacities when operating more than 3 robots, and we would only notify them of critical issues when something goes wrong. And so this human-robot interaction and communication is actually something we use to design our interfaces and change operations that way.
Yeah, I want to add a little more context there. So yeah, our team really targeted for very large space exploration. So yeah, we want to deploy like up to 8 robots or even more. And then we found the deployment takes like 10 minutes, 15 minutes to send out all the robots if we send one by one. So we put a lot of effort to have some autopilot, co-pilot behaviors so that we just, the operator clicks, as the top pop-up windows comes up, and then it goes by itself and entering the gate and then just go. So that was something, yeah, we wanted to show up, but yeah, it turned out to be a very small environment for the final. But yeah, that's what we wanted to do.
So this is Chow from Team Explorer. I think for our team, we are also like trying to push the autonomy as far as possible, and also like trying to reduce the workload of the operator as much as possible. So like usually in practice, or when we're doing like practice at our campus, we also like targeting at like very large area exploration as well. So usually what happened is we send out the robot, like off them go, and then there will be like a large amount of time that the operator was like basically has nothing to do, because we trying to like push hard to let the robot to do like on their own, like out of cons, and then when they return home, then they'll just all come back and offload the data. So then the operator can mainly focus on like being like a very good neural network to like select the correct artifacts. And that was like our approach like all the time. But then we realized then in the final competition, that might be like too aggressive as an approach to win the competition, because still like the environment is like too complicated for the robots to handle. Like one fell down a cliff and then one got stuck in the cave. We realized that if we had like the human intervention for that, or have the robot kind of coming home earlier or something, then we could like gain more points by getting the data from the robot. But then it was too late to realize that. But still, I think it's still like good to, I think like the purpose of the competition is still like trying to have us push the autonomy. So I think that's like still, I don't think like we'll regret too much about that, because that really gained us a lot of experience of like developing autonomous system. And also, I think just to echo the point from CoSTAR, for example, for now, like SLAM, for benchmarking SLAM, there are a lot of data sets and like data that you can just download and then evaluate the algorithms. But for autonomy, like those local planning, global planning, exploration, route planning, there isn't like much or data sets or platforms, because for evaluating planning, you have to like do this control in the loop. So there isn't much like platforms out there for us to evaluate. So actually that's what brings to the point that I would like to also kind of share with all of you guys that we like, that's why we put forward this platform, cmu-exploration.com, that we like put forward a lot of like simulation environments, so then like people can use that to evaluate from like local planning to like global planning in terms of exploration and route planning. And I think, yeah, I think still for us, I think we are still trying to like push the autonomy as far as possible, but still it's also important to have the human in the loop to be able to really kind of be robust, to build like a robust system and actually do like useful things.
I can speak a little from Team Cerberus's approach. So from the beginning, our approach was to have good autonomy for individual robot as much as possible. So the human should not intervene in the low level tasks of the robot of exploration and navigation, so that the robot does not require any teleoperation. However, if we look at the competition, we can see that humans have a better semantic understanding of the whole scenario, and it's humans who have defined the goal. So we focused more on robust individual robot autonomy and allowed the human operator to do more higher level decisions of where the robot should go, or what area a particular robot should explore, when to come back, instead of having these decisions made fully autonomously by the system itself.
Yeah, those are great points. I know like one instance where we had to teleoperate was there was this small narrow section in the cave, and our traversability was not, the traversability criteria was not propagating the tree forward. So our human supervisor nudged the robot a little bit into that part, and then the autonomy took over. That helped us like by a lot. Like we explored a whole new area. Okay, lots of good questions coming up. So let's address this question. How did teams approach deconflicting differing and competing priorities? Example, coverage, exploration, comms. Yeah, how did teams approach dealing with those competing priorities? Coverage, exploration, comms, etc.
Yeah, if I can start. Yeah, so that's a great question. So especially we have some multiple possibly conflicting objectives, then which one to prioritize is a main challenge in general. So as I mentioned earlier, like we have some common awareness, but is subtly tuned or subtly adapted based on the mission time and so on. So we had some higher factor for that, some prioritizing the among the multiple objectives is some mission time, and there are some trade-off between some risk and the coverage. So especially in a tight space, if we want to be really safe, we will not explore at all. If we want to be very coverage hungry, then we will be dangerous. So for that, to adapt that behaviors, we have some point cloud processing to check some spaciousness characteristics of the environment. And then we try to change the hyperparameters at runtime so that in a narrow environment, we know like it's a tighter space. So we are a little more more aggressive, or pursuing some continuing exploration. But if it is a large space, we don't want to get too close to the walls, but we want to just maximizing our volumetric coverage and just continue to a larger another space. Yeah.
Yeah, I know two of the competing objectives that I personally had to deal with was that the robots have to be far away from the walls to be safe, like ideally, because a lot of times like walls have those bad terrain features in the neighborhood of them as well. So whereas at the same time, the tighter spaces are of great interest to us because that's where the artifacts would be hiding. So yeah, so we had to make tough choices there.
On that point, what we realized is that on the higher level exploration planner, we can be a little optimistic and then rely on the low level navigation planner to be more conservative and be more aware of the safety of the robot than the higher level planner. That way we don't miss anything, but also make sure that the robot does not damage itself.
Yeah, that's a good point.
So a comment from us, Team Explorer. I think these kind of trade-offs happen in two different places for us. So one was through this behavior tree architecture where we had specific signals that we're looking for. So for example, if you receive a map from another robot via communication, then you would enter a certain type of exploration that exploits that. And so any of these kind of binary switches that happen more through the behavior tree. For more kind of slightly lower things, so for example, it's coverage versus exploration. For us, that was a little bit more implicit. So for our area robots specifically, we had basically a few different ways of generating frontiers. So some that favored exploration, some that favored coverage, but they all just kind of got pulled together into one big list of frontiers or viewpoints. There was some kind of selection function that was combined a few different terms that figure out which one to go to next, but we didn't really explicitly trade off between those things. They all kind of got pulled together and then got selected by other means. I'm not sure if that was the best approach, but that's what we went for. It seemed to work.
So from the CSIRO side, I think for us as well, that was pretty well implicit. One point where we were, kind of tuning things to adapt behavior and, trade things off a little bit was where, if our like the Titan vehicles were carrying drones, then they'd be more cautious. And then once they were launched, they'd be more aggressive in the way that they navigated.
Cool. Another interesting point is how did teams explicitly address the issue of dynamic obstacles? Like they appear in the map, but does your planner directly cater for those map changes, or do you have to do something additional to take care of dynamic obstacles? Does your planner give an alternate route if you're stuck with a dynamic obstacle?
Maybe I can answer that for Team Explorer. So I think, for example, like in the competition where like a door closed or something fell from the ceiling, but when we're in like backtracking mode, we could account for that. So if you're trying to return home and we found a door's closed, then basically we'd update the map based on that new information. I think the tricky part that we never really quite solved. So, okay, so then you go find an alternate route. If there is an alternate route, then you go use that. Then there are cases where maybe there isn't an alternate route. You actually have to go search for an alternate route. And so we didn't really solve that problem. So we solved kind of the first two things, but then having to, what happens if you're completely blocked? We didn't really answer how to do that.
Yeah, the way we handled it is we would, if our path would be in collision, the planned path, or whatever the criteria for collision is, traversability or something, then we would check the graph edges in the neighborhood of the robot and mark them occupied or unoccupied, and then traverse only the unoccupied ones. But that's tailored to the sampling-based planners or the graph-based planners.
Yeah, and in our case, we actually didn't focus on these dynamic obstacles from the ConOps, but we kind of handled that challenges by having some hierarchical memory about the obstacles. So, local risk map layer. So we have some temporal memory, spatial temporal memory, so that we see something as an obstacle, we don't want to go there, but it'll forget up. The memory will decay over time. So once we get back there, yeah, we'll have some another opening, and we found an opening, then we'll just pursue it. But you'll know, like also there can be some both positive negatives in some obstacle detection, of course. So especially there might be something confusing between the dynamic obstacle or both positive negatives. So for that, we have some higher level semantic encoding in the IRM. So if it is fluctuating too much and then we have some high variance over time, then we say it is high risk edge. So we don't prioritize it. We don't remove it, but if we have some other options, we just pursue the other safer rich edges, either the very flickering edges. There are some our parts to handle that, but yeah.
Yeah, so for CSIRO, we kind of handle that through experience, where if we attempt to navigate things and we can't, then we'd note that. Like, we tried to be really careful with that because we were doing a lot of testing with really challenging terrain that like you would think, it was not clear if it was traversable or not, and we kind of needed to be able to try it. For a significant amount of time to get past those kinds of things. So that made it, quite a challenging kind of thing. And, we thought quite a lot about, those kinds of cases. I mean, I think someone mentioned the case of there exists an alternate route that you already know about. I mean, that's kind of the easy case. I mean, there's another case where there exists an alternative route that you could explore and find, and then there's another case where there isn't one at all. But you also do have the case of is that dynamic obstacle going to block comms, right? So the idea of kind of waiting by that, to collect the data from that agent, using another agent is kind of something that's a real thing. So yeah, it was kind of complicated to try to take all of that into account. And so the other thing that kind of comes in there is like, could another agent look like a dynamic obstacle? Traffic jams and all of that kind of thing are like also a real thing that can happen.
So there is another question.
Perhaps, sorry, I'm sorry to interrupt this definitely fruitful debate. Obviously, each of the topics that we discussed today would get a workshop of its own, but I believe that if we should stick to the plan, to the schedule, so now should be the communication section. So
yeah, I think we are 12:20 was according to our time.
okay.
Time, yeah. So yeah, I just looked at that.
Yeah,
so maybe we should end the discussion here, and then move to the breakout room. What's next, Govinda?
Now is the communication section. So thank you very much. And,
oh, okay. Sure.
Yeah. My name is Peter Čížek, and I'm moderating the communication section. So I would like to start here, and we have a lot of different questions for communications. Like from the DARPA point of view, they already in the beginning like said and announced that the communications is also one of the greatest problems in the underground. And based on the videos I have seen, so there are a lot of different approaches to this problem. So I hope we will learn a lot today. And so without further ado, I would like to ask Team Cerberus, like Marco, Transator, someone, I guess, if they could present their approach to communications. Please stick to 5 minutes presentation if you could. Thank you. So we can see the presentation, but we can't hear anything.
Can you hear me now?
Yeah, we can hear you now. So the plane is yours.
Can you still hear me?
Yeah, still hear you.
Good. We're trying to figure out the situation, how to handle the audio. Okay, hi everyone, I'm Samuel, and I will be covering the communication part of Cerberus. So I will structure this talk into 3 components. So first I will talk about our network structure that we were using, then about some systems that had special networking capabilities, and in the end I will also talk a bit about the software that we were using to enable this. So I'm sure you are all very familiar with these like structured environments that are like large scale and have a very complex topology. And I'm also sure that you noticed that in especially like tunnel-like environments, you lose communication very quickly if you go around the turn or if you have a concrete wall in between or things like that. So in the end, it's very hard to get like a communication uptime that is like sufficient for your mission. And that means you can probably not just connect to one single source where you have all the robots connecting to directly. So from like the robots I saw and also the presentation so far, most of the teams then deployed some breadcrumbing strategy. And that's also what we did. So we used a Wi-Fi mesh network where we deployed reagent breadcrumbs. I think also other teams did that. And with that, I would like to talk a bit about the structure that we used for that. So we first had one mesh node directly at the base station on a tripod that was directly connected to our mission control PC. Then from there, we also connected a tethered rover with an optical fiber cable that had like 330 meters or 1,000 feet. And with that, we could basically extend the high bandwidth communication from the base station. Then we also had the elect robots that had breadcrumbs. So those could drop Wi-Fi mesh nodes, and also had a breadcrumb by themselves, so they were also a Wi-Fi mesh node. Then on top of that, we had the drones around. Those were not directly serving as Wi-Fi mesh nodes, but they were connecting to the client. So each of those DX2s were serving as either mesh node or also had an access point available for other clients. And then the drone could basically decide where it wanted to connect to, because each mesh node was broadcasting the same access point. So now I will talk a bit more detail about the rover and the LECT robot. So as I said before, the rover had a optical fiber cable reel and a directional panel antenna. And with this, we got like a high bandwidth connection to the base station that had a longer range than if we just had a regular DX2 with antennas. And as I said before, because it was carrying a DX2, this was also part of the mesh network. Then our animal robot that was carrying Wi-Fi beacons. Let me try the video. Yeah. So we had a tilting maneuver where we could sit down, and then there were 4 Wi-Fi beacons mounted on the robot, and each of them was held by a magnet. I can play the video again, maybe. So here you see the magnet. Sorry about that. Here you see the magnet, and then once the magnet is released, the Wi-Fi beacon drops, and the antenna has like a passive retraction mechanism, so it can like be put down, and then you group the Wi-Fi beacons together, and then once you drop it, it actually releases itself. So 2 of our LECT robots could carry up to 4 Wi-Fi beacons and deploy them in that fashion. So then let's move on to software. So we did use the following requirements for our software system. We had to handle a multi-agent system. Furthermore, we had to handle unreliability. So like if we lose connection or if we have bandwidth problems. So we also need to use low bandwidth because otherwise you cannot establish the connection for a longer time. And we also decided as a team to stick to ROS1. This may be something that we can discuss after each team's talk, what kind of software teams used to establish the communication. So with that, we decided to investigate 2 solutions. First, the multi-master FKEE and the Nimbro network. So in the end, we decided to use the Nimbro network because it was basically fulfilling all of these requirements. And furthermore, it had the very nice feature that you could select which topics you actually wanted to export. So you were not just streaming everything from the robots to the base station. You could select specifically what you want, and with this, you could also reduce the bandwidth that you actually needed. So here you have an overview of the structure that we used. You had like each agent.
Quick note, the time is almost up. So if you could skip to the conclusions, thanks.
Yeah, I'm almost done. So basically you have this structure with each agent or the base station running the Nimbro sender and receiver nodes directly communicating over TCP or UDP. And then we implemented another feature that is called topic on demand. So if you have a sensor or processing node that provides data, instead of just streaming all of that or throttling that and streaming that data, we implemented another feature to basically request just one single message. And then this single message was directly sent over Nimbro to the operator. So we could just request data when we actually need it. Yeah, thanks a lot.
Okay, so thank you very much. And I would ask Team CSIRO, so Jason Williams or Alex Pitt. I don't know who is presenting.
Coming through?
Yep. So now we can hear you. We can see the presentation. So the stage is yours.
Great. Thank you. Hi, everyone. I'm Alex Pitt from Team CSIRO, and I'll just run through our communication solution as it was deployed at the final event. So like a number of other teams, one sec, I can't see the presentation with the notes. Doesn't matter. Sorry. Like a number of other teams, we opted for a wireless mesh network with deployable drop nodes. For this, we opted for a commercial off-the-shelf solution from Ragent. These breadcrumb routers were all peerable. They came in 3 different flavors, which gave you a kind of different weights and sizes and onboard compute. We opted to use the smallest ones for our drones, which were only a single band at 5.8 gig. And our agents and drop nodes used the ES1s, which were dual band on 2.4 and 5.8. And then at the base, we also used a dual band solution. We didn't opt to use any kind of initial tethering. Rather, we had 2 masts at our base station, one with highly directional antennas and one with an omnidirectional set of antennas, so that we could try and take, in case the environments were highly linear at the beginning, or if they branched, we would be suited for either scenario. You can see in that animation on the right how our drop nodes were actually deployed in the course. We carried 4 of them on each of our ATRs, which gave us 8 deployable nodes in the final event. These used a simple side launch system. The smarts themselves were in the drop nodes, which would self-right, and actually spring-loaded antennas would actually get them a decent amount of height off the ground for better transmission properties. As I mentioned, these were dual band. We configured all our routers for a very simple bridged LAN setup with whitelisting so that our autonomy computers would basically all talk to one another. This was in a multi-master ROS configuration, so we were trying to avoid any kind of brokered scenario. We wanted a fully peer-to-peer solution, which was a lesson we learned from the tunnel event. To do our multi-master solution, we went with Mule, which was an in-house developed software package, which I'll go over in the next slide. We wanted this multi-master bridge to basically support roughly 2 classes of data. This was best effort, which were our commands, status, camera feeds if the operator required them. And then we had another class of data, which we wanted to be pretty strictly reliable, which were these SLAM submaps. Our object detections, obviously, which were required for scoring, our comms node drop locations, so we could incorporate them into our planning, and task allocation information that robots could use to coordinate their exploration of the environment. And for an example, SLAM alone could generate up to 500 kbps per agent, moving at a roughly 1 to 2 meters per second in a very large environment. And this detailed information is key to our highly accurate SLAM solution, but it also prevents quite a big job for the communication system. So Mule, our multi-master bridging solution, is a disruption-tolerant message bridge. There were a number of open source libraries, such as Nimbro Network, that we looked at initially, but the features we would have to build on top of them led us to the decision that it would be better to control that full stack of technology for easier control and introspection. So this offered us transparent multiplexing and transparent compression of everything. And that's not just one-off compression per message. You have the ability for strictly reliable data streams to actually use streaming compression across the full range of messages. So you can potentially avoid, if your topic stream is fairly redundant, you can compress that very well, which was the case for things like occupancy maps. Mule came with a couple of bells and whistles. It was dynamic discovery of its peers. It could have domain separation using simple preset codes, so you could coexist with the same bridged LAN, but keep 2 experiments on site separate. As I mentioned before, these 2 classes fit in. 2 classes of data streams fit into our quality of service offerings. One was volatile, which was at best effort, and persistent for the other one. Volatile was just direct TCP. Persistent was a hop-to-hop database replication. You can see a small diagram on the right, and we offered service calls that could control how synchronization would occur, although we didn't end up using a lot of that in the final event due to our smaller fleet size. And then in terms of how autonomy hooked into that, our operator could see a lot of information about traffic flows and synchronization status. Our task allocation could take advantage of that and even hand off pairs of sync return requests. If two robots were outside comms, they both hit their time limits and started returning, they could negotiate with one another to actually just have one of those robots return to comms range and offload that full set of data. And I think my time's up actually, so I'll leave it there.
Perfect.
Thank you.
Thank you very much. So the next is Team Marble. Steve Megler. So do we have, yeah, we have. Perfect.
There we go.
Yeah, we see the presentation and we hear.
Perfect.
So,
thank you. My name's Steve McGuire. I'm an assistant professor at the University of California, Santa Cruz, presenting for Marble here on our comm stuff. Here we go. So our comm solution had four really main goals. The biggest ones were that we wanted to work with commodity hardware, that we weren't tied to a specific vendor as much as possible with some of the other proprietary solutions that were out there. We wanted our comm to interop with our existing systems, particularly with respect to something like ROS2. A lot of our interesting packages that we wanted to use had not been ported yet to ROS2, so there was an interest in maintaining that level of compatibility. We needed fast reconnect times as part of our experience in Styx showed us, and the other events leading up to finals. Our robots might only have brief moments of connectivity that we needed to be able to leverage and take advantage of. Finally, we wanted to have prioritization controls to be able to keep some types of data from saturating a network medium while allowing other types of data to go forward. So we ended up implementing a fairly full stack solution. And just as a progress of what we implemented versus what we bought versus what we just made, you can see that by the time we got to the final solution, we're pretty much having to create all of our custom layers to solve the things that we want, from beacons throughout the entire network stack. While this took effort, it also gave us the flexibility to implement exactly what we needed to achieve the progress that we did. So a couple of key innovations here. We used a mesh layer from a company called Meshmerize that partnered with us to provide a layer 2 mesh networking solution built on top of AF9K hardware that ran on garden variety OpenWRT. What this meant for us is we kept our commercial footprint very small and allowed us to use any kind of AF9K hardware. From a $40 home router that was incredibly useful for COVID to a 2-watt radio from Doodle Labs that all were capable of running the same network stack. The second innovation that we had was our answer to the same problem that it seems that other teams now are having to solve as well, except we called ours UDP mesh. That allows us to replace the way that ROS works by itself, that ROS works in general, and have a single virtual channel between nodes to allow us to shape traffic and prioritize message types over one another. Finally, one of the problems, we have upwards of 30 radios in our system, and just keeping track of who was running what firmware and what software was a royal challenge. And so one of the things that we also included was a custom layer 2 management tool that allows to flash the same firmware image to every radio and configure them over layer 2, as well as a mapping function. That really helped with some of the system management of dealing with such a large population of radios. For our final event, we had our priority stack. We didn't actually have first-person view until we got to finals because we were concerned over the impact of FPV on our communications infrastructure. But after seeing how good our comm system was working at finals, we added it in with one line to enable that topic to be transmitted, and we were able to have our operators see first-person video from our robots that enabled a significant portion of our score. and contributed to our success at the competition. And I look forward to hearing about all the rest of the challenges that other team members have and how much our solutions are actually more alike than not. Thank you.
Okay, thank you very much. And the next one is Team Explorer. Bildros,
yep, that'll be me. A moment.
Yeah, we can see, we can hear. Perfect.
Excellent. Okay, so my name is Bill Drost. I'm from Team Explorer, and just going to talk about our comms solution. So this was our comms team for Team Explorer, just the Carnegie Mellon and Oregon State, along with one of our commercial partners, RTI, who provided a key part of our communication software, which was DDS. So I'll talk about that a bit later. Here's our Ragent DX250 radio. Every single robot and the base station use these same radios. The communication challenge is pretty much the same for all the teams. QoS and robustness in situations where we have big, thick walls blocking signals, certainly important to maintain good connectivity throughout all of our participants. So each of these parts kind of formed our whole approach to communication. In particular, all of our robots were running ROS1, so all of our code was ROS1 internal to the robots, but we used this RTI-based DDS software to communicate between robots. So very similar to the CSIRO and Marble approach, we had a UDP communication between robots to kind of enable us to work as a successful team. Since it was mentioned in the chat, we did have some issues with FKIE, which was the approach we used in Tunnel. So I bring this up specifically because I'm kind of curious if other teams experience these sort of problems. In particular, we had, it worked sometimes, but other times we just couldn't discover robots. We couldn't figure out why. Sometimes we just had very poor communication, even though we had a strong signal. So we rebooted a lot during the tunnel circuit, but we knew like leading into urban, we needed to find some different approach. So why do we pick DDS? So great discovery. I don't know if I've ever had a single problem discovering a robot that was legitimately connected to the network the entire time since I started on this around urban up until the finals. There's lots of great QoS parameters, such as configurable message reliability. So, sending video, you want to do best effort streaming and not worry about resending. Something like artifacts, you want to have a more reliable sending approach. And there are some other parameters like history control. So much like you would have a message queue for ROS, you would have, configurable message history for our DDS approach. We use token bucket for flow control. So just to ensure that no robot was sort of spamming the network with too much data at any particular time. So basically, as this architecture stands, we just had some communications manager, as we called it, which would you'd publish to a ROS topic on the robot. It would be translated into DDS format, go over RTI connects, arrive at another robot, and it would just be republished locally, in ROS format, just seamlessly. So everything is communicated in UDP between robots. DDS provided a nice functionality here where we could send data via UDP, but that we also had reliability for larger messages that couldn't fit into a packet. So essentially the Connects DDS solution would handle reassembling large messages and knacking, missing pieces, all like behind the scenes. We originally tried a TDMA approach to kind of balance the flow of information between robots, but we had some kind of unreliability there in terms of time synchronization. I'm just going to skip over that. Basically, if the time synchronization between robots is great, then they'll all kind of like alternate sending and balancing their load on the network. But if time synchronization is off a little bit, or you have some kind of bugs, then you could just end up flooding it at the exact wrong time. Just some more information about our DDS approach. There's some great tools. We mentioned RTI Monitor here that come with DDS, which enabled us to debug things like how much data each robot was sending, or what our packages, why aren't messages getting through, things like that. There's a similar Regent Commander type of UI that was available for our Regent nodes that allowed us to look at the network mesh level for any sorts of debugging information that we needed. Just gonna keep moving on through here. This is our robots. So we actually created a method for automatically determining when we should drop communication nodes based on the distance from the base station, line of sight being a Boolean constraint, and RSSI conditions. This work was done as part of a master's thesis by one of our students, Michael Tatum. So this was just essentially some heuristic formula to determine whether location was a good place to drop a node based on some inputs from these parameters. It was somewhat determined simulation based on experimentation at some of our test sites. The token bucket flow control I mentioned earlier is just a very simple method of kind of controlling the flow of information between robots. So essentially each robot has somewhat of a budget about how much data it can send. And we kind of tune these parameters during field testing throughout our practice leading up to the final competition. The data we sent, we use zlib for compression to try and reduce the amount of information that was going between robots. We experimented with some of the QoS and rate parameters.
Ah, sorry. You are actually running out of time, so
okay.
If you could.
So that was our approach. Yeah, I guess we had a distributed coordination method, which we can talk about in the Q&A, that was related to these muling questions. And I wanted to show this video streaming matrix to give an idea of the scalability of our approach. Okay.
Okay,
I think
nice.
I'm good. Yep.
Thank you very much.
Yep.
So next, I would like to ask Team CoSTAR to present their approach.
Hi, everyone. I'm Lily Clark. I'm presenting on behalf of communications for Team CoSTAR. Let me just share my screen.
Yeah, we see. Perfect.
Great. So today I'll spend a few minutes describing the comm system we converged on for the final competition, and then highlighting some of the technical challenges that we've actually already heard about a bit and lessons learned. So our network was made up of MIMO software-defined radios designed for mobile ad hoc networking that came from Silvus Technologies. Each of our ground robots had a 2-antenna model, as shown in the middle picture. Our drones carried the lightweight OEM version, which is shown on the top left. And our base station computer had a 4-antenna model. And then these same radios, each of our robots also had custom hardware to load and deploy additional radios or comm nodes to build up an ad hoc network of static nodes, which we refer to as the backbone network. So during the final prize run, our robots were able to drop 7 of these additional comm nodes. The Silvus radios also offered built-in layer 2 and 3 protocols and provide metrics like the signal strength and noise level through an API and through this convenient desktop GUI, which we were showing on the right. And these droppable comm nodes were crucial to our ConOps because they enabled data transfer over long distances without line of sight to the base. And this data transfer relied on several protocols, each of which provided unique advantages some of which we've heard about from some of the other teams. So similarly, for inter-process communication within a single robot, we used ROS1 for ease of distributed development. But because ROS1 is not really designed to gracefully handle disconnection and reconnection, we started using ROS2, the DDS standard. And ROS2 handles neighbor discovery really well, and it's well suited for sort of time-sensitive data transfer, which is what we ended up using it for. So this is like unreliable data transfer in that this data isn't buffered and retransmitted. However, and we'll talk a little bit more about the specifics of this design choice later, we didn't end up using ROS2 for reliable transmission, and instead we relied on JPL-MM, which is our variation of multi-master FKIE, which others have mentioned. So this, our sort of custom version of this, sits on top of UDP and relies on our data reporter module, which handles acknowledgements, reordering, and monitoring data queues. And these queues, we'll see, were important for decision making. So our communication aware autonomy, that sort of describes all the behaviors performed by the robot, which were designed to enable this timely high bandwidth data transfer. And these relied on two internal representations of the communication state. So firstly, the environment state captured the signal quality throughout the environment, the key metric being the signal to noise ratio to the closest static node along the backbone network. So each robot would update and share this communication environment state in a roadmap as shown on the left. And then as the SNR falls below some desired threshold, the robots would autonomously deploy additional communication nodes as shown in the map on the top right. And then secondly, the network state captures the amount of mission critical data that's waiting to be transmitted from the robot in those queues that I mentioned earlier, where the key metric is buffer size. And then whether the buffer is increasing or decreasing gives insight into how long the robot has been outside of communication range or how congested the network is. So as the buffer size rises above a desired threshold, the robots would autonomously decide to return to connectivity and prioritize data transfer. And that's what's being illustrated here on the bottom right. So with the remaining time, I'll just quickly highlight some of the specific challenges that other people might be interested in. So some of these were fairly simple, like we discovered our USB 3 cameras were causing a lot of noise, right, in the 2.4 gigahertz range. So we added ferrite beads and made small adjustments to the antenna positions of our robots' radios, and that made noticeable improvements. Fluctuations in the signal quality due to noise and the environment made it kind of difficult to use SNR thresholds for autonomy, which is what we had been doing. And even after sort of smoothing and outlier removal, it became clear during the final competition that we had enough droppable radios to just deploy them like generously, so every 20 to 25 meters. Other challenges were specific sort of to our architecture. So at first, our autonomy relied only on the collected SNR data, but this would become outdated as new radios were dropped. So we developed this predictive model to augment these measurements, which is what's being shown here in this video. And then one of the more challenging issues we dealt with was that large messages, specifically artifact reports or their acknowledgements, were sometimes dropped, and this would cause unnecessary retransmissions and delays. And part of the problem was that this is when we were using ROS2 for reliable data transfer, and it requires messages to be received in order. So we switched to our JPL-MM implementation, and we let some topics be received out of order, and this allowed the artifact queues to empty even if there was, say, a problem with a specific message. In the future, we'd like to consider sort of data prioritization, where maybe the most likely artifacts would be transmitted first, but that's not something we had time to implement. And lastly, we had issues sometimes with network congestion when multiple robots would return to connectivity simultaneously. So adding flow control using the same token bucket concept that others have mentioned helped to mitigate this, but in the future we would consider other medium access controls to make better use of the shared wireless medium, although those might come with other issues as time synchronization was already mentioned. So thank you. I'll pass it on to the next speaker.
Thank you very much for the talk. And the next speaker will be Dan Feigl of the CTU CRAS Lab. So please.
So do you see the video and hear me?
And hear. So
great. So hello everyone. My name is Jan Feigl, and I will provide you a quick overview of our approach on communication. So basically, what we use is 3 types of communication channels. We use the UVK Airmax Wi-Fi, but only for like very close communication within the staging area. Then as a primary communication channel is this Mobilicom devices. It's based on 4G with mobile meshes. It's based on precise time multiplexing. But what is the very important part of this is that you have to set up the size or the number of units in the network, and then you can adjust the output and input bandwidth to each individual nodes. And it also provides the hopping. But as a kind of backup, we also use our custom communication modes based on 915 megahertz, which is very low bandwidth, but in the end to provide us the ability to share the positions of the robots within the map. And these modes are attached to each robot, and also the larger robots, typically the ground robots, has a couple of these modes to be deployed. The Mobilicom, the main communication channel, is used for sharing the data, and this central point is actually the distributed kind of database for sharing the data. We use in the finals the database which is based on a RAGS database, which is non-SQL database, and the approach is actually based on sharing the messages or the data in an incremental way. So we try to keep updated data on each of the robots, and we have a couple of these streams or data streams like live cameras and control commands and so on. What is a very important part of this approach that the each message has some unique ID that allow us to fill the gaps if there are some missing parts. And what we also need to is to organize the messages in the way that we prioritize the messages, and we also build some kind of the visibility graph based on the carrier to interference plus noise ratio that is provided by the Mobilicom devices. And basically we do that for avoiding sending data for the units that are out of the communication range. This kind of database works as we are sharing the data, and if one of the robots collects some of them and is within the communication range of the other robots, then it is filled and sent and filled the database. So basically, we try to keep all the databases or the data on the robots up to date, unless they are not within the communication range. But regarding the breadcrumbs, the communication modes that are deployable, this is very, very low bandwidth, so it's around 1 kilobits per second for each robot. The packet or message size is just around 60 bytes. We use our custom like flood network routing base. We test the communication and deployment of these methods in Baroque Cave in Czech Republic. So we examined that we are able to cover almost 300 meters long part of the cave using just 6 of these modules. But in the finals, we actually find out that these modes, like the deploy mode, the breadcrumbs, are not so necessary because all the robots have been in a reachable range. one of the issue with the breadcrumbs is actually that the low frequency of the messages doesn't provide us the exact way to how to measure the signal strength, because the robots are typically much faster, especially the spots, than the frequency of the messages. So we need to estimate, and instead of like using the freeze formula, we work on the kind of learnable models, which we call projected free space ratio, which provide us the way how we can overcome these like issues with exact and timely measured signal strength indicators. So that's all, and I'm happy to have any answer to your questions.
Okay, thank you very much. And I will ask Kevin to present for coordinated robotics, or anyone from coordinated robotics. Okay, we can see the screen.
Okay. So
yeah, and we can hear you. Thank you.
For our communications, our goals were to try and make sure that all robots could talk to the base station, to be able to automatically route the messages between the robots and to the base station. At the urban circuit, we'd actually use manual routing. The operator would program in the routing path in real time as the robots changed position. We wanted to be able to get status from all the robots. We wanted to be able to get intermittent images from the robots, basically as they detected artifacts. We wanted to be able to get commands to all the robots, and we wanted to be able to have the bandwidth for a video feed from one robot at a time. At a lower level, that we roughly estimated that broke down to about a megabit per second and 100 packets per second. And that was about twice the bandwidth and packets per second we were getting through our network at the urban circuit. Our communications network was a mix of Wi-Fi using 802.11n and gigabit fiber. We were using Batman Advanced for routing. We had 2 robots with a powered fiber reel, so they would roll out the fiber as they drove along and used an optical rotary joint. And then several of the robots could carry droppable wireless nodes. Some of the development issues we ran into. Our original droppable node was a Pi 0W with a battery inside a PVC tube. And so using that, we could deploy either 8 or 16 of those per robot. But what we found was that they only really worked if there was Wi-Fi reflective material nearby or above it. Basically, the antenna was too close to the ground. And what we ended up doing then was we did our Weeble Wobble style that had the Pi 0W on the left at the top of the rod, and then a sphere with a weight in the bottom and the battery in the bottom, so that however the node was dropped or ran over or whatever, the antenna that was on the Pi 0W would end up at the top. The next development issue we ran into is network flooding. If you exceeded the Wi-Fi bandwidth even by a bit, the Wi-Fi resends would quickly shut down and overload the network. And so what we ended up doing is both the senders and the receivers would automatically adjust bandwidth to not overwhelm the network. The receivers could see it first in that they were not receiving messages, but the senders also needed to be able to reduce bandwidth. And so we ended up having both sides being able to reduce bandwidth. Minor development issue was Batman Advanced sends lots of packets between the nodes for setting up routing, monitoring the network, signal strength, and so on. We reduced that. There's some settings just we used, but not resolved. We're not totally sure what impact that had, but we had noticed that as a problem in the urban circuit. We didn't see it as much in the finals. Another development issue we had was Batman Advanced would frequently choose unexpected paths. If you had 3 nodes in a row, 1 to 2 to 3, it would frequently use a marginal 1 to 3 route, even if the hop cost was set to 0. So it wasn't trying to reduce routing cost. We did not resolve that before the contest, and we did not resolve that. We actually don't have that resolved yet, and that's still one of the things we're working on taking care of. during the finals contest, as I mentioned, the fiber deployment systems were powered, but it turns out we had some trouble with the motor controllers on those. But the design was good enough and the fiber was strong enough that we just pulled off the motors and allow it to deploy self-powered. So as the robot moved, it pulled the fiber off the reel. And so that had some issues with pulling it tighter on corners and such, but it functioned, and so that was good. We had the fiber wrap around the wheel 2 times because the fiber is a little bit tricky, and so we need to do some work on that. One of the times we're actually to back up to the entrance and allow the pit crew to untangle the fiber. The fiber was undamaged. Another time we just unplugged the fiber from the switch and let the robot drag the fiber in with it, and used Wi-Fi communication then. We were not able to get Batman Advanced running on the aerial vehicles that were using PCs. We were able to get them on the ones that were using the Xavier NX, but that meant that the majority of our aerial vehicles were not on the same network as the ground vehicles. And as I mentioned before, routing issues. But overall, we had multiple successful fiber deployments. We were able to deploy the droppable nodes and extend the range of the wireless mesh. And the automatic routing was used rather than having the operator do manual routing as they was driving. And that's all I have. Thank you.
Okay, thank you very much. And the last one present, I would ask, is Team Robotica.
Okay. It will be really short. So do you hear me?
Yeah, we hear you.
Come on. Okay.
The primary use case for Robotica robots was to explore a previously unknown area, return to the start position, and then run analysis on the operator's computer or a strong server cluster. The main disadvantage of this solution is that nobody had any clue about what was happening during the exploration if the robot was not in sight. To assist with this, we developed a LoRa, long-range radio-based communication devices, so that robots can report their status, typically SIS coordinates, and later also detected artifacts. There are several configurations for LoRa, where we pick the small packets, 40 bytes, but the maximal distance. During finals, LoRa module worked without any problem, but we observed its limitations in testing in caves. Note that if there is a team of robots deployed in the environment, each of them retransmits messages it has not seen before. Robotica logging is implemented in Oscar Python package, and it is relatively compact when compared to ROS bags. It allows deterministics replay of most critical modules, which is very important during development process, especially situations you would never be able to reproduce in real world. This is the holy grail of Robotica, and all processes and analysis is then based on log files, including virtual track. Also, such data can be analyzed on the other side of the world, say Switzerland, and compact size surely helps with that. It also helps for faster download from the robot to the operator's computer. We used standard Wi-Fi networking and Linux resync command to keep track of all active log files of all the robots. The operator then could review the logs offline similarly he would do at the home.
Yeah, so it was really short, and I can just show again the picture of the operator view. So as there was the question, like if anybody report automatically the artifacts up to here, which is the section of like urban tunnel and cave, we get the Wi-Fi signal, but after that we just get the LoRa. So if you have seen the clawback K2 moving back and forth in the urban store, yeah, these were the guesses by the network of the robot or the artifact. So that's all for Team Robotica, and time for questions and teams.
Okay, thank you very much, Martin. So I would open the discussion part, and perhaps one of, like, if we can see like what the teams used, like everyone used some different approach and different technology, each having its pros and cons, and like one of the important important question is how deep inside the the network stack do you think it is necessary to go, and how deep have you went when working on your communication? So obviously we can't just go to Walmart, take a off-the-shelf solution, and it will work seamlessly. So there was always necessary some of the changes. So how deep did you go, and how mature do you think that your technology was, and if it can scale to tens or hundreds of robots? So if you think that you are on the edge of the technology, or it can take much more. So if you can comment
I know
on that.
I can talk about Marble's solutions. I mean, we were finding firmware bugs in ATH9K, which is the Qualcomm chipset. So when you're finding firmware bugs in the baseband, in order to actually be able to diagnose those sort of things, you need to be as close to the wire as possible. I know I would be interested in hearing how some of the teams that used the Radiant and the Silvus radios, particularly the Silvus, when you have a custom waveform, whereas the Radiant is really just a repackaged Wi-Fi solution with a custom layer 2. How other teams' sort of experiences were with that. I know I valued being able to go directly down to the baseband, and that really helped shape our success.
So I can talk somewhat about the Silvus radios. Their latest version of their firmware is actually able to scale to like 30 nodes, so 30 radios pretty well. The previous version was not able to go beyond like 15 or something like that. So we had pretty good experiences with the Silvus radios.
So I can comment on our solution. So we have this Mobilicom device, which actually, as has been said in the presentation, has like, you have 80 megabits per second for the whole network, and you need to divide it between the units. And there is like precise time division multiplexing, and therefore, if you have like a lot of units there, then like the throughput drops significantly. On the next solution that we have are these droppable modules, and those actually scales pretty well, but their throughput strongly depends on the topology of the network. So if the network has topology of the full graph, you can lost up to 99% of messages. But if it is a tree or a path-like structure, you can get down to 20 to 30% of dropped messages per 60 nodes, 60 active nodes in the network. So this is, for example, quite a nice solution for us. So
I guess we probably had one of the higher level, and I just mean we didn't reach as deep into the network stack as others with our commercial off-the-shelf agents, but I definitely think more kind of cross-layer information really would have benefited us. We were, restricted to layer 3 and upwards, which, yeah, we just didn't have the project capacity really to have that kind of lower level engineering effort that probably would be necessary to scale to, fleets more than, triple, quadruple what we currently run.
I know that for Marble, one other consideration was also cost. And at least with the solution that we found, we were using these little GLInet pucks. And it's like $35 for a radio. And yeah, they're really low power, but it's the exact same hardware that you would find in the Doodle Labs component. Just the Doodle just has a much higher power, has a 2-watt front end to it, which made testing and debugging far more easy, especially in COVID times. We could give people these little, we could give everybody their own set of GLI nets, for a fraction of the price of one of the Doodle radio-based devices, but still have confidence that the whole affair would work when we got to actually do integrated testing.
Yeah, definitely. The price is also like very important thing in here. So need to keep it in mind. Any other comments? So if not, then I have here some other questions. What about simulations? Have you used simulations of the networks for the development? So I can say that we have tried to simulate the flat network for our mode, but otherwise we didn't use any sort of simulation like for networking. So what about others?
For Marble, we found that simulation was far more useful for some of the higher level features that that, for example, the team that had Mule, I think that was CSIRO maybe, had the feature, some of the higher level features of their system were baked into our sort of autonomy mission management system about how to distribute information, how to ensure that commands could be relayed through different robots at a time, and how to share maps so that everybody had a copy of everybody else's map eventually. For those sort of higher level aspects, the simulation was quite valuable. For some of the lower level aspects, at some point we designed our system so that there was like the physical track and then the virtual track, and then the two married up, and then we could go and make the simulation be useful. But for the purely physical components, the simulation wasn't as useful as it perhaps was for other aspects of the competition.
So anyone else has comment on this topic?
Yeah, I think we did some on Team Explorer. We did a few like 2D kind of simulations to test and debug our automatic node dropping strategies, and also to kind of try and guess what the RSSI values would be in like a certain region, but not hugely in depth, and we didn't rely on it very extensively, mostly just to sort of compare kind of what we saw in the field during our in-person tests with you know, kind of how we understood the optimal placement on our 2D simulations.
Okay, then another question. So how many teams actually use this like data mule sharing between the robots? So from what I heard, so I don't know, for example, for Cerberus, because I guess if you can comment on that, if you consider the fact that the robot can die inside of the cave and some other robots will have all of its information and bring it back to the base station, or if you rely on the just on the direct communication through the deployable modules. So I know that a few teams, I guess Marble said it, definitely, yeah, Marble, CSIRO as well, that they have this data mule, we as well. So what about the other teams?
Yeah, I can comment on that. So we did consider this data muling at some point, but in the end, we actually didn't come around to implement it. But it would definitely be a useful thing in our opinion. But we just, in the end, we didn't have the resources anymore for that. So also in general, our networking approach was also on a rather high level. So we did not dive as deep into all of these things as you guys did. So we bought the reagent solution and mainly used it as is, basically.
For Marble, we did implement a muling type of solution, as well as in an earlier phase of the competition in Urban, we had a smart beacon that coupled the physical mesh layer with a higher level at the application, that muling system, with the idea that robots could happen by and potentially drop off, make a deposit at the smart beacon, and then go along their merry way. The challenge for us was that the connectivity system that we were using at the time was very subjective to multicast flooding. So FKIE Multimaster relied on multicast advertisements to do discovery. And at least in our implementation of layer 2, what that meant was that every time we added a node to the network, we were increasing the number of discovery packets that were going back and forth and quickly exhausting network bandwidth. So that was something that we had de-scoped for the final event because of the bandwidth constraints. And at least from our perspective, that was a feature we could add to our radios and just basically turn our comm beacons into stationary robots for all intents and purposes with no sensing.
Yeah, for Team CoSTAR, we also had the same radios being used as static relays and on the robots, so they could all act as data mules. But our like robot communication was all opportunistic. So in at the autonomy level, when we were planning things like prioritize data transfer, return to an area with connectivity, it was always making decisions based on the known locations of just those static nodes, rather than saying like this spot will try to get closer to this other spot.
Oh yeah, I wish we could have had a team that's like, oh well, we could engineer some conjunction to get data back, and maybe someday we could, but not for this.
Okay. And one more question is also about like considering the data throughput. So what data were shared between the what are the like mission critical data shared between the robots and the base station? So for us, we could work, for example, only on that low bandwidth communication modules where only the positions of the robots were shared together with position of the drop node. Like we didn't drop any because it wasn't necessary. But then we shared only like the detections, like these three simple things. This was like the bare minimum for some meaningful operation of our robotic team. So how with the other teams?
I think I had to note in my slide that our SLAM data streams were pretty rich and our object detections were tied to the SLAM submap that they were detected in, and so there was kind of a sequential dependency there, which made that mission critical data for us, and so that was by far the largest component of our data. Everything else was kind of semi-opportunistic on top of that and probably comprised maybe like 10% or less compared to that SLAM throughput. And that was to agent to agent, agent to base, etc.
Hearing some of the other teams present, it's definitely evident that we all had to solve the same sort of subset of problems. I know that we moved from holistic mapping to submap mapping between urban and then cave, well, and then final, just to prevent and make better use of bandwidth management. And if you look at how we used bandwidth at the start of this project versus we were fast and loose with what we would transmit. And then by the time we refined our approach towards final, we had enough overhead that we could do things like add first-person video and not impact that mission critical data, which for us included in the following priority: manual controls of mode or even manual takeovers, telemetry, and then maps, and then FPV is just on that as able basis, where if we don't make it, it's not that big of a deal. There was an interesting a feature that I know I baked into our UDP mesh stack that I'm kind of curious how others handled as well. But mentioning that ROS2 doesn't let you do out of order reception. That was that feature kind of got baked in as well as there's also the idea of waiting for timeouts, that if you have a message that's fragmented over multiple multiple frames, if your robot goes out of range, you just sort of hold on to it for a little bit and then flush it at some point. And I'm surprised to hear that there are some solutions that would not include that sort of feature. That seems like if we had to come up with a minimum viable feature set for the right kind of ROS to mesh bridge amongst all of our teams, that sort of feature would be a critical inclusion. I'm just curious the thoughts of other comm leads on that.
Yeah, I can speak to that a little bit because I had raised that concern. To be honest, we had been using ROS2 up until like a few days before the final competition without issue, basically. And then we started noticing, particularly when we were adding additional comm nodes and additional robots, once we started sort of deploying at scale, we were having these issues with reliable messages getting through. So we didn't really have time to go through and figure out what exactly was causing those issues or play around with all the different tunings that you could do. We just sort of switched to this other implementation that we knew was working. And then in terms of the original question about what were our mission critical data, obviously artifact reports. We were also sending from the robots position estimates, incremental updates to the pose graph, and keyed scans, which were like LiDAR measurements that were important for loop closure, which was being done at the base. We also had a sort of fun experience during one of our field tests where the artifact team sort of broadened what was going to be sent to the human to interpret. And so they just started sending like way more data than was originally planned. And we had all sorts of issues with that. So I think a lot of what we found to be good bandwidth management, we sort of offloaded onto the artifact team to really determine what was important.
I would love to just carry on with this line. One of the things that we learned over the course of the competition was the picture is worth 1,000 words. And so in our initial implementation and tunnel, we did not include pictures of the artifact. And that was something we had added to have some sort of situational awareness for the human operator, that they can quickly say yes, no, or and evaluate based on just one picture from the artifact detection system. And so that was sort of, for us, it was, well, are we making the best use? Is that a good use of this bandwidth of these bytes? And as we learned in our testing, it was absolutely critical to success.
Yeah, just to comment on that quickly, I think we were sending like 9 different views of any artifact for the human, and so it quickly added up.
I believe we just took something from the middle of 10 views to get a detection.
Nice.
Yeah, we were sending about 3 to 6 artifacts back, or views of each artifact back from Team Explorer.
So for us, the images were also critical, like these artifact images, but I guess colleagues will talk about it a little bit later in detail. Yeah.
I just wanted to jump in on kind of a side kind of topic in terms of unexpected surprises from other components of the system. For people using 2.4, did you guys encounter difficulties with incorporating Bluetooth detection, or did you have some kind of aware system that could handle that?
For us, we didn't really worry about it. We had a small Bluetooth chip dongle that you might buy for $10 off of Amazon, and that was how we detected all of the Bluetooth enabled artifacts. One critical thing that was important that might seem subtle is not only to have the fact that it was a artifact of cube or whatever, but to include the SSID of the thing. and that let our operator know which detection, since it's Bluetooth, it's not nearly as localized as a visual artifact would be. But that SSID let us, and this happened in our final event where multiple robots detected the same SSID, but in different sections of the environment because the environment was radio transparent. And using those multiple detections, our operator was able to intuit and make some good guesses about where the artifact actually was and score as a result.
Yeah, that's a good point. I guess I was touching on more for the active scanning process of Bluetooth interfering with the 2.4 gig band. Not sure if other people encountered that.
If you use 2-watt radios, it's not a problem. And that's something it very well might be. And that's something that we just we didn't see it to be if it happened, it wasn't significant enough to be noticed, at least by Marble.
Yeah, so for the reagents, it was a really big deal, or at least that was what we found. Yeah.
So if I'm correct, we also didn't encounter this problem. Like we had this 5 gigahertz Wi-Fi and 2.5 gigahertz Mobilicom, and we didn't notice these interactions.
And I'm actually kind of curious about this. Was it that the Bluetooth, how did this problem manifest? How did you know that there was a problem with the reagent radio and your Bluetooth detector?
So, I mean, the Bluetooth detector is an active scanning thing, right? So it transmits, and so, you know, I mean, like, I guess we eventually discovered it quite late in the piece when we were trying to diagnose things and like had a spectrum analyzer, and like, you know, we hadn't quite realized that that was an active transmitter, or you know, put 2 and 2 together. And then when we turned that off, we were amazed at the quality of the comms that we were getting.
Okay, so you saw it in degraded comms, not in degraded Bluetooth. So it's not like you didn't see any of the Bluetooth beacons for the Bluetooth artifacts.
So Bluetooth detection was working perfectly, but comms degradation was large.
Yeah, but we suspect the constant scanning up the 2.4 ISM band was just causing reagents an incredible amount of difficulty in terms of getting packets through. So that's just, for us, it just manifested in much slower data rates than we were expecting.
I admit, I would like to actually try this out now.
Because at various stages of our competition preparation, we had various interferers bringing down our comms bandwidth. I think one of the earlier ones was the DJI light bridge. Whenever that was turned on, that completely killed our bandwidth. And then later on, we realized there was another interferer. We couldn't figure out what it was, and it turned out to be the manual remote controllers that we use for the tracked robots, because we used to use the manual remote controllers to drive the tracked robots onto the pit, and then we usually kind of set them aside but didn't turn them off, and they were.
And also internally, the robots would actually constantly probe to reestablish connection to the remote control, which had been since switched off.
Yeah.
And they were broadcasting telemetry, I think.
Yeah, yeah.
And then the last one was the Bluetooth scanning that we diagnosed and zoned.
But yeah, so I mean, our reaction to that in the end was that we were not actively scanning for Bluetooth in finals. So we detected cell phones based on Wi-Fi and the cube visually. And I mean, I think that was actually a really positive thing overall for us, for the impact that had on comms.
Okay. Anyone else has comment to this section? If not, I would ask whether there is one more question. Okay, there are more of them, but one question is, what was the strategy for dropping the retranslation units and the level of the integration of this behavior into the autonomy? So if the autonomy was like communication error, we have heard that with some teams it was a lot. But in general, how did you drop off the mode?
Well, for us, for Marble, I'm assuming, by the way, for the purposes of the question, that retranslation unit covers basically the comm beacons, the breadcrumbs, whatever we wanted to call them. For Marble, our strategy was based on distance. So using the Edgar mine where Styx was actually held, which is in Team Marble's backyard, we were doing distance testing and found out that our radios did not have a line of sight limitation. We were going to stop by a turn in the course and be stopped by solid rock first. So we had a distance measure of point to point for the beacon that was used by our autonomy stack to decide when to preemptively launch a beacon. There was a
Euclidean, only like Euclidean distance or like topology distance along the path that the robot took, or
I
really
believe
just
this was
Euclidean distance?
Visible. This was a ray traced visible distance.
Okay.
So the long hallway problem. And then alternatively, it could also be based on lost comm. If you lost comm, you would then turn around and drive backwards till you had good comm and then drop a beacon. And then the third modality that we had was a button on the operator's control panel to drop a beacon preemptively if the operator saw a promising junction that looked like a good place to drop a beacon. And even at the final event, we didn't drop all of our beacon. We didn't need to deploy all of our beacons to have coverage over the bulk of the course.
So for Team CoSTAR, we similarly tried a bunch of different things. We had manual comm dropping, which the human supervisor could press a button and do. We had a distance-based threshold, which is what we ended up using during the competition, but we also tried SNR-based thresholds, which I mentioned during our presentation, which would be like drop one if it gets to a certain okay value. Then we had like a backtracking mode where it would drop once it lost comm and try to return to the last point where it had comm. And then we tried a couple other things like automatic junction detection, like Steve mentioned, of if this is going to be a good place to drop one because it has line of sight in a lot of directions. We tried to make that call based on the point cloud data. And we also tried a spaciousness measure where they would be more likely to manually drop the comm nodes in areas that were sort of cavernous and more likely to not be a tiny narrow junction. But ultimately during the competition, we used the distance-based measure.
And Lily, just I think you present this, but we were tracking the signal as we explore. So we can reason about where was the best place to return if we had to return. So we're making that explicit.
So measuring the...
I know we basically decided to go as distance because we had enough nodes to drop. But yeah, we could have, we tried the other processes working. It's just that, okay, we have so many nodes, let's just drop as often as we can.
I would just make one observation that at least in our team, there was sort of a disconnect between some of the physical layer properties and the higher level autonomy. And part of that was by design because we didn't want the autonomy to care how messages were getting from robot to robot. But a downside of that approach is not having the kind of, having like DBM metrics that would be pushed up to autonomy so that you can figure out and have a better idea about the quality of the link that you're actually using. And that's something at least our team didn't implement that could have helped us with our exploration strategy to detect the worsening link and use that as a yardstick to decide when to help drop a beacon.
Okay. Any other comments on this section? Any other questions? Like short, quick questions. We are on time, so if
I'd love to hear from my fellow team members. There's a lot of I heard a lot of Ross going back and forth, and I'd just be curious as to your thoughts about even looking at the features that Ross 2 provides. I'm like, hey, I just re-implemented half of these. About the value / need of having a dedicated communications layer as opposed to using something that's a standardized sort of affair. I know I would be in favor of having the dedicated thing. We felt like we had to do it to get the feature set that we were interested in, and I'd be curious how other teams felt about that.
So we used ROS 1 internally and then ROS 2 for inter-robot communication, as we described. And that was actually a big benefit to us initially, was that because we had to basically say, these are the particular topics that are going to be transferred, it allowed us to have more control over those. And so that's one thing that I have concerns about. Just using ROS 2 purely across the entire thing, you would lose that control of basically being able to have, say, this topic can be shared inside of a robot, but it cannot be transmitted over the radio, and having more control over that. So that's one big concern I have with ROS 2 going forward, is that I think that there will be some need to at least have something that is controlling the information before it gets to the radio.
so for our team, I'm perhaps not the best one to report on this, but we stick to ROS 1. The guys reported for ROS 2 that actually this sharing, like this multi-master communication, is somehow unreliable. So therefore, we better utilize this shared database to really, prioritize what we need and get the data with the given bandwidth from place to place where we need it. And pretty much we did almost everything on the application layer. So routing, everything was broadcasted to everyone, so everyone has the information. So yeah, but we use ROS 1 for everything.
All right, thanks, Peter, for sharing that session. So we will go into another short break. I will play a 1.5 minute video, which I think is quite entertaining from a comms point of view. But feel free to go on a break for about 15 minutes. I'll set up the breakout rooms as soon as the video finishes playing. And the link colors are signal strength, and if it's red, we are already not getting anything from the robots. So if you look at the score and the time remaining, that's what makes it very entertaining.
Wish I would have had time to write this kind of visualization for Marble.
Yeah, at this point, we only have one mobile agent.
Did you actually use this visualization for the operator, or was this just for post-processing?
This is post-processing.
The operator had kind of a partial view of this. This though is kind of a global God view of the whole thing.
Yeah, that kind of shows us scoring the last point with 20 seconds to spare. So yeah.
Awesome. Joe Navinda.
All right, guys, I'll set up the breakout rooms now and see everyone in about 15 minutes.
Hi, my name's Ben Rell. I'm moderating the next session. I just want to do a check for some of the panelists, make sure you guys can connect all right. Carol Zimmerman, are you on the call now? Can you hear me? Can anyone hear me?
Yes, Ben, we can hear you.
Yeah, I hear you.
Cool. Okay, good. Mark, I guess you're probably with us in the conference room, are you, Mark Cox? Okay, I guess people might be away from this table. Cool. Just a quick reminder to anyone on the call, if you haven't already, if you are from one of the systems teams, if you could put your team name after your name on Zoom, which helps the discussion so people know which teams people are coming from. If you're not from other systems teams, it's awesome to have you here. And feel free to put your institution or your university or your company afterwards, so people have a bit of background. We'll be back to the next session at the hour in about 7 minutes. Hey, Sammy. Can you just do an audio check?
Can you hear me? I can hear you.
Oh, I heard you just at the end. Do you want to say something again?
Can you hear me?
I can't hear you at the moment.
Hello? Ethan, can you hear me now?
Okay, we are just going to do a sound check, make sure we can hear.
Ethan, can you hear me?
I can hear you. I don't know if that helps, but
Okay.
Yeah, I can hear
we can hear you, Bob, too.
I think you just need to come close to the microphone a little bit.
Okay, let me try from my phone then.
I mean,
You're muted at the moment, me though.
Understandable. We can hear you, but it's not very. It's not super clear.
Hello, can you guys hear me now? I can hear myself.
Yeah, that's coming through, Sammy. Sounds good.
Much better. You just need to.
I'm going to stop the feedback.
Yeah, turn off the speaker on the.
Let me do it. Sorry, guys.
Yeah, unfortunately, we're not allowed to use Zoom at JPL, so our setup's not quite great for that.
Can you hear me, Ben?
I can hear you loud and clear, Barry.
Oh, great.
Yeah,
Thanks.
I can hear you clearly as well.
Thanks.
Great, and we can hear you, Carol, too. Awesome.
Can you hear me? Can you see me?
Yep, can hear you.
Perfect.
Can hear you and see you, Carol. Awesome. I might just wait for Navinda, or Navinda, let me know when you're ready for me to take over. Or I might just dive right into it. So my name is Ben Rell from Team CoSTAR, and this is a panel on object detection. And I'll just start, for people who may not be familiar, a little bit of context is just to kind of play one of the videos from the competition of the fly-through of the point cloud. And so hopefully you can kind of see a little bit of what we're going through, some of the artifacts there, such as a drill, some small artifacts, and easy identifiable artifacts like the backpack, the rope in different domains. And this is what we're having to autonomously detect. Helmet, small, with a light in the front. And then we get to some more challenging ones, such as a cell phone, which is hard to see visually, but has Wi-Fi and Bluetooth. And hopefully they show a cube soon to give you a bit of an idea of what that is. So just for people who aren't too familiar, this is kind of what the objects are. There's a cube there that flashes different colors and has a Bluetooth signal as well. That's the objects that their teams are trying to get. So with that, we'll go into the teams for the 5-minute presentations. Again, I'll try to keep time and I'll just speak up once we hit that time. And I'll go in reverse alphabetical order for the team names, just so you guys can prepare for that, just to change it up a bit. So we'll start with Martin from Team Robotica. Martin, are you there and ready to go?
Thanks for the surprise. Yeah, I will try to. Share sound this time and share. And okay, I will ask again Lisa to talk for more reasonable speech.
Based on the experience from the urban circuit in Olympia, we switched to run robust artifacts detection directly on the robots. As the platforms are primarily designed for a long-term operation, the power for computing is limited. And yes, the computer consumption can be more than the motors themselves. We use 2 types of neural networks, an ensemble of OwnNet and SSD Inception v2. The net was based on artifacts, colors, and texture, developed by Cogito as replacement of original color blob evaluation back in Virtual Tunnel. Both neural network solutions took advantage of the onboard GPU, so our main control computers were extended by 2 Jetson Nano on Robot Clawback K2, and by Google Coral USB device on Skitty. There was a plan to even use 2 Corals to run real-time detection on both cameras in Skitty, but one turned out to be sufficient. Coral was finally plug-in solution which could be tested and prepared on other robots. There were 6 cameras on Robot Clawback K2, 2 security IP cameras with fisheye lenses looking forward and backward plus 4 Intel Reolsen's depth cameras. The images from IP cameras were superior to RGBD, so for artifact detection we used only those. On Skitty we had only 2 RGBD cameras, so there was not much to choose from. By the way, Skitty is our latest platform, and it was supposed to be imitation of Cogito's Swiss robot Freja, which had 6 cameras, and covered also the sides. The following video shows view of 2 main cameras on Clawback, detecting the drill and backpack and the quick exploration of cave part. Note freezing rear camera, which degraded vision in the second exploration of urban part, in particular the vent behind the corner, which would be easily visible by rear camera.
Okay, so I will try to run the video. I hope you will see it. Well, maybe. So this is videos from Clawback. Oh, I should run it first. Our robots never wanted to enter the cave. And yeah, let's quickly. So this is the very first run. I just wanted to show the quality of image really from the IP cameras were nice. And this is the moment where already the traversability evaluated that it's maybe not best to start here and Clawback return back to the stage. And this is the moment of the rear camera, at the very start. Yeah. So now we have only 1 camera. So shortly, this was like the very first run in the finals. For the second, the Clawback went to the urban part, but our detectors of the vent were not really. Oops, sorry. Stop sharing. The vent, like we have seen like 2 vents in the urban part, but the detector didn't work there very well. So, yeah, I will wait for later section discussion. Thank you for Team Robotica.
Thanks, Martin. I think there's some interesting points there to bring up in the discussion later on. We'll go to Marble next. So Harold, are you ready to go? Yeah, I can't hear you at the moment. Just sound check. Okay, I can see you're unmuted and talking, but I can't hear you. Okay, you're muted now. Oops, sorry. I still can't hear you, Harold. Sorry. We can swing back to you if you want to have some time to debug. Okay, cool. We'll give you some time, Hal, and we'll go to Explorer. And Bob, are you good to go?
Yep. Okay, cool. So hi, everyone. Okay. I'm Bob, part of Team Explorer. So I kind of figured first start off with sort of a high-level overview of the hardware constraints that we had, because that kind of informed our software design. So we were primarily looking at ground and aerial vehicles. For our ground vehicles, we had a pretty big perception payload. So we had 4 Intel RealSense cameras facing kind of in the cardinal directions. We had 2 thermal cameras for picking up the survivor and vent. And then we had Wi-Fi and gas sensing as well. For compute, we used NVIDIA Xavier embedded GPU, which we had some pretty good experiences with. For the drone, sort of similar pared down design. We had a UI fisheye camera off to the front. That was our primary sensor for visual detections. We had an Intel NUC. That was kind of the primary computer for the entire drone. And so we actually kind of made the decision to offload a lot of our CNN computations onto a neural compute stick. And then we also had Wi-Fi and gas sensing on the drone. Our high-level detection strategy was for the visual. I'm sure many teams probably arrived at similar conclusions. For the visual detections, we use CNNs. We actually had 3 different CNNs for each image type. So for the real senses, we had one. For the thermal cameras, we had one. And then actually we trained a separate one for the fisheye images, just because of the distortion around the edges. For the cell phone and gas signals, we actually found it really difficult to build sort of like a signal strength to distance model. So we instead just used the maximum received signal strength as a source location for these objects. One thing that I think we really emphasized over the course of the competition was generating this large-scale real visual detection data set. So we had this handheld data collection stick with all of our different cameras, RealSense, thermal camera, fisheye camera, and we basically walked this around in many diverse environments, and the stick really allowed us to get diverse viewpoints around the objects and really collect a dense data set. After we collected that data set, we had almost a dedicated team of undergraduates at CMU and then some people at Oregon State as well, basically hand labeling the data. We developed a tracking sort of module inside of our labeler. So we had the human label one frame, and then we use standard tracking algorithms to actually track that object across the various frames that were collected. And we ended up with about 70,000 RealSense images and about 30,000 fisheye images. All of our training for the CNNs was done using TensorFlow, just because we kind of determined at the beginning of the competition it seemed to have the best deployment pipeline for our needs. On the UGV, we compiled our models into the TensorFlow TensorRT format, which is really kind of gave us a minor hit in accuracy, but really boosted our FPS and allowed us to process all this information very quickly. So we processed the RealSense data at 15 hertz and then the 2 thermal cameras at 10 hertz. On the UAVs, we actually compiled our CNNs into OpenVINO, which is sort of a similar idea, but it enabled us to really deploy really easily onto the neural compute stick. We ran our CNN at 10 hertz on the fisheye camera. After we detected the objects, we filtered and localized them. So our detection threshold on the CNNs was really low. And so that really promoted heavy filtering afterwards. So we color and size filtering on the UGVs. We use a RealSense depth out to, I think, 3 meters, and then with wider depth farther than that. And then we required a minimum of 3 observations to be sent back to the base station, so that we weren't overloading the comms network too much. For the UAVs, similar story. We used the LiDAR data to localize, and then we required a minimum of 5 observations. Faced a variety of challenges. I think really one of the big ones for us was image quality. So there was a lot of white bleed, a lot of dust obfuscating our view. So we spent a lot of time in the lighting design. Also the noisy cell and gas readings. We spent a fair amount of time really trying to dig into even developing a basic model for signal strength to distance, but we really couldn't arrive at one that we found to be robust across environments. And then finally, platform diversity. So we kind of arrived at a scenario where each new camera required a new CNN, and that wasn't particularly desirable and made it kind of difficult to scale. Yeah, so I think kind of finishing up, there's some interesting future research directions. The first, I think, would be looking at more robust CNNs. So we kind of came to the conclusion that object detection across a wide variety of environments is not a solved problem. So I think there's some interesting work there. Fusing image types. So I think RGB and thermal data provide complementary information in some sense. And so if we could fuse that data and then feed it into a CNN, I think there's some interesting research applications there. And then, yeah, I think kind of harped on this a lot, developing those better physics models for signal strength to distance in order to do non-visual detection better. That's it.
Thanks, Bob. Pretty much right on time there. Thank you so much. I'll just check on Harold. Can you do an audio check? Are you good to go now? I guess that's a no. Okay, so then we'll keep going, and then we'll try to come back to Harold later on. Karel and Wojciech from CTU CRAS.
Okay. Let me share the screen.
All right. Okay, 5 minutes starts now.
Okay, I hope that you can still see it.
Yep.
Okay, so we have followed some very straightforward pipeline, which consists of processing RGB images by deep convolutional neural network. And then we just project the detected bounding boxes on the existing 3D map and cluster these 3D detections into some more confident or more reliable clusters. And if the cluster is sufficiently consistent, then it is reported to the operator, and operator decides whether it should be reported to the server or not. So just to be more specific, so this is how it works. Basically, we've got omnidirectional camera. Each robot has a little bit different set of cameras, but yeah, it works more or less the same. So what we have is that we are processing the RGB images, and we are obtaining bounding boxes for close this one. So for UGVs, we have separate NVIDIA Jetson Xavier dedicated to running the detector. So here it was easy. We just used some version, last version of YOLO, which was a little bit adjusted to our needs. And we were able to achieve processing speed about 6 frames per second using this GPUs. On quadrocopters, on UAVs, we did not have the GPU, so instead we decided to use mobile net architecture, which is significantly less hardware demanding. And it turns out that it can actually run 30 frames per second, but it turned out that we don't need it. So we decreased the frame rate to 6 frames per second to save the computational power for other processes and also save the battery. So the data set, we collected over 40,000 images. We have collected them manually just by driving the robot, using the gamepad in the environment and setting the objects into different positions, different illumination conditions, and so on. And we then just manually annotated bounding boxes using some simple interpolation method. So this is it. This is the summary. Overall, you can see that we have collected over 40,000 images. We did not distinguish the images collected from UGVs and UAVs. We just put everything together and trained the detector on the mixture of these data sets. Okay, so it's about how we get bounding boxes from RGB images, and then there is a second part. So it is as easy as it could be. So when we detect the object in RGB image, we project the bounding box either on the existing or on the current LiDAR scan. And in case that we don't have the available LiDAR scan in this case, in this direction, we just use existing Octomap. Then we just keep these 3D detections and we keep clustering them based on spatial locations and their class probabilities into in order to create some more credible clusters. And if the cluster is sufficiently credible, then it is reported to the operator. In our case, we required to have something like 5 image detections per cluster, and also low covariance in class prediction and spatial distribution of these things. So there are some examples how it looks. So there's a robot going in the tunnel, and there is an object detected and localized based on the RGB images. There is another example with the human survivor. So I try to summarize what I found might be interesting for others. So the toughest artifact or toughest object for us was cell phone. Also, humans were quite challenging sometimes because of either under illumination or over illumination using this reflective markers. Basically, the
time check, Carol, we're on 5 minutes.
Okay, so I'll be faster. Can I have 1 more minute?
30 seconds.
30 seconds, okay. So the cell phone looked like a small oversaturated rectangle. So in most of the cases, it was almost impossible to detect it from RGB images. And toughest false alarm objects was probably, again, small oversaturated rectangles, reflections, camera, illumination source, and so on. Our user interface looks like that. Maybe the only feature which I would like to emphasize is the ability that we could also adjust the brightness of the thumbnail of the detected object. So if the operator wasn't sure what is on the image, he could adjust the brightness and check it for on the other levels. And that's it, basically. So thank you very much.
Awesome. Thank you so much, Carol. And yeah, I'm sure we'll get back to some of the parts you had to rush over at the end of the discussion. So keep the slides handy. But thank you for keeping to time. We'll jump back to Harel. I think he's got his computer set up now.
Everyone hear me now?
Can hear you loud and clear. Yes.
Just waiting to share.
Carol, you might just have to stop sharing so we can get.
I'm trying to. I don't know how to do it, but.
Oh, I might be able to do that for you. Or the.
Ah, yes, thanks.
Oh, there we go. Cool. Thank you.
Can everyone see this presentation?
Yes.
Great. So I'm Harel. I'm from Team Marble. And I'm going to briefly talk about our solution to the object detection problem. So first, this is what we use for our perception head, and we based our artifact detection pipeline on RGB. So we used the 4 FLIR Gigi cameras for 360-degree vision around the robot. Each one of them had a 90-degree vertical field of view and about 120-degree horizontal field of view. And then we registered depth using our 64-beam Ouster LiDAR. So first, I kind of want to talk a little bit about how we trained our network. We used a variation of YOLO version 3. And for our core kind of data set, we collected around our campus about 100,000 different images under 3 varying lighting conditions. Each of our robots had 5-watt LEDs. And so we were able to dim those. So we did low light, medium light, and no light, which gave us a variety of lighting conditions, which really helped with things like the survivor and specular highlights in our testing. And what we found was we were getting mostly false positives after this training. So then throughout the rest of the testing during the summer, we would augment our existing training set with all these false positives to try and reduce them in future sets of weights. So the core of our pipeline starts with the Gigi cameras, but it's also very modular, and we can use any kind of camera with a RAS driver. So that's inputted into a TensorRT accelerated version of YOLO, which gave us a little bit faster performance from the traditional YOLO V3 model. We were using a YOLO V3 tiny model with a 608 by 608 resolution, which also dictated our camera choice at a resolution of 808 by 608. Once we get the raw bounding box from there, we look at our octomap, which is what we use primarily for mapping, and we do a raycast to the center of the bounding box, and we return that as the 3D position of the object. That's all passed into this artifact fusion module, which is based on a weighted median filter. And that just takes all the detections that were within a 5-meter radius of the same class and would send it over to the human supervisor for final confirmation before being sent over to DARPA. With regards to the Bluetooth artifacts, we used a USB Bluetooth dongle to scan the cell phone and the cube. We would report the SSID back to the human supervisor, and those were primarily localized with the median filter, and we took the position of the robot as the position for those artifacts, so they were a little bit harder for a human supervisor to localize. Gas was done in a very similar manner using the CO2 sensor suggested by DARPA. So a little bit of a summary on our performance. We had 27,433 raw detections from our neural network. And over the course of our pipeline, we filtered that into 25 reports back to the human supervisor for visual artifacts. And then what was really nice to see is every projected location that we had from an accurate detection was scored immediately for DARPA. Our human supervisor, the ones highlighted in yellow are ones that he had to move, and the ones that were moved were ones that we also, as mentioned in earlier sessions, we had a really hard time detecting the vent, so we added first-person video. And occasionally the human supervisor would see artifacts through that first-person video before the robot got enough detections to deem it ready to report. So those were scored with those methods. And kind of touching on why the vent was hardest, I know a lot of people have asked that, like which was the hardest artifact. The vent was hardest for us for sure, and that was mostly due to the kind of very sparse features on it. And we trained on an event that had white sides as opposed to black sides, which made our detector not really detected at all at the DARPA event. So that was kind of why we went to the first-person video. And overall, the average error for our visual artifacts was 1.52 meters using these methods. And I'll be happy to take questions during the panel.
Fantastic. Thank you for that, Harold. Thanks for taking the time as well. Next up, we'll have Mark Cox from CSIRO. Mark, are you there?
Yes, I'm here.
Great. Able to get your slides up?
Just having a...
Give us a second.
A second. Difficulty sharing the screen. You'll have to come back to me, sorry.
Sure, okay. So Sammy Lee from CoSTAR, you good to go?
Can you hear me, Ben?
I can, yes.
Yes, great. Let me share my screen.
Yeah, I can see that.
Can you see that? Okay.
Yep.
So my name.
Yep,
thanks. Yeah, I can start. My name is Sammy. I'm from Team CoSTAR. In the chat, we also have Barry Rich. We have also a few other team members working from different countries. I'm not sure if they are here today, but hi team. The challenge of the object detection, I would like to highlight the information load challenge of the mesh network and the human operator cognitive load, as some questions are listed in the panel list Google Doc. For our architecture, we have hardware and software solutions, of course. On the hardware side, we selected these like 7 types of sensors. And we have software techniques to detect and recover from sensor faults to keep the connections throughout the whole mission time. On the software side, we divide the data processing problem into visual and signal, and we build 2 pipelines. The visual pipeline takes in the color and the thermal images and run the object detection separately on them. And we have something called scalability to filter out the false positives. I will discuss that later. And each valid detection we will pair with the relative location. There's coming from this module relative localization using the reading from the valid line, and also a global location. Then all this detection will be sent to the base station real time. And at the base station, we have a reconciliation, further reduce the data load for the human operator to review later. Similarly, for the signal-based pipeline, we are taking in CO2, Wi-Fi, Bluetooth, and sound from their drivers and different processors. And each valid reading above the threshold would be paired with a global location and then sent back to the base station for the further visualization optimization and then show to the human operator. And so the highlighted components here are the part of what we call the ERP, early recall late precision stage object detection pipeline. And the goal of that is to reduce the false positives and optimize the data before being transmitted via the mesh network and to the human operator under the constraints of the GPU processors, network, and human-rated cognitive load. At the beginning of the pipeline, robot sensors generate many images at a high frequency. We sample them, for example, by selecting the least blurry images, and the images then go through the detector. And the resulting detections have a relatively low confidence at this point because you want to keep the high recall, meaning we don't want to miss anything, but of course we need to consider a high amount of false positives. And the scoreability and the other grouping technique can further reduce the majority of the false positives down the road. And before go to the human operator, we can enhance the precision even more. And after this whole pipeline with the human operator's help, we can achieve a really high precision and recall. So this is the methods we use to implement the ERP. I want to highlight some of them. So one is that the model we use, we use the YOLO version 5 medium pruned by 30% on Tensor RT. And at this high resolution and high detection rate, so we can get the small objects and all objects from far to be detected. Then and down below we have a color and size filter to estimate the likelihood of the object, so we know to filter some extreme outliers. And range filter to group the objects for different locations wise, etc. So that we can have one report for one detected object. The next stage is the reconciliation on the base station, so we can group the report from different robots. Then the reports would be sorted by scoreability, so the operators can optimize his time on the information with a higher certainty. Then this one is for our signal-based artifact detection. We use these 4 sensors as we discussed earlier. Then we use a similar techniques to handle all of them. So first we stream the signal strengths above the threshold to the base station, and then visualize them on the map looking like this in the user interface. And closer to the end of the mission, the operator can use the highest strength mark on the map of each signal ID, and then he can click on the map to get the reports generated and submit. So here I want to highlight how we optimize the visual report demonstration in the user interface. As I mentioned, ERP has the ranking step using scoreability. In the user interface, by default, all the reports are sorted and shown by in descending order of scoreability. And also we have this a quick access bar for the operators to select different confidence groups, so we can work on the high and the medium first, and then the low when he really have time. And for each report, we have this 4 thumbnail wheel. So they are coming from different angle of the report, using for example, the highest YOLO confidence, the brightest and the closest in the distance, the least blurry images. The result is
so just try to wrap up.
Yeah, so we actually can detect and report all the artifacts we encountered, but unfortunately we missed 1 5 signature because we submitted that 2 seconds late. And also this number shows how much we can prune the false positives down the low from almost 4 million color images at this point, and we only send 164 unique reports to the we group them for the unique reports for the human operator, and 9 of them are true positives. That's all. Thanks, Ben.
Fantastic. Thanks, Sammy. Okay, Mark, are you good to go now?
Yeah, I'll try it again. Sorry, I had a permissions issue.
Okay. Yep, I know what you mean. Thanks, Sammy. hear us clearly though, so let's see if we can get the slides up. Okay, I can see a screen. I can see slides. Yep, when you're ready.
Hi, my name is Mark Cox, talking about the object detection for Team CSIRO Data61. Our object detection software was the same across all of our platforms. For the final event, it wasn't for the early events, but it was for the final event. And we also had near homogeneous hardware as well. For our ground platforms, we had our CatPack perception platform, which contained 4 cameras in a 360-degree configuration. We used the Wi-Fi signal detection that was performed by the CatPack as well. And we also added the Sensorion SCD-30 gas sensor for detecting gas. This was not embedded in the CatPack, it was externally mounted on the platform. And like the other teams, we used NVIDIA Jetson AGX compute device. On the UAVs, we had a tiny variant, which we called the TIC. So it was, instead of 4 cameras, it was only 2 cameras, and it didn't have a gas sensor or a Wi-Fi detector, and it used the Jetson Nano rather than the AGX. And as we mentioned in the comms group, we didn't perform Bluetooth detection as the active scanning interfered with communications. So for the non-visual artifact detections, our strategy was very simple. For gas, we only broadcasted a detection to the operator when the change in concentration was above a threshold. It was similar strategy for Wi-Fi artifacts. The first step was to search for the known IDs across all of the channels. And once the device had been found, we would use the signal strength to determine if we were close or not. In both cases, we tried performing triangulation to obtain a more accurate location of each artifact. But we found this strategy unreliable and instead just presented the location of each detection and let the operator determine where on the map that the artifact was placed. For visual detection, we used the 4 cameras publishing at 3 Hertz. The object detection model we used was the CSIRO DNet object detector. We used this model because it was designed by people at CSIRO, and also the computational resources for this model is very small. So this model is capable of running at 30 frames per second, but we didn't need that level of that frequency. So we only ran it at 3 Hertz for each camera, so 12 Hertz in total. So much like the other teams, we thresholded detections based on the confidence from the detector, and then we localized the bounding box using the 3D point cloud, and we again filtered these based on distance as well. We compiled a new data set for the event consisting of 30,000 images. And once the objects had been localized, they were sent to the tracker. Oh, sorry. So as you can see here, all of our objects are stored in the global map. So what you see here is the local view of the agent, but the trajectory where it's been throughout the entire run. And when a detection, when an object is detected, it would be compared against the tracked objects, and new objects would be sent to the operator immediately. And another broadcast would occur if we re-observed the same artifact by closer than a meter. And the reason that we did that was that sometimes the detector would detect objects in poor illumination, and the operator was unable to confirm whether it was actual artifact or not. And much like the other teams, we employed the tracking approach to dramatically reduce the number of detections sent to the operator. So for the prize run, we detected 4,828 objects, and these were consolidated into 215 tracked objects across the 4 robots. And lastly,
you're on 5 minutes there, so just quickly wrap up.
Lastly, so we detected 23 objects. We detected 5 but didn't report those, and we passed 3 objects, but we didn't detect those, and the remaining 9 we didn't pass at all. And one of the things I loved about the challenge was that the operating point for the detection was completely determined by the operator load. And I thought that was really interesting part. And that's it.
Fantastic. Thanks very much. So we'll move to Sarah Centeno from Coordinated Robotics. Sarah, are you ready to go? Okay, I can't hear you at the moment. I think you're muted on Zoom there. Sorry, you just have to unmute on Zoom. At least it's showing me you're muted.
I'm so sorry. Okay, I'm sharing my screen right now.
Great. Perfect. Thank you.
Here we go.
Okay, that's great.
Okay. Hi, everyone. I'm Sarah Centeno, 3rd year mechatronics major student at Cal State Channel Islands. As part of Coordinated Robotics, I'm going to be taking you on a short walkthrough of our approach for our object detection in the challenge. Our hardware setup included 2 cameras with the same AR0230 sensor. We had an Intel RealSense and an ArduCam V0203 we had some fisheye lens. To connect them, we have a USB 2 and a MIPI. Our field of view was a 185 by 130. For the network to train for the object recognition, we use YOLO V4. We use option number 1 for our laptops, YOLO V4 with Tensor. On our Jetson Xavier NX, and then we had a YOLO V4 Tiny for the robots without GPUs. Our training image set totaled to 8,300 images. For our testing and image collection, we recorded both in the lab and around our campus. Here's a video right here of me and a couple of my other teammates taking one of our robots out to test our image detection. And then as a result of this training, we were able to, right off the bat in the finals challenge, as you can see here, we were able to detect the backpack and accurately report its location and gain a score of 1. That's a start. Some of the challenges we faced in our detection include false negatives and positives, as well as USB driver issues. So we could only use 1 fisheye camera at a time. Our CO2 threshold was too low, despite doubling our original threshold for the course per DARPA's recommendation. Our Bluetooth detection had depended on operator localization, which was thrown off as we were going into the course. Ultimately, after the finals, we collected about 200,000 images and managed to get to a total of 24,363 once we narrowed things down. We had 85 passes by artifacts, and we detected 3/5 of the ropes, all the helmets. We detected the objects. YOLO V4 had correctly identified These correctly identified 37 and 85 images. It worked overall well, but it's worth noting that the false positives, about half of them came from human operators that were in the frame during operation wearing the safety vest similar to training. And we'll be happy to answer any questions in the Q&A session.
Thanks, Sarah. I think my team and I have seen similar things of humans who are operating the robots being detected as survivors very frequently. I know we saw a lot in Team CoSTAR.
Yeah, it's just the safety vests.
Okay, we'll
they're
exactly, yeah, yes. We'll come to the final team, and that's Team Cerberus. And we've got Mihir, Victor, and Gabrielle. Three of you ready to go?
Thank you. I hope I'm audible. I'll start presenting now.
Perfect.
Let me know if you are not able to see my screen.
That looks great.
Hi everyone. I'm Mihir Kulkarni from Team Cerberus, and I'll be presenting our approach for the final, for the object detection for the final round. So we are dividing it into these 5 major subsections, and I'll go over them one by one. The first being the object detection algorithm training. We used the YOLO V3 detector framework, and we collected data extensively. So we had about 40,000 images spanning across the 7 classes of artifacts, and we had phone, cube, and carbon dioxide as non-visual artifacts. So so this was done. So we trained only one network for all the robots, all the cameras on all the robots. So we pooled all the images together and trained everything so that we could deploy them on cameras having different resolutions, different fields of view, different sensors, and so on. So we found that doing this was much more robust than training a separate network for every different type of camera. During this process, we actually had some difficulties. For example, in the initial stages, everything that was red in an image would be detected as either a backpack or a fire extinguisher. We could not deal with motion blur or obscurants or particulate matter in the surroundings. So for dealing with that specifically, we collected very specific data and considering those cases. For example, in the first 2 images, you see the fire extinguisher and the backpack kept in front of red backgrounds that were previously being detected as false positives. But after collection of very specific data like vent in front of white backgrounds or images with obscurants or some amount of motion blur, we were able to make the network much more robust and improve the quality of our detections by a lot. So after the YOLO network detected an artifact in an image, the location estimation of that artifact happened on board every robot. For that purpose, on every detection, the bounding box was converted into pixels. And for every pixel, the camera parameters were used to cast rays out into the map of the robot. So this happened on board the robot, and the points of intersection of the rays with the map were determined, and a spherical bound was constructed in the map around the estimated position of the artifact. And this happened for one measurement, and with additional measurements, the rays that intersected with the map inside the previous bounds were considered, and the location of the spheres were updated for estimating the position. With this, the label of the detector class was used so class-based probabilities were used, and this label came in handy while updating the probabilities of the class that was detected. And after a certain threshold was reached, that detection was frozen and was sent back to the operator for confirmation. For phone, cube, and carbon dioxide, we had a different approach. We detected the signal strength or the ppm concentration of carbon dioxide in a similar way. So when the robot was going over a trajectory, we had a set threshold for the signal strength, and the values above that particular strength were logged. And after the robot was sufficiently far away and the detections had gone below the threshold, a weighted mean of the position was reported as the location of the artifact. So we did not really look at the artifact directly and say, here it is. We estimated that the robot would be close by and close enough for it to have, for it to be accurate enough. This is an overview of the UI that the human operator used. After every detection that came in from the robot was displayed on the right panel with an image, an option to select option to reassign the class basically to that particular detection, options to visualize it onto the map here, which displayed the onboard estimation as detected by the robot. And there was another option to report that artifact, delete that artifact, or send a refined position as updated by the multi-robot mapping framework. So this was what the operator had used, and this was a procedure for reporting to DARPA. None of the artifacts went to the DARPA servers directly. Every artifact had to go through the operator manual confirmation.
Right. 5 minutes in here, so you quickly wrap up.
Okay, so these are the sensors and the robots that we used. We used 7sense, AlphaSense, and the antibiotics inspection payload with around 3 or 4 sensor streams on parallel nodes, parallel detector nodes. For the flying robots, we used the Intel Movidius and a neural processing unit on board the smaller robot, and a dedicated GPU on the ground robot. With this, the final slide is this: the result that we got. We scored 8, 8, 6, and 1 artifacts respectively in the order of the robots listed here, and we scored a total of 23 artifacts. Thank you, and I'd be looking forward to any questions you have in the panel.
Thank you so much, Mihir. Thank you, everyone, for those overviews and presentations. Thanks for keeping on time, because I think there's a lot of interesting things to discuss. One thing I find really compelling about this particular topic in the context of SubT is it's not just let's focus on neural networks to detect images and look at the detection performance, which obviously is one part of it. There's really a system to work in an applied setting for detecting these objects and locating them. And I think that was reflected in a lot of the team's presentations, where it's not just here's the CNN and how it performs. There's different filtering methods, there's a UI, there's obviously hardware involved. And I want to touch on a bit of those different aspects in the discussion. But I might start by kind of a question on something that was pretty consistent through a lot of the teams, and that is kind of filtering the detections beyond what the CNN does. So downstream of the CNN, where there's different types of ways of removing false positives, reducing the number of reports, and then eventually on the operator side of reducing reports. What did you find was the most impactful method of filtering for improving your precision? And what do you find had the biggest impact on kind of getting to the end result that you wanted?
I can start.
That's open to anyone to take.
So for Team Marble, our original filtering strategy was to do a histogram-based kind of binning approach to bin the different detections. But that had kind of a size constraint to the environment, so it didn't work as well in larger environments. So we ended up switching to a weighted median filter, where we'd weight each detection by the probability from the neural network. And we actually found that worked very well. Eventually, once our robot kind of got angles all around the artifact, it would really localize kind of right on the center of it. And then we also had a secondary kind of fusion technique that when multiple reports came from multiple robots on the operator screen, they would show up as the same report if they were within, I think, a 5-meter radius and already scored. So that was another area where we were kind of minimizing our operator workload by doing another round of filtering on the base station.
Anyone else want to jump in?
Yes, this is Sammy from Team CoSTAR. So at our approach, we have something called the, yes, Ben, can you hear me?
Yes.
So we have something called scalability. Basically, that is some different types of filter. For example, I don't see any teams actually using color and size to estimate the reports. So that was actually, we used that for the final, but not in the other conditions. So we estimate that we have the range for example, a backpack, mostly it's red. So we have a range of that when it's super dark and super bright. And we use that range to filter some, like, for example, if we detect a backpack like in yellow, because the shapes really look like the backpack. So we use some of those factors to actually help a lot to reduce the false positives and help us to like rank the probability of being that a true positives. So even though sometimes we don't filter them too aggressively, but when we reach the human operator, we can show them the ones we think mostly like the best color and in the size. So that's one of the approach we did.
Yeah, I think.
Like to chip in. Sorry.
Okay.
So
maybe I'll just.
Please go ahead. Okay, but I can.
Right. Sorry. Yeah, I guess just to kind of jump off of that, Team Explorer, we also use color and size filters. So one spot that I found color really helped is if our bounding boxes were too big. And we were suddenly using points inside the bounding box that were actually like nowhere close to the object. If the object was like sitting on a column or something like that. So yeah, in that scenario, localizing using the color we actually found to be very helpful.
Hi, this is Mihir from Team Cerberus. We did use the size, and we did use the size of the object as well. So in the rays that we cast into the map, we check the size of the object based on the intersection of the rays, and we were able to reject quite a few of the detections based on that. We did investigate. So our approach was basically based on ray casting, and we did investigate filtering out the color based on the kind of artifact we had, and projecting rays only for pixels having the colors above a certain threshold for that artifact. And that did improve computational performance for us, but we didn't end up deploying it due to reasons in the final run.
Anyone else got comments on that topic?
From our point of view, like I don't think of object detection and tracking.
We lost you there on the CSIRO side. I'm sure if anyone's there on their computer separately, but we lost the conference room.
It's just the bridge altogether.
Okay, I have to come back there. Carol looks like. Okay, I got some feedback now from Pullenvale.
I'm sorry about that. We keep getting booted from the Zoom call. What I was trying to say was I think of object detection and tracking as the one problem now, and one of the things I was kind of curious about from the other teams is that, like, one of the advantages of employing tracking is it removes some of the variability that you get from the object detectors in unknown environments. So we certainly found that our posteriors varied depending on the environment that they were in, which made it difficult to choose thresholds. It'd be interesting to hear if the others observed the same thing.
Yeah, let's open it up to the panel. Anyone got comments on Mark's and there in terms of adaptive thresholds or seeing different thresholds in different environments?
For us, it was mostly kind of a hand tuning type. It was mostly hand tuning for our thresholds. We tested in a variety of environments around here in Colorado, and we actually found thresholds that worked relatively well at all the environments. I think that was largely due to our really bright LEDs that were more or less consistently lighting up the environment in the areas we were actually trying to detect the objects.
Yeah, for Team Explorer, we also used hand-tuned thresholds. Just due to like human resource constraints, we didn't really implement tracking. I think it definitely could have helped. So actually, the areas that we were testing in leading up to the final circuit were much larger in terms of scale than what we saw in the final competition. So our detection thresholds were extremely low. And the end result was that we were sending a lot of data over comms and overloading the human operator. So yeah, I think improving that thresholding or tracking would have definitely really helped us.
So it was
Sami.
more. Feel free to continue.
Carol, do you want to go?
Okay,
And then
so
we'll have
yeah,
Sami.
so for CTU CRAS Norlab, it was more or less the same. We were also using hand-tuned detection thresholds, which has been usually tuned in a way that we wanted to preserve very high recall, but we did not want to overload the operator completely. So we were targeting towards operator have to process not more than 100 detections during the 1 hour mission or something like that.
So, Sami?
Yeah, same for Team CoSTAR. We have the threshold to control each object at each stage. So we can we use like those our preliminary run to actually estimate how much we can do in such as like more narrow area than the huge space we have been testing on. Yeah, because we at the beginning we have thinking like, oh, the DARPA we're gonna put things like really far away, like 20 meters away, and we were able to achieve that performance. But when we go to the final condition, we just realized that that's so different.
One of the things I found interesting, I think it seemed consistent for most of the teams, was that everyone opted for high recall. We don't want to miss an artifact, given we put all the effort to get the robot there. And I want to kind of get a poll for the teams of, firstly, kind of what was some things that you've learned now that you would do again differently for the data collection and training? Because we know that the data is a really big part of the neural network performance. Whether more types of data, get a sensor rig earlier, data augmentation, what were the things you did well, and labeling? What were the things you would do better? What are the lessons learned from your data collection and labeling? But also, what do you think could be done in general from a research perspective to improve both precision while maintaining recall in this type of context of effort? So data collection, augmentation, training, and labeling, what were your lessons learned there? And how can we improve precision while maintaining recall?
I can start off this Team Explorer. I think actually kind of as you alluded to in the beginning, I think from my perspective, the big source of our problems were more hardware and sort of like HRI related. So I think we spent a lot of time leading up to the final circuit dealing with our lighting solution. So we originally had these really bright LEDs very close to our RealSense cameras. And this was causing not only a lot of light bleed into the camera, but a lot of illumination of the dust in the environment. So we spent a lot of time, moving LEDs to different positions, trying shielding, that sort of thing. And that helped a tremendous amount. I think also on the HRI side of things, I think if we had been more intelligent in the way we actually designed our GUI, I think the massive amount of false positives that we sent back wouldn't have been so much a problem. So we actually, at the end of the competition, we actually had a pretty good communications network. So we actually send over a decent amount of data to the base station. But in terms of organizing that data in a coherent manner and reducing that base station cognitive load was really a challenge for us.
I think we'll dive into those two topics more as we go forward, the hardware and the UI. Really good point. I'm going to jump in on the data sets.
I can go. For Team Marble, for us, it was we collected mostly around our campus at night in different kind of environments. We have like a variety of different building styles on campus, so we were able to do a variety of data and up at Edgar Mine. But we also saw that, for example, at the cave environments, we didn't have as great realistic data and our weights didn't translate quite as well. So that does kind of beg what we could have done a little bit better. And we did at one point experiments with a little bit of a synthetic data augmentation, but we found that it really wasn't changing our neural network performance that well. And I think that's largely due to we tried to do it on some of the simulated models from the simulator and try to put them on realistic backgrounds, but that didn't really translate that well. Probably because the models aren't as realistic. But I think doing some of this with like some of these newer kind of rendering engines and especially like gaming engines and doing a lot of the data training from simulated data would really reduce the workload. Because for example, for our virtual weights, we had a pipeline developed where we could actually just automate it when we drove through the simulator to do the bounding boxes and everything. So I think you could really get tons and tons of data very quickly by utilizing a more realistic simulator in the future.
Cool. I think CSIRO or Mark, you were going to say something?
Yeah, so I was, I had a bit of a different tack with it. Like if I was DARPA and I do this competition again, I would probably release the artifacts the day of the event and really drive home the fact that having to collect 100,000 images in order to make something useful is not, is not something that would generalize to the types of activities and clients that we deal with. The second thing I'd probably mention is that, like, for the clients that we deal with, you have to turn up to an unknown environment, and the systems have to work there and then for an hour or 2 hours. So generalization is really important, and I think trying to achieve generalization by seeing everything is not the right way to go into the future. I think we need to revisit what generalization actually means parametrically.
Yeah, another interesting point I think I'd like to dive into a bit more, but I want to leave opportunity for other teams to comment on the data set training and precision side of things.
Can I still add some comment?
Yes, please, Sam.
Okay, sorry. So from our these years of data collection and training, we just found that the model's really overfitting on the lighting conditions you fit to the model. So if we want to detect the objects in a really dark environment, we just need to find those data and fit it in. And for our team's approach, we mostly rely on the real world data because we find that really effectively change the behavior using that. But so actually the model we use actually doing a really good job in detecting really far and really dark. Then it actually much better than human can actually detect in that scenario. Then we ended up being too good on that, and the human operator could not really distinguish it. That then we do some image enhancer in the UI so that this really good behavior can also be compatible with what the human operator can conform. So this is our approach. But of course, we also have some LEDs mounted on the robot to enable us to see more than 10 meters away. So within that time is fine. So even more than 20 meters, we're gonna see the objects really dark. So we always try to make sure the model is able to do that in the dark environment. Yeah, that's it.
Thanks, Sam. Any other comments on that?
Maybe I could just add some thoughts to Sammy's comments. I'm also from Team CoSTAR. I think, yeah, just to answer your question about precision, Ben, I think it's going to be really, really tough to kind of achieve, to sort of take the operator out of the loop and kind of get precision up to the point where, where it's kind of fully autonomous. I think, you're, the approach that most teams seem to be using, is probably the right one, which is kind of solve the narrow problems and then leverage the operator to kind of get the final step. You can achieve that high recall. You can retain the true positives, and then it's about kind of, how many of the false positives can you prune away and make it a manageable problem for the operator. I think that's kind of the core of this, but yeah, just my opinion. I would be very surprised if you, if you see kind of a fully autonomous solution that manages to just get everything, that peak high precision, high recall. It's going to be super tough.
Thanks, Barry. And I saw Costas was about to say something. Can you? I think we can hear you.
But I'm not sure if I'm audible.
Yes, we can hear you.
Okay, good. So I want to say that, from all the presentations, it's pretty evident that with respect to, as long as we know the artifacts, because I agree also in one of the previous comments that, it's not really realistic to assume that you know specifically what you're looking for. But anyway, that was the competition. I think I was observing the images throughout these presentations, and I was trying to find out which team had the better camera images in this competition. And it'll be very interesting to see also what will happen in the more long-range environments. And I think for me, this will be something very interesting to discuss. Of course, also when we have the time to write papers, et cetera, for the finals, some of these details can be discussed more, because there is a lot of technology for better low light performance that could be exploited. From our side, we didn't exploit this at all. We didn't investigate it in too much detail out of limitations. But if you see what goes on in the smartphone era or these type of areas of technologies for cameras, there is a lot of work for low light imagery and so on and so forth that could be useful for this type of environments.
Yes, great comment, Costa. Maybe we can kind of circle that around to the teams as well. And because one of the things I think that was lined up was how much does hardware impact your performance in terms of your light configuration, which Bob touched on from Explorer, the cameras, as Costas is saying. How much does that kind of system design of your hardware impact the performance, and how much does that limit your performance?
Well, from our point of view, our training data consisted of multiple devices taking photos. And from the lighting point of view, lighting does have an effect, and so does like the gain in exposure control. It was also interesting from all of the talks that no one spoke about exposure control. There could be a few things to do there. But we certainly experienced some variation in terms of gain and exposure time.
Go ahead.
We also had a little bit of testing done with gain and exposure, but due to lack of time, we didn't have that much time to really fine tune it. So we kind of left it on auto mode for our cameras, which seemed to perform pretty well. I'd say the biggest problem for us in low light was the added motion blur of the camera. The rest of it, like the images were clear enough from our cameras in low light. We chose a relatively wide aperture lens, relatively high aperture for better light performance, but which result in more motion blur. So that was kind of our trade-off, was motion blur versus quality of image.
Bob, are you gonna go?
Yeah, I was just going to say pretty much exactly what Harold just said. So we also looked at exposure, but due to time constraints, among other things, we found it difficult to tune. I think it was interesting, just due to the diversity of the environments for this application. You could be in a completely pitch black environment. You could be in actually a very bright environment. We found it pretty difficult to actually find that right balance in terms of exposure time.
Ben, can you hear me?
Yes, you can, Peter.
Peter Maloney, I'm formerly from Emerson. We had a solution which relied on a gimbal system, which we ran for tunnel, urban, and cave, and we went with the CSIRO system for the last event. There's a lot of learnings around that as a hardware piece. One of the key ones was the reason for the gimbals was decouple the exploration of the drone from the coverage searching that we're doing with the camera, or trying to do with the camera. And effectively, that searching algorithm changed earlier this year to basically focus on targeting surfaces, and the hardware piece in terms of the amount of exposure you got, because we're focusing on surfaces, the light actually had something to reflect off. We actually got more light back into the camera. Previously in cave, for example, we'd aim off into a cavernous area, and then you'd get this massive whiteout where the drone would be illuminated, but it'll be black after, out towards the area. And so you have major issues there with exposure control.
Thanks, Pete. Anyone else on the hardware topic?
So maybe it was quite similar for us. We found pretty complicated to work with the cameras, which has automatic white balance. So in the end, we prefer the camera in which we can switch off the automatic white balance.
I have one more quick comment. I think in this area, the future is probably going to be more in the software processing pipelines than the actual hardware. If you kind of look at where smartphones are going, a lot of the newer phones are using like pretty simple cameras, but are achieving really great low light performance just due to advancements in the image processing pipeline. So I personally think that that's going to be like the future, as opposed to trying to improve the raw optics.
Interesting. On that topic, I can't remember which team was presenting on that, but someone was asking about the dust handling, and I take it that was in software, or did anyone have a particular solution to tackling dust or obscurance in the image, and how to handle that from a detection perspective?
So we actually found that we could kind of avoid dust through a hardware solution. So basically, by moving the lights far away from our cameras, we found that we were able to achieve the best performance in terms of not illuminating the dust right by the camera, and instead illuminating the environment.
Okay. Any more comments on the hardware? We've got about another 4 minutes before we go to the breakout rooms. I wanted to touch a little bit on the, Victor?
Yeah, I think so. One setup that we were very happy with and switched to in the end was the Alpha Sense. So it's a sensor made by a spin-off from our lab. I think one very big advantage was that it was one unified setup that we could use between all the different robots. And we also tried to keep the lighting very consistent. So I think this helped on the detection side and also on the mapping side and so on. I think this was quite a trend in general between a few other teams as well. And it did have custom auto exposure and white balance on there. So I think this worked quite well. So on the hardware side, there's quite a lot that can be done, and very good time synchronization helps a lot for mapping as well.
Awesome, thanks, Victor. And in the time we've got left, Navinda, hold off. We've got one more question to go through before you kick us out. I just want to touch on UI. And the way I see it from these presentations is that the UI is really, I think Bob from Explorer was touching on that the HRI was a critical component. And it really is that last stage of filtering. And we joked, we've got KionNet. Kion was our operator, and KionNet was human detection. Obviously, we can't beat humans at that at the moment. So I guess I'd like to go around to everyone, and I might just call people out as we go through, of like, what were the key parts of your UI that you found were most important to manage the operator load, to make sure they could get through all the detections, to better manage the ability to go from many reports, perhaps many false positives, down to the ones that mattered. So yeah, what were the key parts of UI that you found were most beneficial? I might start with Sarah from Coordinated Robotics. Sarah, can you hear me?
Is it us?
Yeah. All right, you're on.
Hi.
You're on
yeah.
mute.
So. No. You
go.
Hear us? Can you hear us?
Yes.
Yes. Okay. So the biggest feature I think for our GUI to get through the objects that we received was to put them all into a list form. and to be able to sort that list based on class or confidence or which robot detected it. That allowed the operator to really go through the list as quick as possible and to quickly sort them and figure out exactly how they wanted to review each object. The other thing we did as well was did a quick evaluation process. So if there was an object that we didn't quite know, it was effectively a maybe. We just sort of put it into a separate list and could quickly sort of reject objects between definitely rejections and maybe options, and then review all the maybe options right at the end. And that allowed us to really quickly go through all our objects.
Using the keyboard rather than the mouse.
Yeah, using the keyboard. We didn't usually do it all by maps. Sorry?
Did you use thumbnails as well?
Yeah. So we have a list. Oh, right. No. Still there? Yeah. Okay, we're back. So we had a list of all the object detections, and as you sort of cycle through the list, it would pop up the detection image and its location on the map. So we could quickly look at the image, confirm that it was actually an object, and then look at the map and make sure it was localized correctly, and then send it away to DARPA. And that allowed us to really quickly go through the lists, through the object detections. And like Mark said, we use the keyboard, so we could just sort of enter for a positive detection and backspace for a rejection, and that allowed us to really quickly get through a lot of objects. And I think in a single hour, we can probably manage about 600 detections.
Awesome. Just leave it open to other teams to go through as long as Nebula gives us.
I can speak for Marble. For us, our interface, we made sure that we had an image for each artifact, which lets us really quickly filter through them. And then each artifact had a separate cube on the map that we could move around very quickly with the mouse to relocalize it if needed, especially helpful for the Wi-Fi and the gas ones. And then we also clustered our artifacts by if they were the same detection from different robots, so our operator didn't have to look at them again. And then I'd say the last kind of piece was the ability to kind of enter a custom artifact. If we saw anything in like the first person video stream, we could do that pretty readily inside of our interface as well.
Awesome. Thanks, Sarah. Any other teams?
I can speak a bit about Cerberus. So since all our robots did the localization on board, we had instances where multiple detections of the same artifacts, but by different robots were sent to the human operator. So it was fairly easy because the location could be visualized on the map, and just with a few clicks just on the map, we were able to reject duplicate reports. And another feature we had was to spawn a virtual artifact and move it around in the map that by the operator to see or to change the position of a reported one and to report it back to DARPA. That was something we used for the final run.
Awesome.
For Team Explorer, for Team Explorer, it kind of sounds like we ended up with sort of a similar system to CSIRO. The human operator could go through, tag certain artifacts as come back to later, that sort of thing. And I think we really relied on the fact that our human operator was very fast in terms of keystrokes and that sort of thing. I think one thing that kind of really helped us was in terms of the image presentation that we gave to the human operator. So we really focused on trying to present images that were diverse in terms of viewpoint, in terms of like location from where they were captured. And then we also spent some time looking at post-processing the images actually in the UI. So looking at like image brightening, as well as zooming in on the actual bounding box that was detected, which could all be sort of done locally on the base station and avoid having to send back even more images over the comms network.
Yeah, so we have kind of similar experience. We also allowed the operator just to click on the map and to see directly the detected object and the representative tumbile. We presented only a single one due to the network bandwidth restrictions, and we also provided some tools for adjusting the brightness of the image and so on. We found it quite useful because some of the thumbnails were quite dark.
Okay. Any other teams want to jump in?
Team CoSTAR. We shared a lot of similar experience on how to organize the reports based on the rejected, pending, or submitted. So as I presented, we also have like a contents group, so we can the operator can have different options to do so. And as also said that each report we have like 4 thumbnails. So the thumbnails will actually adjust it to be like small enough for the communication network, and also being when it comes to like really small objects that our human operator Kion still can be able to detect that. So we adjust that like this resolution like perfectly for our system. Then other things we also like be able to like click on the map to create a new object even though we didn't have any detection for either type of artifacts. I think Daniel and Barry also in the call, and they actually observe a lot how Kion used the UI. I'm not sure also have some UI people here can comment on more on that.
Yes, so some comment, Daniel here from Team CoSTAR, some comments that we saw the operator in practice didn't have a lot of time to do any adjustments, and that's the strategy that Sami described provides several options. As he said, many times we detected one object, but also given the density of objects, the operator might find other objects in the view, and we found very useful to be able to put objects in the view. And in particular for the Wi-Fi, we were submitting the highest intensity, but we saw that given the properties and how it bounces, we saw that many times we not get very close, at least in the environment we're testing before. And for most of the Wi-Fi and gas detectors, we let the operator to analyze and see the intensity of all the measurements and send what it thinks is the best, given of also the bias, knowing that the human intuition that, for example, for the CO2, the signal is going to be, the detection is going to be on the entrance of a room that is going to be very hard to put in the algorithms.
Fantastic. I realize we're going about 5 or 6 minutes over time. I just want to give a chance to any other teams who haven't spoken on that last UI one. They want to go, otherwise I'll hand back over to Melinda, and I'll try to copy some of the questions that weren't answered over to the Slack channel. I encourage people to go there for some more extended discussions in threads off on some of the different questions. But it was really interesting. Thank you so much, everyone. I think it's some good research areas going forward.
Thanks, Ben. Look, I think it's been a long day, a long night for us here in Australia. I think it's been wonderful. I think it's been great. I thank everyone who participated, all the moderators, all those who helped. Just to give you some numbers, we actually had 295 registrations on our Eventbrite site. But usually it's about 50% for attendance for this sort of workshop. So we had a peak of around 120 people on Zoom. We had I think about 15 people at one point on our YouTube live stream. So this is a distribution of where people dialed in. So as you can see, it's pretty global. So pretty much every time zone I think it's represented here, which I think is amazing. I think we talked about all the technical stuff that we did over the last 3 years, which is wonderful. But I think something that we achieved through this is something beyond that, that is community building. I think some of us probably would have met each other in academic conferences and all of that. But I think today's audience was a bit beyond that, which I think is great. And I would really encourage everyone to join the Slack space. The Slack space already has more than 200 people on that, and that'll be an ideal place to carry on the conversation, keep answering the questions that weren't answered. And I think Peter had a comment earlier that the panel discussions that we had for like 80 minutes usually would warrant a full day workshop. So on that note, I think do consider having joint papers and other workshops on these topics. Use the Slack space as a way of communicating. And on that note, I'll probably hand over to Kostas to say a few words about papers.
Yes, before I say that, let me also thank everyone, both the team members and everybody who joined, and especially you, Navinda, and the CSIRO team for organizing the summit in such a nice fashion. So for the papers, we are working already on the organization of a new special issue for the DARPA SubT Finals, and both the technologies that were developed and also the lessons learned, exactly what we discussed also today in a distilled fashion. And in that, I think we also emphasize contributions that maximize the reproducibility, such as open code and open datasets, especially as those further support the development of community of researchers that push for the same direction and same research. So with that, we will keep you posted about these updates, and I guess we'll find a way to communicate with everyone who is interested to both make sure that people will submit their contributions, but also to read the contributions once published.
Thanks, Kostas. And as next steps, on our YouTube channel, we already have the summary videos from all of the finalist teams. And what I'll do is I'll try to post the video. Give me a few days because I just realized I'll have to deal with a 9-hour-long video file from the recording. In hindsight, I probably should have stopped the recording in each of the breaks, which I didn't. So give me a bit of time. I'll try to chop it up into the separate panels and then have separate videos that people can view at leisure. I would also like to take this opportunity to thank DARPA. I think without them, we wouldn't have this. We had a lot of fun over the last 3 years. We might still have Victor on the call. I don't know whether Victor would want to say a few words before we close. Victor, are you there? Maybe not. But again, I think we all agree that DARPA did a fantastic job in organizing this challenge, and especially the finals, which was fantastic. Is there anything else anybody wants to quickly add before we close? Sean, anything you want to add?
Sure. Yeah. Again, thank you, Navinda, you and your team for organizing this. Wonderful. Kostas, thank you for taking the lead on the special issue. Wonderful to see everybody. Really appreciated all the students and postdocs that were able to present, especially the undergrad from Coordinated Robotics. Sarah, you did a great job. Again, thank you to all the students, and wonderful to see you all. Looking forward to collaborating in the future.
Very good. Anyone else who wants to say any closing words? Cool. Thank you very much, everyone. Well, hope to see you on the Slack space. Have a good night, good day, evening. All right, see you guys.
Good day.
Thank you.
Yeah, bye.
Thank you. Bye-bye.
Thank you.
Have
Bye.
a good night or morning.
Goodbye.
Thank you, everyone.
Thank you, Ben.